Hello guys, let's start the warm-up for today. So in 3 minutes we will start. Okay, hello Love, hello Alin, hello Masayuki.
Hello.
Hello, hi.
Hello. Hi. Hello Maju.
Hi
Hello.
everyone.
Hi. Finally we can see you today.
Yeah, I'm glad to be here today.
Yeah, congratulations for the volleyball championship that you team win.
Thank you.
Nice. So, hello Yuka.
It is nice to see you back for the second day of the event, including Maju, which we missed yesterday.
It's nice to be here.
And Masayuki, which lasted up until the end yesterday. He's only missing in the final picture.
Yeah.
Don't worry.
The workshop, so before start off.
You stayed quite long. It was past midnight when we spoke last time. We appreciate the effort. We know that it's not easy for scheduling an event this long that will work for all time zones. So we want to thank you all for joining us.
Thank you. Yeah, I think, hello Mark.
Hello.
I think Masayuki was more than 2 a.m. when he, right? The last time we asked the time for him, it more than 2 a.m. already. Mm-hmm. He stayed very long. And today, I hope you still with us at the end. And I think today, Alin said I am a little bit confident on it, but I think maybe it will finish 3 or 4 hours early because they are very very fluid one after the other, so it will finish early. Let's see.
Yeah, that's it. I think that we are really close to the first start time for the first session. The first session will be presented by my colleague, Masayuki Ishikawa, and he will talk about running NuttX with MMU on QEMU. Masayuki, do you want to play the video yourself?
Yes, possible. Yeah, sure.
If you can do that, it will help us a lot because yesterday we ran into some technicalities. The person that runs the video cannot work on anything else, and the person that streams.
Let me share my screen.
Thank you very much. Compared with yesterday, today we have the majority of presentations live. And we also have a demo that will come after Koizumi-san's presentation.
Yeah.
So shall I start?
Yes, you can start whenever you can.
Okay.
Thank
Hello.
you.
Thank you for joining this session. My name is Masayuki Ishikawa from Sony. Today, I'm going to talk about running NuttX with MMU, Memory Management Unit, on QEMU. Here, QEMU is an open-source processor emulator, and we can run NuttX on it. About me, I have several technical backgrounds, including embedded systems. As you can see in this slide, I introduced Linux, Android, and NuttX to our audit products before. Since 2016, I've been joining several conferences such as Embedded Linux Conference and NuttX Online Workshop and talked about how we applied NuttX to our audio products, and also talked about feasibility studies such as SMP and networking. Here is today's agenda. First, I introduce MMU and MPU, which is Memory Management Unit and Memory Protection Unit, and Netx build types, as well as board support history. Then I explain both V7A Netx and RISC-V Netx implementations. After that, I will show you how to build Netx and show you demo video. And finally, I will explain future work. First, let me explain MMU and MPU. Perhaps most of you already know them. As you can see in this slide, MMU means a memory management unit, and its features are virtual memory management, as well as memory protection and cache controls. On the other hand, MPU means a memory protection unit for low-power processors, such as Cortex-M. It does not support virtual address translation, and it supports region-based memory protection only. And also please note that RISC-V MPU is called as PMP, physical memory protection. The feature is almost same as ARM MPU. In NuttX, we have three build types. They are flat, product, and kernel. In this session, I'm going to focus on kernel build type, but let me explain flat and product build type as well. And most of you are using the flat build type, which does not use MPU or MMU. Regarding application address space, the kernel build type has per application-based address space by MMU. In the flat build type, application runs in privilege mode, which means that there's no differences between application code and kernel code. However, in the protected build type and the kernel build type, application runs in unprivileged mode. And also, memory protection can be done by MPU or MMU, respectively. Regarding loadable application support, in the flat build type and protected build type, it is optional. However, it is mandatory for the kernel build type. Finally, task creation API support is slightly different between the build types. In the flat and protected build type, we can use both task create and POSIX spawn MP. However, we can use task create for the kernel build. We cannot use task create for the kernel build type. The next slide shows an example of the flat build type. In this case, user applications are statically linked to the kernel and run in the same address space, which means that applications do not use system calls and are not protected because MPU is not used. As you can see in the linker script and the map file, kernel code, for example, are full context restore, and application code, for example, ensure main, exist in the same area. In addition, a loadable application is possible that is dynamically linked to the kernel. This slide shows an example of a protected build type. In this case, User applications are statically linked to the NuttX user.bin, which is separated from the kernel. Also, applications use system calls and are protected by MPU. As you can see in the linker script and the map file, kernel code and the user code are separate. So please note that loadable applications is also possible. However, the applications are dynamically linked to NuttX user bin, which is not the NuttX kernel. The final one is the example of a kernel build type. As I explained earlier, this type uses MMU, and user applications run in their own address space. As you can see in the memory map figure, the init application and the hello application use the same virtual addresses. However, they are mapped to different physical pages by MMU. So this model is similar to Unix environment. Next slide shows ELF support differences between the build types. In the flat build type, undefined symbols such as printf in the hello application are resolved at runtime. In this case, symbol tables exist in the N shell in NuttX.bin, and application calls libc symbols directly. In the protected build type, undefined symbols are resolved at runtime. This is the same as flat build type, but symbol table exists in the N shell, which is linked to NuttX user.bin, which is separated from NuttX kernel. And libc in the NuttX user.bin uses system call here. In the kernel build type, libc is statically linked to applications because currently shared libraries is not implemented. In this case, undefined symbols are not permitted. And also in this case, system calls are used, which is the same as protect build type. This slide shows support history on config build kernel. The config build kernel was introduced by Greg in around 2014. However, the build type has not been maintained in a long time. And this year, I ported this kernel build type to server 6 core, which has Cortex A9, but I only tested with a single processor configuration. After that, Oki-san added SMB support to them. As for RISC-V support, we ported to iCycle board, and then I ported the RB-BERT environment, so which is based on QEMU. So before talking about MMU, we need to understand CPU mode. In ARM v7a architecture, there are many processor modes. In ARM v7a NuttX, we are using user and IRQ and supervisor and the system mode. If a processor mode is in a user mode, it runs in unprepared mode. In this mode, some instructions cannot be used. In the CPSR, this is current program status register, there is a mode bit field. And you can find the current CPU mode in the CPU register. So, and like this. This slide shows more concrete examples for V7A NuttX CPU mode. When the CPU starts with the reset handler, the CPU is in SBC mode, supervisor mode. This SBC mode also happens at the entry and exit of the SBC handler. In these handlers, we change the CPU mode to the system mode immediately. And when hardware interrupt happens, CPU change to IRQ mode and jump to the IRQ handlers. In the IRQ handler, we switch to system mode immediately. The system mode is used for kernel code, including kernel set. For example, idle task or HPWAC, so which is used for networking. And the user mode is used for user tasks, as well as the pthread and signal handlers. So you can see CPS registers like this in a GDB. The next slide shows an address translation for V7A. With MMU, we need to use page tables to map virtual addresses to physical addresses. In V7A architecture, two-level page tables are used for address translation. V7A defines a supersection that supports a 16 megabyte memory region for the first level. However, in V7A NuttX, we only use a 1 megabyte memory region for a first level table. Similarly, we only use 4 kilobyte memory page for the second level, even though V7A supports 64 kilobyte memory page. Here, the first level table has 4096 entries, which means that the table size is 16 kilobytes. And the second level table has 256 entries, which means that total table size is 1 kilobyte. After setting up tables, we need to set TTBR, translation table-based register. The next slide shows a memory map for Serverless 6 quad N-shell. The Serverless 6 quad support board uses NXP's MX6 processor, which has OC RAM, on-chip RAM, as well as SE RAM that locates following physical addresses. Regarding virtual addresses, I assigned addresses as follows. In the kernel area, there are L1 page table and kernel text data heap and page pool, whose addresses are the same as physical address. Regarding a user text data heap, which are allocated from page pool, like this, and map to a different page memory with MMU. When V7A NuttX boots, the start function in head.s is called. This is a common logic for V7A NuttX. In this function, the L1 page table is initialized here, and finally set on TTBR here, translation table based and register. As I explained in the previous slide, L1 page table exists on the i.mx6 OCR. As I explained, there is the page pool in the SDRAM. This is a memory pool used for LT page tables and LT pages for user, text, data, heap, and granular allocator is used to manage the pool. Regarding the page pool API, there are the following APIs. And for example, when loading a ELF file, for example, MMPG-alloc is called to allocate pages for text data heap for it. Here, please note that on V7 and NuttX, the L1 page table is statically allocated, and the table will be updated instead of updating TTBR when switching a context. The next slide shows the kernel heap and stack. In NX stat, up allocate k heap is called to allocate the heap. In this case, in the case of sublet 6 quad kn shell, the heap exists between G idle stack, so which is at the end of the kernel data area, and page heap, like this. To initialize the heap, kmm initialize is called. In the kernel code, kernel memory is allocated with kmm alloc. The kernel stack is allocated with up address and kstack alloc, and stored to TCB XCB kstack. After that, switch to the kernel stack during system calls in syscall.c. The next slide shows the user heap and stack. The user heap is initialized with initialize when user application starts. The heap's address and the size are configurable in defconfig, so like this. The user stack is allocated from the user heap and then stored to TCB stack alloc PTR, which is same as flat build type. As you can see, the user heap address, user heap area can be seen in the core stack, like this. The next slide shows Struct task group S, which is allocated when creating a task. The struct holds such as child exit status, environment variables, file descriptors, file streams, sockets, and address environment for MMU, so which is very important for the kernel build type. And please note that if a task creates a pthread, the thread will belong to the struct of the current task. The next slide shows struct group addresses, which is a CPU architecture specific struct. In the v7a NuttX, the struct retains MMU information for task group. More specifically, it holds L1 page table entries for the user apps text data and heap. And there are some APIs for the struct. For example, app address and creates address environment when loading a user application. In this API, it calls address create to allocate physical pages with MMPG-alloc. Another example is app address select, which selects an address environment when switching a context. Regarding context switching in NuttX, there are some APIs associated with it. For example, when application calls read system call for the URL driver, then the driver calls next some wait and wait for user inputs. In this case, app block task is called from nxm wait, and it calls switch context to issue SBC instruction, supervisor call instruction. And when a user input happens, do IRQ is called, and then calls a group address env to change the address env associated with the task. In v7a NuttX, the L1 page table is statically allocated. Because of this, app address env select does not change TTBL, but only updates the L1 page table entries for user apps. This means that the kernel address space mapping is not changed. Also, please note that RISC-V NuttX implementation is different, which I will explain later. This slide shows the core stack for starting the init tasks. In Server 6 quad KN shell, it uses a hostfs, host file system, to mount system bin, then called exec spawn. As you can see from this core stack, the kernel code is running to load the init task. This slide shows core stacks for starting Hello app from the init, so which is known as nshell. In this case, nshell calls project spawn to load the Hello app. As you can see from these addresses in the core stack, the user code is running. From here, I explain about RISC-V NuttX implementation. In the RISC-V specification, there are some MMU modes defined, such as SB32 for RB32 architecture, and SB39, SB48, and SB57 for RB64 architecture. However, in RISC-V NuttX, currently only SB39 is implemented. To work with MMU, RISC-V needs to use S mode, supervisor mode, to run the kernel code. However, we need to use M mode, the massive mode, as well to access such as mtimer, mHeartID, so on. In RISC-V, we need to use eCore, environmental core, to change the CPU mode and jump to exception handler to proceed. This is a big difference between RISC-V and ARM. To access a for example, mtimer register from S mode, so we need to use, for example, OpenSBI, so which is open source supervisor binary interface, or we need self-implementation for QEMU RB. As I explained in the previous slide, NuttX implements SB39 mode. This mode uses 3-level page tables that are L1, L2, L3. Each table has 12 entries, and each table size is 4 kilobytes because entry is 64 bits. For example, L1 entry maps 1 gigabyte, and L2 entry maps 2 megabytes, and L3 entry maps 4 kilobytes respectively. RISC-V has SATP supervisor address translation and protection register to specify L1 page table. The next slide shows memory map for RB bird KN shell configuration. This configuration uses 8 megabyte RAM, but the size is configurable. Also, virtual address for PG4 and the user text data heap are configurable in defconfig. The address mapping is almost same as Sublet 6 quad, but it does not use a dedicated L1 page table. In RISC-V NuttX, page tables for the kernel area mappings are statically allocated in the kernel data area. Here. This implementation is different from v7a NuttX implementation. The tables are configured in QEMU RB kernel mapping in initialization. Because the tables are statically allocated, MMPG alloc is not used for the table. And when creating a user task, copy this kernel mapping to the user task in app address and create. The next slide shows Struct group address and S for RISC-V NuttX implementation. This Struct is architecture specific and different from v7a NuttX. In the Struct, there is a member called SPG tables here. In the case of SB39, 2 page tables are allocated with MMPG alloc. SPG table 0 holds kernel and user L1 mappings, and SPG table 1 holds user L2 mappings. And when creating a user application, app address and create is called. In RISC-V NuttX, this API calls copy kernel mapping to copy PGT L1 to SPG table 0 for the kernel area mappings. Then call map SPG table to associate SPG table 1 to SPG table 0, and finally allocate memory for user text data heap from PG table, a page pool with MMPG alloc. And when switching context, app address and select is called. In RISC-V NuttX, it just restores SATP supervisor address translation and protection register with SPG table 0 in the address end. It's very simple. This slide shows how to build the NuttX kernel with applications for Sublet 6 quad Netk Ensure NSP, which is used in the later demo. First, we need to configure and build the kernel, and by executing configure.shell, sh, and make. This step is same for flat build type. Then export the libraries and header files by executing make export. Finally, you can find NuttX, and NuttX export the version number /z under the NuttX directory. After that, execute mkimport.sh to import the library and the header files, and then make applications by executing make export. Finally, you can find applications under the bin directory, like this. Before starting the demo video, let me explain the demo scenarios. In the demo video, I will demonstrate the NuttX SMP kernel on QM 6.2. The kernel is configured to use ARM Cortex-A9 4 cores with MMU, and total CPU usage can be seen with the top command on the host OS, so like this. In the demo video, I execute several Shell commands, as well as applications. The configuration also supports networking. In the demo video, you can see the Telnet demo and the IPAR are working. So let's start demo video. So first, start the QEMU and see CPU usage with top command this. And you can see Sublet 6 quad configuration is running. So help and PS. So 4 quads are running, and 3 page memories can be seen, and the host FS is used, and also we can use networking and how applications running. And SMP, this is application to test a merge core. Okay, so 4 core is currently running. And get prime. This is only one thread is running. And then 2 cores are running. Please see here. 2 cores are running. And get prime 4 runs 4 threads. So 4 core is running. And get prime 5. This is also 4 cores running, but takes more time to finish. Then log in with Telnet. And you can see Sublet 6 core. And also you can see Telnet is running. And yes, SMP application also can run. And run IPAR in server mode. And then run IPAR client on host processor. And you can see almost 100 Mbps can achieve. And you can also run several commands on serial console. And if you run a SMP command, this will use a 4 processor, so the performance will be degraded, slow down. But soon recover to after finish SMP application. So now IPAR application is not running. Yes, PS, and so finally exit Telnet daemon. So finally, let me explain the future work for the build kernel. I think the biggest one is we need to improve stability issues, because sometimes a kernel crash happens with data abort. Perhaps there's something wrong with context switching. Regarding risk 5, as I explained, OpenSPI support is needed for QMRB configuration to work with Mpu. Currently, QMRB works with MMU, which does not, I didn't demonstrate today, but Mpu does not work. So also, SB32 should be supported for RB32 architecture. Other CPU architectures, such as ARM64 and x86 64, might be desired. And new features such as shared library and paging would be useful to improve memory usage on NuttX. That's all for my presentation. Thank you.
Thank you, Ishikawa-san. It was a really nice presentation. And now, if Alan or Maju can help me with the questions from the YouTube channel.
Okay. By the way, I am give some help to Maju to use the comment chat, and maybe you need to update the comment link. Okay,
I already did that.
She's getting the link. I send you a link, but it is from my computer. I will send you a link to you in a few minutes. But we can help here with the question.
Please.
The first one is, do you need to manage the TLB? That is, do you need flushing on context switch, etc.?
Yes. TLB flushing is done in the NuttX kernel libraries regarding MMU management libraries. And as far as I know, currently, as I mentioned in the slide, B7 NuttX updates our L1 page entries when changing our user context switch, and which means that entries for L1 level entries for user address is updated. So this will update flushing the TLB. This is my understanding.
Okay. Thank you, Masayuki. Any other questions? Please write here to Masayuki respond.
I would like to ask a question.
Please, Michael.
Yeah, it's great work, Masayuki. Really amazing. But do you know perhaps if you or anybody else did look into using the MPU to separate task groups from each other for normal microcontrollers where you don't have the MMU?
Yes, as I explained in some slide very earlier, there is a so-called protect build mode, so which is very useful for non-MMU, but only protected by memory protection unit. So this maybe should I show us a slide again?
Yes, sure.
Yep. No, let me.
Sorry,
because my slides are very. There is many topics there, actually, and so perhaps in your case, and so without MMU, but only supported by MPU, this mode is very useful for such a case. Yeah, actually, as maybe next slide. No. Yeah.
Mhm.
So application area. So
Yeah,
that will suitable for more smaller SoCs such as Cortex M architecture.
Yeah, I'm aware of the protected kernel build, but in the protected kernel build, you only separate, let's say, the applications from the kernel, but not the different processes from each other.
Mm-hmm.
And it would be conceivable to reconfigure the MPU on a context switch and make sure that the different processes cannot access each other's address spaces or address regions, let's say. I was wondering if anybody has looked into that one because I think NuttX as of today only differentiates between the kernel space or the protected space and the user space, but not separates the different applications in the user space from each other. You know what I mean?
Yeah, actually, as perhaps this slide can explain, and protect build is just only separated from kernel and user. So this means that the user applications are, for example, this is a Hello application here, but also as another application, can be linked to a user model application. So that will be, a big difference between protected build and the kernel build. And as you know, so kernel build is different. Yeah. So in this, as in kernel build type, so as you know, each applications are separated. So this means each application uses a separate address space and also protected by each other. Yeah.
Yes, and I was wondering if I know from Trusted VMware M that they have partitions with services in them, and they separate the different partitions via the MPU. So there's basically the protected or the privileged mode where the partition manager runs, and then separate MPU regions for the different partitions. And when you have a context switch from one partition to another, then the MPU is reconfigured so that partition 2 cannot access partition 1 memory. Yeah, and we don't have such a support in NuttX as of today, as far as I'm aware. And I was wondering if anybody did look into this already. Yeah, but
perhaps in my understanding, as you know, MPU, ARM MPU, maybe it's the same as RISC-V, so PMP, so physical memory protection, because there is only 8 or up to 16 regions, and maybe so each region I cannot remember, but so there is a alignment restriction for each region. And so it might not be, how to say, not easy to configure for some cases. Yeah.
Okay. Yeah, but you can reconfigure it dynamically on a context switch, the MPU, so that you have.
Technically possible. Yeah, but not implemented. Yeah.
Oh, okay.
Yeah.
Thank you.
Ali, I just sent the new link for Maju. I saw you update the previous one, right?
Yes.
But the new one now is from Maju. I was testing.
Updating it now.
Yeah, and
it
so
is updated.
Okay. Please, Maju, try again clicking in the in the message.
Yes,
you want to select.
It works.
Yeah, it's working.
Question for Masayuki. What happens when one user app crashes in this kernel build?
Yeah, actually, I still not a deeper test for it, but ideally, user application crashed in when running in user context. It should be only crash application, but not affect to any other application or any other kernel area. Yeah. But we need to test more.
Thank you for the explanation. It is a really nice area, and it offers quite a lot of insight on protection and different modes. Thank you again for the presentation. Do we have other questions?
I think that's only it. We don't have other question. So
in that case, I think that we should move to the next presentation from Niall Ferguson. I hope that I pronounced it correctly. And he will talk about loading of 80 dynamic shared objects.
Yeah. By the way, I am just closing the acceptance of responses. Okay, in the form. This time we got only 11 response. By the way, for people that are just coming here today and don't know the rules,
I can put that slide.
that should be a good idea to put that information, because we just started today, and there are many people that are arriving here today and don't know the details yet.
Sure, it's a good idea. Just give me a few seconds. So we have a raffle. Yesterday we had a raffle for 5 presence LTE boards. Unfortunately, one of the winners was from an area that is not suitable for us to ship due to the LTE certification. So for today, we will have 6 presence LTE boards. And on top of that, we have the grand prize, one Xiaomi smartwatch S1 Pro. So guys, if you want to participate to the raffle, you have to find the words that we will send during the day. There will be 4 words in the last 4 presentations, and 3 of them are needed to enter the raffle.
Alin, just on the table I saw here, I'm looking the table of winners, and yesterday it was Eric Ferdinando, Yernik, our speakers, Lorival, Robert Lippi, and Roberto Butcher. I think people here in Brazil also are not cannot receive it because it is not certified in the Anatel yet. So we need to. I will find some other board, some way to get other prize for them. Okay.
Yeah, sure. I'm quite confused because we actually shared the rules before the event.
Yeah.
But, how many people are from Brazil?
Let me check. Lorival is from Brazil, and I need to check now. Only Eric Ferdinando.
Okay.
Let's open. Just a second. Let's open the confirmation presence. Eric Fernando from Brazil as well.
Okay, so we have 8 boards available for today.
Mm-hmm. By the way, these guys that received that win yesterday, they still participating of the final raffle of the Xiaomi smartwatch. So this smartwatch there's no restriction. Okay, so everybody will be able to enter to win this smartwatch. Okay. Thank you very much, Ali.
Thank you. Please keep the people that won in the list, and we will try to figure something out, even though they cannot win an LTE board.
Yeah, I will. Thank you.
Thank you. Now I think that it is time to start the next presentation from Neale.
Yeah. Hi guys. Am I audio fine for you?
Yes, we can hear perfect.
Okay. I'll just call up my app and we'll exit away. Is my screen up on there now?
Yes. Please put it full screen.
So far, so good. Welcome everybody, and thank you for inviting me to talk at this workshop. My name is Neil Ferguson. I am from a little consultancy called Sine Nomine Associates. If anybody knows Latin will recognize that the name of the company means a company without a name. That's because we have 2 co-owners who were classics majors who couldn't agree on a name when they went to register the company. So we're stuck with that, and we ever deal with is able to pronounce the name of the company the first time, so it's always a long explanation of what's happening. My background is I'm a long-term maintainer of the S390X port of the Mono JIT. Now, if anybody's not familiar with S390X, it's the IBM mainframe. So I look after the very big end of town when it comes to Mono and the JIT. I started working on it in 2003 and have been working on it since, and ultimately have worked with both IBM and Microsoft to have .NET include this architecture as part of its community release. So a lot of big work, end of the town work, but also have done a lot of work on embedded systems and as well as the typical Intel systems. For example, a few years ago, we added AOT, ahead of time compiler support, to the SH4 platform for a client. Technically, it was a lot of fun. We learned a lot of things about the platform you never learned before doing low-level stuff. Also provide a number of runtime support to a number of clients. So people running Mono in their production environments, they want support for the Mono runtime, we do that. I had lived in the US for 20 years up until 2019 when I returned to Australia. But as you can tell, this accent is definitely not American. It's a strange one, and it's coming to you from southern Queensland at the moment, where it's just going about 10 o'clock at night. So if I start to drift off, please forgive me. I began working on this current project for the Wilderness Labs folks in early 2021. And if anybody hopefully saw Mark Stevens' presentation there, he gave a great in-depth description of Meadow and the type of stuff that we are involved in. So what they brought me on board for, because of my past experience with JITs and stuff, was to provide ahead-of-time compiler support, and that requires the ability to use DLOpen to bring in dynamic objects. And so the first thing I did when I looked at doing this was try to DL open with such an object and saw that it did not work with NuttX, or at least the level of NuttX we're running. And I think Mark indicated yesterday, we're running a little bit back level from what's current. So there are going to probably be a few things I say here about support within NuttX. You're going to say, well, yeah, that's there now, but this is all coming from the point of view of the NuttX that we started on and have been working on since. So I quickly found out that we needed to expand DL Open support to be able to support this ahead of time compilation. And that also involved additional relocation types that currently weren't supported within NuttX. Also needed to provide some limited external reference resolution, such that if the AOT module had references to things like printf or memcopy, we were able to resolve those at runtime. What we didn't need and what it didn't provide is support for nested shared object dependencies, such that if my shared object had a reference to another shared object, I won't go down that track to be able to provide that resolution. So it's very much focused on what was needed for this one particular application. So it is certainly not a general purpose solution, but hopefully it's something that could be turned into a general purpose solution with a little bit of effort. So again, for those who did not see Mark's presentation yesterday, I'll just quick single or couple of slides talking about the Meadow environment. So Meadow is a complete Internet of Things platform with defense-grade security that runs a full .NET standard. So applications run on our embedded microcontrollers. They're developed using the same type of tools that people running on the desktop. So you're running Visual Studio or VS Code. You're deploying to these devices. You're debugging these devices all from that IDE environment. We provide a complete plug-and-play Internet of Things library with a huge library of peripheral drivers, industrial control, graphics, DisplayPort, etc. This means that the application developer is strictly worried about functionality of the device rather than having to go down and plumb at the very basic levels there for you. So what we're trying to provide the application developer with is an environment where they can write code such as this and have this type of thing work with the devices. So as you can see, all the application programmer is worried about is purely functionality and letting the Meadow Foundation and Meadow Core libraries take care of all the bits and pieces. So the motivation for this, my part of the operation, has been speed. Mono is used to drive these applications on the F7 board, which is running the Thumb2 instruction set. Now, Mono itself had no JIT or AOT capability for the Thumb2. It certainly has an ARM support, but currently had no Thumb2 support, so that speed became a big issue. So, for example, we have the two boards running the same application here. Just keep your eye on the pictures in the little LCD screen in each of these boxes. On the left-hand side is one running without our JIT AOT support, and on the right is one with it. So just quickly note the pictures at the bottom when this thing starts. And the JIT application is finished. The interpreted application is still running. And running. And there it goes. So the motivation for providing JIT AOT was the speed up requirement to be able to run some of these time-sensitive applications very quickly. Now, in interpreted mode, there are a number of applications that are quite happy to run interpreted mode. So our use case is we're using the F7 device, we're using Mono to run these .NET applications. Initially, everything's running in interpreted mode, so to provide the increase in speed so that these applications that are time sensitive, we needed to provide a JIT and or an ahead of time option. Now, the ahead of time option requires the ability to load .so objects. So when you build these things, you end up with these shared libraries. These libraries need to be loaded by Mono and connected to and accessed. Currently, NuttX only supports the relocatable file style of objects, so that when you run DL open, it actually does an explicit check. Is this an ET-rel object? If not, return saying cannot do. So as I mentioned, Mono already has ARM64 support, but to provide a JIT facility, we needed to provide the underlying code that's going to produce the thumb2 instructions. Now, there are a couple of options to this. We can start from scratch and create a whole series of runtime files that implement the thumb2 ABI, etc. Or we reuse existing code in there and throw in a few if-defs, and we wanted to keep this as a minimum. So that's the option we chose. So we're using the same Mono drivers that they use for ARM, not ARM64, obviously. So the macros that they created to issue the instructions are reused, so we didn't have to create a whole heap of other things and extra code. We used the same trampoline code, and we're handling both 32-bit and 16-bit instructions. And this is the big change from Mono's existing ARM support, where everything is 32-bit. So there's a lot of assumptions of alignment and things like that. So a lot of work went into handling those cases. We also needed to cater for the differences between ARM and thumb2 instructions. So certain instructions are available in the ARM environment that aren't available in the thumb2 environment. And I think we had a reference to that in yesterday's first presentation of the workshop. In addition, there are a couple of instructions that do exist in thumb2 that don't exist in ARM that became quite useful. Just off the top of my head was the floating point rounding instruction, VRND, I think, that actually proved very useful in the Mono environment. There are also register restrictions, such that certain registers can't be used in certain instructions. There seems to be a lot of differences or restrictions on using the instruction pointer, the stack pointer, etc., when in certain instructions. Displacements are different. The maximum size in an ARM environment is different to the maximum size in a thumb2. And conditional instructions, the if-then, if-then, else type of instructions have to be used in the thumb2 environment that aren't used in ARM. So there are a whole lot of issues to get this support happening. We needed to provide a JIT capability so that the AOT could be generated using the stuff that JIT put out, etc. There are two other options when creating a ahead-of-time compiler. You can use the LLVM in two modes, LLVM and LLVM only, which use the Clang compiler to generate the thumb instructions, etc. So we've got those three capabilities here, but the JIT we provided first because it works without even needing an ahead-of-time capability and provides a certain speed up to the application developer. So just to give you an idea of how this all fits together, once your application's built, you end up with a series of DLLs, MS Core Lib DLL, your application DLL, and certain other class library DLLs there. And their footprint is rather huge if you leave them by themselves. Obviously the MS Core Lib is very, very big because it has the core of .NET running there. But your application itself doesn't use a whole lot. And it seems pointless to load in megabytes of code onto your small board just for the purposes of running the application. So what we do use is the Mono linker to shake out only that which is necessary within the application and creating a much smaller footprint there. So we take those big DLLs, we run it through the linker, we end up with some smaller DLLs that we put into a directory. And at this point, we can then perform the ahead-of-time processing. And as I mentioned, we can run it in one of three modes. And in this instance, we're going to be running it in the just-in-time compiler mode. And what that means is Mono will start up, will pull in the application and generate the machine instructions and point Mono at them, or point the AOT part of Mono at them, and it will then generate the necessary object decks, which will then link them and ultimately produce .so files. So after the process finishes, you end up with .so files, and you can look at them through the readelf command, and you can look at the headers and get an idea for what the requirements are in terms of the size of the text areas and the data areas. The other thing we're interested in now, because we're using dynamic objects, is the dynamic symbol table. And here again is one difference and one shortcut we have been able to make for our support for loading these objects. Mono's AOT objects are fairly self-contained. They don't have a large number of external or exported symbols. They basically have one that they're interested in. And this one is Mono AOT file info. And what the loader does is take that information, that address, and we'll be able to locate a whole lot of information about the object itself and all the methods that live within that object. So we don't have to worry about exporting a lot of symbols and then creating updating the PLTs and GOTs and all those type of things you generally need to do with shared objects. So again, an expedient thing for us to do, which precludes it from being totally general purpose. So again, here's what Mono's doing when it loads an application. It will go there and have a look to see if these .so files exist. And we'll go and find if mscore.lib.dll.so exists on your file system. And if it does, we'll try and issue a DLOpen request for it. At the moment, prior to the support, it would fail because you define an object with an etdyn type in its header. So what this support has done is been able to add this etdyn support. So what we do now is we read the header and determine if it's an etrel or an etdyn object. If it's an etrel, then we just palm off to the existing code that lives in the system to take care of what it does already. If not, we go and perform our functions, and I'll give it a schematic shortly, but just in brief, we're loading the text and data area, we're performing relocations, and we're resolving any external references. So diagrammatically, it looks like this. So item 1 down the bottom here, we have the shared object living on the file system containing the ELF headers, the relocation table, symbol tables, and relocation information, as well as the text and data sections. So our code will go in and read those ELF headers and determine how much space is required to load the object, the executables, and the data area in for that particular object. So we suck those into the system, into memory. We then read through the symbol table looking for any exported information. And if we export a symbol, we tuck that away, and I'll talk about that in a little bit more depth shortly. We also go through the relocation information for symbols, and we really relocate them according to the symbol type so that the addresses match where they are placed in actual memory. We also look for undefined symbols, so unresolved external references. And this is, again, something we've implemented that is probably not as general purpose as is necessary, but works for our particular instance. We take that information and we find these external references that we can't resolve, and we go and look through a global symbol table. And we will do a binary search because of the way the table is created, locate that information for that entry point, update the object within memory, and mark it as resolved. And so by the time this entire process is finished, we have a fully functional working object sitting in memory that the Mono system is able to access and use. If we were to find an external reference that we can't find, we tell Mono, it prints a message, and we default back to the JIT rather than ahead of time operation. So it doesn't break our application if this thing can't be resolved. We take note of the unresolved reference and we try and find out why that is as it is. I'll talk about now the global symbol table that we've created that helps us resolve these external references. If you look through the symbol table of that .so we've created, you'll find things like memcopy, as you can see down the bottom there, marked as undefined, has a 0 address and an undefined type. So we go through and scan through our symbol table as part of the DL open operation. What we are trying to achieve here is the ability to create these shared objects without statically linking them. So when we run the AOT in JIT mode, everything's self-contained. There are no external references because everything's taken care of in the Mono runtime library. When we're running in LLVM or LLVM only mode, there are a heap of external references like printf, like memcopy, etc. there that need to be resolved. One option was we could have created the shared object as statically linked and linked them against the .a files that NuttX produces, in which case all these DLLs end up being unnecessarily bloated. We have multiple copies of memcopy sitting in memory and there. So our object was to eliminate this need to statically link by creating a global symbol table. We also necessitated the inclusion of the libc++ library at the runtime link because the LLVM only code has certain C++ dependencies. What the global table is simply a module called modlib_globals.s created by a script. The script searches through the runtime and the .a files created by the build process, filters out unwanted entry points, sorts them so they're suitable for use by bsearch. So here's what part of an excerpt of that table looks like. So at the beginning, we have all these names of the entry points, which we will then match during our search process. The table itself starts down here, a global table. It consists of a pointer to that name and the address within the NuttX runtime where that symbol lives. In addition to the global symbol table, each module has its own dynamic symbol table. So as you saw earlier, mono_AOT_file_info was one such and probably the only exported symbol. And we keep that in a data structure associated with the module, such that when Mono loads an ahead of time module, when it uses DLSym against that handle returned by DLOpen, we're able to find that symbol, and Mono can then do its work of determining where all the methods live within that particular object. So we've got two things happening. We've got a global symbol table that contains all those typical libc functions that the AOT object may be calling, and we use it to resolve those at load time. And we also create a local module symbol table containing all the exported symbols of that particular object. At the moment, as I said, with Mono, we only had one, but it's general purpose enough that if it has multiple, we were able to store them and keep them available. So a quick look at under the covers here, what's happening, what we had to add to NuttX to achieve these things. And I won't go into too much detail because it's a fairly dry topic, but I'll try and hit the highlights of what was necessary to provide this particular function. Well, first of all, we needed a global offset table, and that needed to be added to our .ld file for the linker so that it can be present when we start doing PLT type things. We had to add some additional definitions found in shared objects, the load types, the program header types, etc., that currently weren't this is what needed by NuttX, but in our particular example, we needed to add them to support the these dynamic objects. We needed to add handling of the R_arm relative and arm jump relocation types. These are fortunately very simple ones to add to the code. The code's nicely structured as a series of case statements. We just had to add our particular cases in there and have them added. For the DL functions, the library routines, we needed to do things like for the close operation, we had to make sure that the symbol tables that we created are freed, so we don't leave memory hanging around. For the open, we needed to add some debug code. The existing DL open has a nice little debug feature where it will print a whole lot of debug information about the objects. We just added some more to cater for that, our particular cases there. And we also obviously needed to let it understand that there were things called etdyn objects. We added new fields to the data structure that manages these DL opened objects. We needed to keep information about the program headers and the exported symbols, etc., certain data section addresses that exist within a dynamic object, and some indexing information, because we're now searching through a number of different symbol tables. So we had to expand the symbol table lookup capabilities within NuttX to help us with the global symbol table. The important things we added here within the definitions in modlibs.h, there's a couple of new prototypes for new routines we had to create. An insert symbol table and a find global operation, so that when we load an object, we create its own symbol table and we're able to insert those into that table. And when we're resolving external references, we need to be able to find those things. So we added entry points there. The bind module, we were able to differentiate between the relocatable and dynamic objects. We extended the read sim to point to a given symbol table. As I mentioned, with dynamic objects, you can have multiple symbol tables, the dynamic symbols, the local symbols, etc. And we also needed to add a function that was going to go through and do the relocation of the symbols, much in the way that there is a similar relocate function for the etrel type objects. One of the major changes we made to functions was that we used the program header information rather than going through the section headers to determine how much memory we needed for the text sections, text areas, and the data areas for the object. So that was, as I mentioned, probably the biggest break from the existing processing that we performed. So notably, in modlib sections, we no longer call it load S headers, but load headers to reflect that. So we use the programmer header information to extract important sizes and addresses. A lot of work happened in the symbol processing. We added exported symbols so that DLSym could look things up. We added offset information so we can easily locate symbols without having to go through and repeat calculations every time. We added this insert symbol to create a symbol table for exporting symbols so that Mono can find things that it needs in there, and adding a find EP to resolve those global table information. Freeing things when we uninitialize a module at DL close time. Verifying, this is the first place it actually checks that the object you're trying to load is valid. So at the moment, it only checked for etrel. We now expanded that to say, look for accept etdyn, and we'll handle them elsewhere. And of course, this global symbol table. And relatively ugly, the way it works, that we created it, but it works. And as I mentioned, expediency over elegance ruled in this particular part of my project. So the global symbol table is created by a script that traverses all the runtime. So it looks through the runtime.elf object, looking for things. It looks through the .a files created by the build. We use nm to extract the symbols. We have a filter to ignore other symbols that we're not interested in. So it's a fairly, as I mentioned, it's a relatively arbitrary process. It builds a sorted list containing the addresses of name and entry point information and builds that .s file. And then you rebuild NuttX with that symbol table the first time. So the first time you have it, you need a dummy module so that the build completes without error. Then you run the script and repeat, and this time the global symbol table has all that information that you're after. Is there a better way? Yes. A more elegant way? Yes. A more general purpose way? Certainly. But again, for the purposes of this project and being expedient, this global symbol table proved to be the easiest way to accomplish our task. So some final words, and you'll see this is a relatively quick presentation because the concepts and are relatively straightforward, though the code may not be. As you can see, there's about 2,500 lines of diffs created from the base NuttX that we were using. It consisted of one new module and 19 changed modules. And you saw that through that list of other things under the covers there, what particular changes we hit. Again, what we're looking for in the future is to generalize it so we can support dependencies on other shared objects. So if we have a nesting of shared objects that require other shared objects, we'll be able to handle it. We want to generalize it to other relocation types that may rear their ugly head. We also want to look and make sure that it works in all the modes of operation of NuttX. At the moment, we run it in the mode that we build our particular runtime in. So does it run in flat mode? Does it work in X mode, etc.? We've purely concentrated on the way we do things in our particular environment. So we need to revisit ultimately and verify that conformance with coding standards, revisit and verify that it works in all the different modes of operation, that it doesn't break other architectures, that it doesn't cause all sorts of other grief for people. So hence why it's not available as a pull request. Ultimately, we'd like to be able to make it available to do so, whether we do it ourselves or just say, here's the code, would you like to work on this as a base, etc. That's the what we're looking for in the future. Again, if you're interested in the way that Meadow and that works, see if you can dig up Mark's presentation from yesterday from the video. I think it starts at the 7-hour 43 mark in the video. I went and revisited today because I think he spoke about 3 a.m. Australian time. And sorry, Mark, as much as I enjoy working with you, I wasn't particularly enamored about staying up that late. So with that, I will hand it back to the organisers and unshare my screen and prepare myself for the oncoming onslaught of questions there. So to the organisers, it's back to you.
Thank you, Neil. I'm sorry for mispronouncing your name.
You're totally forgiven. We have so many nationalities and so many options to choose from when pronouncing things that I have no issue with the way my name is pronounced, given the way I tend to spell it compared to the most people who spell the word Neil in this world.
Maju, can you help us with the questions from YouTube?
Yeah, I'm seeing here the questions.
Okay, thank you. Thank you, Neil, for the wonderful presentation. And now let's see if we get some questions.
For now, we have no questions. It was a great presentation. Thank you.
You're more than welcome.
Alan, you want to say something?
Hello, Maju. Neil, thank you very much for this presentation. By the way, guys, are you listening me?
Yep.
Yes.
Okay. Great. Thank you very much for this presentation. It's really good. I think everybody enjoy it. And just before I follow up, please, I ask everybody to turn on the camera. Let's take a picture of this moment for posterity. Hello, guys. Pedro, Thiago, Marty, Lupi, Xiang, Koizumi-san, and
Let's see, we still miss Koizumi-san.
okay.
I do like Petro watching this out in the outdoors. That's a good way to watch things. If only there was a table and a beer in front of him, it'd be perfect.
Yeah. Yeah, that's true. Okay, guys, I take a picture of everybody, so we'll post it later. And yes, the first question that we got there. Sorry, Maju, to pass you. Just it's not a question, but direct a technical question, but is a question from Xiang that is here with us. He was asking if the Wilderness Labs are planning to give it to NuttX, and he asked the Brian. I don't know how to pronounce his name correctly, but he was here with us last year, Brian Kostanic. He offered this dynamic loader to the community, but from our side, we need to adapt it. We need to make it more Linux-like, NuttX-like. Sorry, and so we need to work on that to put it on mainline. But
yeah, exactly. As I said, it's certainly not general purpose. I think it's a good base for being so, and yeah. I've got no problems. I'll talk to Brian, and as I said, we can publish the diff somewhere, and people can take a look and try and apply it. As I mentioned, it applies to a back level of NuttX, so it needs to be brought forward, and then the people who understand these things better than I can make it that more general purpose for things. And given what Matsuyuki-san talked about earlier with his shared objects and that type of thing, it seems to be something that may be of useful more than just to us.
Yeah. Okay, so I think Maju already put the next question on the screen. It's from Felipe Koval. Just a remark. Did you heard about the Azure executive who suggests that C++ will become obsolete and promoted Rust in place?
Well, given that it's getting introduced to the Linux kernel, it's certainly Rust is going to be there, but given the amount of C and C++ code in the world, declaring something obsolete this early is a bit adventurous, to say the least.
Yeah.
And we're running our applications are C# anyway, so...
yeah. And I think someone declared COBOL obsolete 30 years ago.
Yep, and I'm still making money out of COBOL. Thank you very much.
Yeah. So
if you didn't tell, that's about my vintage. I first started around 1981 with things, so I'm one of the older members of this fraternity.
Yeah. So I think C and C++ will be there for a long time yet, but eventually, of course, they will not be the most used language. But yes, I think for C is even a long way to be here with us, because almost everything is done in C. As you know, there is a meme when God created the world, they use the C language. So we'll see.
There's a lot of truth in that one. I don't see anybody rewriting the entire kernel in Rust anytime soon.
Yeah. Okay, Maju, I think we don't have other questions there, correct?
No, it looks like we can continue with the next presentation.
Okay, so Neil, thank you very much for this great presentation, and we are looking forward to get this dynamic loader on NuttX because it will bring even more flexibility and more powerful to NuttX. Thank you very much for help us and for this great presentation.
Thank you for inviting me.
You're welcome. Bye bye. But stay here, of course, if you can still with us.
I got another. It's not midnight yet, so we're good. I don't tend to pump it just yet.
I forgot to comment. You are in Australia, so this is why we put Japan, Australia people in the first presentation, right, Ali?
Yeah, so that they can.
And I appreciate that.
Thank you. So that they can be with us as much as they can. Also, a big shout for Ken Petit. He woke up really early, and he's here with us to help us with the audio framework and the next presentation from Koizumi-san. Also from Sony, he will talk about suggestion about the NuttX audio framework. Koizumi-san, can you please turn on your camera?
Okay.
Microphone.
Camera is now bringing up. Can you hear me? Okay.
Yes.
We can barely hear you.
Yes, that's some kind of noise.
Thank you. And I will share my screen. Okay, so hello. Today I'd like to talk about audio framework.
There is a bad noise on your background, a bad background noise.
Yeah.
And seem like it is generate some feedback and increasing over the time.
Okay, so yep. So I know I'm writing this as a best practice, and I hope that we can have a discussion here for expanding the functionality of audio. And before that, let me introduce myself. I'm working for Sony as a digital engineer, the digital ASIC designer, and embedded software engineer. And production involved is some LSIs and PlayStation 2 and 3, and digital camera like a Sony Alpha 7 and Sony TV, Bravia. And now I'm working for Expressions. And Expressions provides SDK and uses NuttX as its operating system. We also use not only the kernel side, but also the app side too. And what we already contributed on the Expressions work, we ported the NuttX on the Expressions several years ago, and fixing some bugs during the current
Netx. And audio driver before to interface like and example code. And on personal work, from this year, I could do this, and I contributed the 3 functions like music micro language parser and frequency modulate synthesizer and simple audio utility library. And next contribution we are planning is about audio framework. The SpreadSense has an audio capability. The SpreadSense SDK already included an audio implementation to take advantage of SpreadSense's audio, but the current SpreadSense audio framework is specific to SpreadSense, of course, and it's very complex and heavy because we have been used code from the past production and modifying and patching implementation. So we are now considering re-architecting about audio. So since we are re-architecting, we would like to define general purpose audio functions on Netx and be able to take advantage of the SpreadSense functions within the defined interface. So in today's presentation, I'd like to introduce the audio framework basic structure that we are currently considering. And I hope to share our idea and discuss with community members. So, and basically, there are 2 major functions are expected to be performed as audio. One will be the playback function, and the other is the recording capturing function. The both playback and recording will be read from or saved to the specific file format, like WAV or MP3 or etc. And however, a number of parameters must be set to take advantage of these functions, like channel number, bit width, bit rate, compression. This is needed for compression format, and sampling rate, input-output devices choosing. And of course, these parameters will already be configurable in NuttX audio driver. But there are not only features required by audio. These are cases where you may want to use the audio signal processing, or more recently, the recognition is very famous. So the example of the signal processing is like equalizer or gain control or dynamic range control, mixer, filter, etc. And audio recognition, very famous function is voice activity detection. And recently, voice recognition can be done in the microcontroller board by using the TensorFlow, Light Micro, as you know, and music classification, for example. Yeah, this kind of the feature is, I think, required on the audio functionality. Of course, it depends on the application, but so to achieve some how to use this functionality, that this is just a kind of the example of the signal flow. So the playing the music, playback music, so music data from the storage and decoder to decode to make the LPCM and equalizer, for example, and some operating tone is mixing and gain control and output. And audio input case is input the audio and filtering and encode to the kind of the compressed format and file access to save the storage. And in parallel, for example, voice recognizer here, and the application do some action depending on the recognizing. So the question is how to implement these functions and how to unify them as a NuttX platform, as the hardware has different functions depending on the devices. Now there are three major implementation methods, we think. And one is implement all on the audio driver. So the advantage of this method is that only one file descriptor is needed, but it tends to complicate the application audio driver, and signal flow cannot be freely configured. Of course, it's possible, but to make it very complex. And if we take this way, the number of I/O control is explosive. So I think this is not a good idea. So the second way is to create each function block independently and implement it in application layer. So this method allows free configuration of signal flow. Also, by using loadable application can be built with minimum amount of memory required for each use cases. In addition, the one file descriptor is consumed only. However, in this case, if the hardware has the specific functions, how to generalize it is more difficult, because this one is block size implemented directly, so there is no hardware things here, because it's a software implementation only based on basically. So the third method is to define device interfaces for each function block, and then this method allows free configuration of signal flow, optimal memory usage by module loading. The int mode we can use on NuttX already. and simplicity of each function, of course, but also allow the driver to be configured as a lower upper structure to absorb differences between the platform. The weakness of this method is it consumes a lot of file descriptors resources. However, some functions such as recently method merged FM synthesizer do not require a driver, so the best solution is hybrid use of the second and the third. This one and the second last one. Yeah, and it's as a side note that when configuring the signal flow in parallel, the life cycle of the memory used may be different for each block. So memory release management with reference counter is necessary. And the NuttX audio data structure already defined a reference counter and a semaphore for exclusion, but not used right now. So for achieving this kind of the structure, this kind of the signal flow, they will be actively be used in such cases. And it will be useful to have some kind of the utility library for this use. I'm planning to include some useful functionality in audio util libraries. Yeah, that's the conclusion. To make the signal flow configurable or separate each functions in each drivers in the application of the library, hybrid method 2 and 3. And it is also useful to add the functions for it to the audio utility library. Yeah, that's all. Thank you for your attention.
Thank you, Koizumi-san, for your presentation. And what do you think, since you are the one that designed the initial audio support? Can you share some thoughts?
Oh, sorry. Actually, right now, from this year, I lost my hearing, and I got surgery implant devices on my head right now, but to recover the hearing, but not how to say, good hearing yet. So please more louder and slowly, please.
Ken, you are muted.
Sorry.
Ken, you are muted.
Okay. Yeah, I actually had earphones on, so I can't really hear the volume of my. Is this better?
Yes, it is better.
Okay.
Thank you.
So I switched to just my normal speakers. I actually did the audio system, 9 years ago? I think I was looking, it was 2013. It's been a while since I've looked at it. And I definitely see the concern where, you've got a lot of stuff going on down in the driver level and, trying to configure the chain of events, right? You want to be able to have different modules, one, like the equalizer, if you go back to your slide where you're chaining those together, right? Where you've got an equalizer and a mixer and a gain control, etc. I can see where if you have a single audio driver, you're right, that means that there's a lot of I/O controls with a lot of setup for just a single driver. I like your idea of having a driver from one where you have the ability to change.
No, just put it up there because I finished it falling off the end of the bed.
Yeah, if you can go back.
Please mute yourself. Let me see if I can.
Yeah, if we can go back to that one.
Let me help.
Yes.
Okay.
I mean, I see the idea where it's using a number of file descriptors, which is 1, 2, 3, 4, 5, 6 in this case, which, is not extravagant. But I can see where if you have, as your audio gets more complex, that starts to grow more and more. I don't necessarily see an issue with having this number of devices, but I believe you would want a way when you're chaining these together at the driver level. If each of these are a driver, where you would want to have to go through the user mode back into the top and back into the application and send actual audio data through that chain. Seems like what we'd want to do, or what we want to do, is we have a way in each of the drivers to be able to have the kernel set up an audio chain, right, where you do have a driver and we have some standard interface for data coming into the module and then its output. Those would be chained together at the kernel level, but directed, have that chain set up by the application. Let's let each one of the drivers of the application tell the driver, your input needs to come from this other kernel mode driver, right? That way, the application is configuring each of those, but the actual flow for audio data doesn't have to make jumps to and from your application, right? And I don't know if that's what you had in mind when you were doing this diagram.
Couldn't catch it.
Did I speak too fast?
Koizumi-san,
Yes.
did you?
So I guess the question is, with your idea for this diagram, when you have these multiple drivers, were you thinking to have the actual audio stream, flow through that driver interface, that file descriptor, and have the actual audio flow through the application? Or was the idea that you could set up a flow between the kernel drivers where they can send data directly to each other? Otherwise, you're going to start getting a lot of added latency and a lot of added delay. What was kind of your thought there?
Oh, so you mean that, for example, the hardware supporting the how to say the equality already inside of the device. So such things. What your question is? The path through via the application is not good. You mean?
Oh, okay, so you're saying that the hardware already has the connections to be able to send the equalizer to the mixer to the gain control, and you're thinking just have a different driver for each function within the hardware. Is that my understanding correct?
Sorry. I
okay.
expected to close caption on the YouTube, but now this channel doesn't.
Oh, so
Yeah.
I'll say it slow. So you're saying the hardware already has an equalizer and a mixer that gain control, and the hardware automatically takes the data from the equalizer into the mixer and into the gain. In other words, that those aren't individual blocks. You have to somehow pass data from one to the other. The hardware already passes that data. Is that correct?
Guys, just let me interrupt you a little bit. I think, Koyasumi, your background noise is not helping Ken to ask. I suggest we turn off your microphone while Ken do the question. Then you will understand it better, and then you reply. I think now it will be better, correct? Ali, the sound now is clear, correct?
Yes, the sound is clear.
Yes, I think that's the point. The noise is not helping. So
Mixer, the gain control, etc. And you're showing, connections through the application. And so my question is, the hardware that you're looking at, or does the hardware automatically pass the actual audio data from one block to the next? Or is that something that the application has to direct that flow of audio? In other words, do I get a buffer from the equalizer? The application then has to pass that to the operating tone, has to pass that to the mixer. Or are these file descriptors used only for configuration? In other words, are they configuration or configuration plus data flow?
Yeah, I can guess what your point, and maybe the about the for example the some media driver also supported like the bypass mode, if the equalizer and the audio output connected directly in hardware side, and there is no way to getting the result after the just equalizer. So the bypass mode is needed, and some capability maybe can get from the device, and but the equalizer itself should be done on the equalizer device file. That is because equalizer functionality is just equalizing. So some parameters for the equalizer can be injected from the device file. It is the kind of the answer of your question. Sorry.
Yeah, my earphones kind of kicked in a little bit there at the same time. So yeah, I believe it does. So is it? So I guess the question would be your idea there is even if we have the hardware supporting the data flow through multiple things, your idea is to still have different device drivers for each function
different
within the same piece of hardware versus like I know right now the way the audio interface is defined, there's a an I/O control structure, and there's a structure that you pass down that supports different features, and those features are bit fields and different fields within a common driver. And I think what you're suggesting is maybe that you could split that driver into independent ones and reduce some of the traffic between the application and those drivers. I mean, you would still need to be able to send control down to each one of these. But I think your idea here is that you're minimizing that amount of traffic, or at least the complexity of the traffic. Is that your idea?
Yeah. So we actually, I can understand, fully understand what's being told. Yeah. So,
yeah, I think it's an audio, maybe the background noise again.
Just tango.
Maybe mute again so we don't have the background noise, and I can try saying it again.
Yeah. Quickly, Thiago has a question here, or some comment. I will ask you also to turn off the microphone to let Thiago ask or comment. Okay? Could you please turn?
Yeah.
Thank you. Thiago?
Hi, everyone. Are you listening? Okay. The current implementation works in a days chained way. So the application calls the audio driver, that calls the decoder, that calls the lower half audio codec and I2S, for example. According to this new suggestion, there would be different device drivers that could call the hardware itself, because some audio codecs already has built-in equalizer, volume control, gain control, balance, and bass and treble controls. But some of them doesn't have it. So we can handle that in software. If I understood the suggestion, is that these multiple device drivers could handle these better, these hardware capabilities, and if it's empty, it's not available, we can handle that with a software device driver or something like that. Is that true, Kayoshi?
Mm-hmm. Yeah. So, okay. If the hardware supporting some decoders, equalizers, and the several so low is maybe the monostic in that, and this upper level just define the separate interfaces. Okay. So the how to say driver and if there are some separated functions, not only specific for the audio function, like kind of just the DSP example. It can be used as a equalizer or the mixer or something else. And so in that case, it's not how to say the monosync audio devices and device block, hardware block. So it can be separate. So that case so can be cured on. Yeah. So sorry, I'm not sure that this is answer of the question, but this is maybe guessing also.
Okay. Maybe Masayuki can help us. Maybe he works with you and he understands a little bit how it works, and maybe he can help us. Masayuki, do you can help us in this discussion, or you suggest we discuss it later in the mailing list? What do you suggest in this case? First of all, do you understand the KMPT questions to Kodayumi-san? And can you help us to get a better understanding of these questions, of the what is proposing here for this modification?
Hi, Alan. I suggest Koizumi-san should send a new issues or new proposal to GitHub. So for updating audio implementation, and I think in my understanding, there is many configurations for audio. So which, for example, so some audio device has hardware equalizer or hardware decoder, and in some cases there is no such hardware accelerated. So there is so many configurations, and also there is some how to say we need to consider power consumption as well, and maybe need to understand some kind of limitations. So anyway, we need to push send this kind of proposal to GitHub or mailing list first, and then discuss in the community later. So including Ken and other who want to discuss with this kind of audio discussion. Yeah.
I personally think that the mailing list will be a better place than GitHub.
Mm-hmm. Okay.
Yeah, I agree with Ali. Okay, Thiago also want to do some comments. Okay, Thiago.
Let me know if you can talk more about this subject. But I have made some questions from YouTube, and I think Petro also did some questions. We could see those questions in there. If you want, I can say there, here, or
yeah.
I don't know.
Maju, please put the Thiago question again in the YouTube, and then.
Okay, 1 minute.
Okay, thank you.
Thank you.
Right. So the audio structure allocates the audio buffer and take care of it. How would you handle hardware-specific limitation like block alignment, for instance? Did you understand the question?
Let me complete the question. I would say that the proposed approach of Takayoshi, that is implemented different device drivers, would be better handle these questions, because with different height drivers, we could handle differently the auto buffer and cares for block alignments and something like that better in a different approach. Don't know, my guess.
Yeah, I don't see anything in the audio driver that would preclude having different drivers for each of these. Even if it's an audio chain that does this in hardware, I don't see any necessarily drawback or limitation of doing this. I think one of the main things to consider is if you are trying to do things where you're implementing an equalizer in your application and the hardware doesn't support it, and you want to get access to that data stream, I think the solution we come up with should have the ability to understand, is this a hardware chain that's where the data's flowing, or do we need to have the ability to have those audio buffers passed back to the application to do some software task and then down to the next driver, right? So I think that's the main thing I was getting at. Is I like this mode. I mean, it's not a massive number of drivers that you have to write, and I think the existing architecture will support this with some extensions, of course. But the main thing is to understand not just the control path, but also the data flow path, and when do buffers automatically go from hardware to the next block, or when do they need to pass back through the file descriptor or back to the application level for additional software processing. That's the main thing I was getting at, which that's something we could certainly discuss through the mailing list.
So one question. I got some words from you right now. So the audio driver uses this like the first idea. I mean, the thing is the and basically usually the audio signal is fixed in the hardware, so the audio is the functionality control is whatever is good enough.
I didn't catch the last part of that. Usually the audio, so the audio normally is done in the hardware. And I didn't catch the last part of that.
Koizumi-san, please write in the YouTube chat because your connection is a little bit with issues. We cannot listen you correctly. Okay. It is cutting.
Of course, thank you. Yeah, sorry for using many times. Okay, thank you very much.
Just write it in the YouTube chat, and we will ask it to Ken. Do you have the YouTube link? Just enter in the YouTube channel or in NuttX.event. We have the link to this YouTube transmission, and you can put the message in the chat because, or if you want to try to speak again, I don't know what you think, Ali. What's the best?
I think that it is quite hard to continue the conversation because there is a lot of noise. And the answers and the questions are, at least I feel them like they are a little bit of things. So there is some misunderstanding. If we move all this on a mailing list and it will be in a written form, it will be easier. Also, Koizumi-san mentioned that he had a surgery to recover his hearing. So he cannot hear. That is, or he cannot hear perfectly. So it's better if we all move to the written part, written conversation. I would propose that we actually hijack now the whole plan, and we invite Tiago to present his part, which is also audio related, and then we move further with the schedule.
Right.
We cannot hear you.
We cannot hear you. You are saying something, but we cannot hear you. Even when the microphone was unmuted, we could not hear you.
Now you're also muted.
Yeah, Ken, you are muted. Yeah, try again.
Do that again?
Now we can hear you.
Listen.
Okay. I was playing with my earphones and it switched over again. I said there was also a question from Petro how to integrate the automatic echo cancellation into the audio pipeline. I guess that would depend on how it's implemented, whether that's a hardware function or that's a software function, right? And I think this kind of gets back to that same discussion. If it's a hardware function, then that's a specific driver and a specific function that we would have to add into the audio capabilities. The structures there have bit fields to define the different capabilities for your particular audio hardware, your particular driver, right? So it would be an extension to that if it's a hardware function, or even if it's a software function, right? And so then it would have to be an extension, based on that. If it's being done in software, which I wouldn't think you could do echo cancellation in software, it would just be an extension to the driver for that. And so it would be very specific to the hardware implementation for that echo cancellation. But I think, as part of the discussion on the list, that's something we could certainly discuss of how to add that and what, in terms of the control and the data flow, right? How do you integrate that into that audio subsystem?
What do you think if we look at how things are implemented in ALSA and we create our own subset? Because we cannot have support for the full ALSA. At least I looked at that. But I'm fairly sure that we can inherit some things from there which have been proven as working.
Yeah, I think that's a good idea. In fact, last night after you asked me to join this, I kind of looked at the ALSA driver, the architecture a little bit. I know when I did the NuttX audio, I couldn't just pull in ALSA, right? And so what I ended up doing was looking at the USB audio drivers and the headers, and I kind of mimic things after USB audio. And that's kind of where the NuttX audio stuff came from, a lot of the headers and a lot of the stuff that I added there. Now, when I added all that, I defined all kinds of structures, and mainly I was using an MP3 decoder at the time when I decided to add it. Right, I didn't have equalization. So most of the stuff that has feature support there, I didn't. I just added it because I realized this is stuff that we might need at some point. Some of that has been filled in. So yeah, I agree with you that looking at different architectures and that you can't just copy those in, of course, that's Linux code. But we could borrow ideas from that to say, how do they do it? Is there a better way for us to do this in the NuttX audio? Yeah, absolutely.
That's something that I'm interested to, because I've made a question on YouTube chat about some auto server service for the NuttX, like something like Pulse Auto or Jake or something like that. And that's related also. So that's something that I would like to see on NuttX soon.
I personally think that we should have something that scales, and ALSA has been proven to scale fairly nice, because at least my personal opinion is that we will see more and more microcontrollers with audio capabilities in the next years. And we should be able to have this as a proposition. If you want the bleeding edge SoCs, microcontrollers, then take NuttX. It works out of the box. It has many features, and you can develop your product as a business proposition. Because in this moment, the implementations that we have are kind of splitted. Presence uses its own audio. Me and my colleagues did some work to get some features working with Presence directly on NuttX, but it cannot match the in-house solution, let's say. And that will probably happen with many other boards, and it's a pity. We should have something that works the same, checks for capabilities, and then it just works.
Sorry, I'll jump in. Sometimes, like, the hardware capabilities may be not enough, and we need a way to switch some hardware capability, for example, the equalizer off, and re-implement it with the software if we think that it will give us a better quality. And the same for the other parts of the audio pipeline. So in general, it's like what I see from this presentation, it's like a set of devices, set of drivers that like pass the data output from one block to the input for the another block, and each of those blocks can be replaced as I expect, but maybe it is not.
I would expect those blocks to be software or hardware modules that can be detected at runtime or plugged in. So something that that works
driver output, and the application need to redirect that to the input of another block. That is like increasing number of system calls, especially in some kernel mode. So that differs a lot from performance perspective.
Sure, that will add a lot of latency and increase the power consumption. So that's why I think that we should look at how ALSA did the things, and then try to define something that we all agree with and start working towards that goal.
Yes, I like that idea.
Okay, then I propose that we move to the mailing list so that everybody can share its idea. Maybe somebody has a better idea.
Yeah. Just a comment. We still have just one question there for our here, Guidelin. Guiding
I'm sorry, I didn't see the question since I cannot see YouTube.
Yeah, Maju, could you please put it in the screen in the YouTube? He's asking, how about? Thank you. How about format negotiation? Can be dynamic? Format negotiation.
The current audio system does have the ability to query the driver on the formats that it supports. Yeah, so when I first created it, I did add that capability. So already the application can query, as it opens the audio device, it can query, hey, what are your capabilities? And one of those queries is the format support. So yeah, it could be dynamic. Now, it might be that during our discussion on the mailing list, we decide to extend or change that, enhance it. But yes, it certainly can be dynamic.
Okay, perfect. Thank you, Ken.
Also, Ken, we did the port for the bitrate converter. So now the NuttX audio is able to do bitrate conversion. At least it's tested on Sprezzo. So that is also something that we should probably think about when we implement the framework. Because if you query the capabilities and you're not matching in hardware what the software requires, you can automatically include the bitrate.
Yeah, that's a good feature.
The same for the format itself. We can try to software decode the format.
I think that is a little too CPU intensive, at least for some formats.
Yes, it can be.
Guys, it was really nice to see so many discussions and so many great ideas. As we mentioned, let's continue on the mailing list. And now I think that it is time for Tiago to hijack our presentation list and show us something audio related.
Okay, let me share my screen. Sorry. You can talk, Takayoshi.
Hello, yeah? You mean the my screen?
No. Tiago will have the next presentation.
Next one. Okay. Yeah. Thank you, everyone. Thank you for your comment and questions. And just one thing. Let me say one thing. So now yeah. Let's keep continue the discussion. And the purpose of this proposal is to see if we can generalize the functionality of the audio, which is tremendous variety. We know, the audio is very unique for each devices. So it is easy to implement its specific driver, but it's not the general. And NuttX is kind of the general thing. So this is a trial. So let's try. Let's keep discussion. Thank you very much.
Thank you, Koizumi-san, for being today with us.
Thank you. Let me share my screen. Let me know if you are seeing me and the slides.
Yes, we can see you and the slides.
Okay. I will show you a short demonstration about the I2S support on ESP32 by doing a demonstration of an audio streaming. Okay. I will make it very short, so you are free to interrupt me and write some questions or something like that. Just one moment. You are seeing me? No, I think there's some problem regarding the OBS. Just a moment. Okay, now it's right. Just a quick presentation of myself. I'm a specifier. I work with Alan on the third-party software platform Teams, specifically with NuttX. And previously, I've been working with ISP-IDF, that is the official framework for specific SOCs and development boards, for almost 5 years. And also, I've been working with embedded Linux too, mainly with OpenWRT-based boards. So these both experience, RTOS plus embedded Linux, proudly led me to NuttX. And now I'm working on SquareS support for ESP32 family on NuttX. Okay. That's quite interesting because one of my personal interests is about audio. I started studying electronics and after that electrical engineering and embedded programming because I have made my own audio system in a DIY manner. So it's very interesting to be working with the audio applications and everything related with that. So I'm very excited about that. The main guidelines I've been working on is to provide faster delivery time about this feature of the ESP32. So I've used an already supported audio codec for this demonstration. I will talk about that later soon. I've been working with the DMA capability of the I2S peripheral on ESP32. And that's why I have raised that question about the audio buffers, because on ESP-IDF, the framework takes care of the buffer. So there is no problem while users are send data to the device. But that's not true for NuttX, because the higher level interface, the audio codec and the PCM decode driver, for instance, take care of the buffer. So it would be not memory efficient if I had to duplicate those buffers into the I2S device driver. So I've been working with the DMA enabled buffer and have made some interventions to assure that there would be no glitches during audio playback. And of course, I'm talking about ESP32 that is known for its Wi-Fi capabilities. So it would make no sense if I didn't use this for the this demonstration. So I will be showing you an example using HTTP streaming of the auto file. So that is the proposed lines of this demonstration. As I've said, this demonstration and this I2S auto driver is still under development, so work is in progress. Hopefully, I expect it to submit the patch to the NuttX mainline in the next few weeks. But as the NuttX conference approaches, I would like to show you what is being done about that. And the materials I've been using is a ESP32 DevKit C development board, which is one of the most common development boards. Also, I've been using a ESP prog board, which provides us a JTAG interface. The autocodec I've been using is the Cirrus Logico CS4344, which is already supported by NuttX. And of course, I have to use some logic analyzer to make sure everything's alright on the I2S bus and pins. And talking a bit about the specifications used by this demonstration, I can handle up to 16 per sample on the auto sample. In fact, there is a NuttX limitation about the auto codec about that. Of course, I would like to remove that limitation, but today I will show you an example using 16 bits per sample. And I was able to play files up to 48K kilohertz. Again, that's something that I would like to improve. I would like to achieve 192 kilohertz. That is high-end audio format. And also, as I've said about the DMA enabled buffer, I'm pre-buffering those auto buffers into the DMA capable I2S buffers, because of course I'm streaming data over the Wi-Fi connection, so I would need to do that to have no glitches and no interruptions during the playback itself. I will show the demonstration. Maybe some questions raised during this demonstration, so I will not show you more slides. Let's go to the demonstration itself. Let me share my setup. Are you seeing me from another angle?
Yes, okay.
Okay. Okay. So, hi everyone. As I've shown you, this is the setup I've been working on. That's a DevKit C board, development board, which contains a ESP32, which is attached to my computer through the USB cables. I'm using a CS4344 autocodec on this board that is attached to the I2S pins. Also have a Wi-Fi router here, the loudspeakers, ESP prog board with the JTAG interface that I'm using to debug the codes, and a logic analyzer attached to the system to make sure everything's all right. The idea is to show you a live demonstration with no tricks. I hope everything works as expected because it's on live, but let me try to show you about that. I will be streaming 16 bits per sample auto file, sampled at 44.1 kilohertz, so CD quality, into the Wi-Fi network. It's an uncompressed file. This codec does not support any format other standard PCM uncompressed file. So let me show you my terminal. Okay, I will reset the board and make everything from the scratch. So I will connect it into my Wi-Fi network. So interface up wireless LAN 0, wireless API Yes key. Wireless LAN 0. A very difficult password for my Wi-Fi network. Wireless API ASSAG. Wireless 0. Test network. Oh. SSAG. Wireless 0. Testing network. Okay. Renew wireless LAN 0. I will ping my router to make sure everything's all right with the Wi-Fi connection. Okay. Everything seems to be all right. I will connect the P2 plug into my loudspeakers. I have muted it so we will not hear any pops or something like that. So again, on the terminal, I will enter NX player. Previously, I've set up a simple HTTP server with a Python server on my personal computer. So I will play a file in there and hope everything's go well. I will turn up the volume. As you can see, the information on NSH terminal, I have 16 bits per sample, sample weight of 44.1 kilohertz, 2 channels on an uncompressed file, which is quite impressive for a device that costs under $10 US, and it's being streamed over the Wi-Fi. I think you are hearing my loudspeakers. Let me mute it. So the idea is to make this short presentation. During this development, it's been very challenging about the specifications of the ESP32 and the auto drivers related to that. And of course, that raised a lot of questions regarding the auto subsystem of NuttX. And I hope this I2 support raise another questions, improve the auto subsystem of the community. And I hope people could enjoy ESP32 with auto applications. That is the demonstration itself. I will not take more time from you. So I put my mail in there. Just one second. If you have any questions, I would be pleased to answer you. Let me mute the audio here.
Thank you, Thiago.
Very nice, Thiago. Thank you. It was really nice to see NuttX and ESP32 finally playing audio. So now it's opening new possibilities to ESP32 and NuttX. So people can now use it to play music.
Yes, yes. I'm very impressed about that because the cost of the device itself, and I've been playing around with HTPCs to stream audio to my audio system, something like that. And I'm expecting that I could replace Linux, embedded Linux devices from these ESP32 based boards. Some families of the ESP32 has built-in USB support, so we could make external audio boards and something like that to stream audio over Wi-Fi, over Bluetooth, and over USB, and attach that to a audio system. Well.
Yeah. Now you can start a new company to compete with others.
No, that's not my personal interest. I would like to make it for me, but that's the general idea I would like to share.
Yeah, actually, it's a good idea to create some kind of audio server, or that you just put for example, as you said there, we can use USB, like a USB thumb drive or something like that with music, and you can string it to your phone or other speakers in your house. It's very nice and very clever idea to use it. Thank you very much. I have a question. Did you is planning to submit to this driver to mainline?
Yes. As I've said, I expect to submit the patches in the next few weeks. So this would be available first to the ESP32, and after that, I plan to support the others device on ESP32 family. And of course, the next step is to provide the I2S input, so we can handle microphone signals and something like that. So I hope this will be available soon, but I would like to show you at the first moment before submitting, because I think it's interesting.
Yeah, it's very nice. Thank you very much for that. Now we have a next presentation. Now our friend Felipe Neves. He also is expressive or expressive, right, Felipe?
Yeah.
But your heart, yeah, but your heart is still expressive, I suppose.
Yeah. I'll never stop to do something with related with ESP32. So I maintain some personal projects regarding ESP32, and also still contribute for mainly for Zephyr OS. But I probably will start to do some work from Netx side. But today I will not talk about ESP32.
Yeah. Today is a different platform, and
yeah.
So if you are with everything set up and you want to start, so
let's go. I will share my screen,
and I will turn off my camera and microphone.
Just a moment. I just need to do. So, do you see my presentation?
Not yet.
No. We can only see your camera.
Yeah, only the camera for now.
And now?
Not yet. By the way, sometimes it's happened with Jitsi. I faced this issue yesterday, so I close up the session and open again, and it worked. So if it's not working, you can try to do that.
Let's try.
I think sometimes Jitsi mess with the
sharing
permissions, and maybe it thinks we are not we not allowing it to transmit, but we click it in the allow permission. I don't know why they do this way.
So still not sharing, right? I will try to rejoin.
Yeah. Also, maybe if you can try other browser also.
Yeah. I will try. I will try the Google Chrome and see if this works.
Yeah. Actually, I am using Firefox here, but if not working in Firefox, try the other one. It's like USB USB-A. When you try to plug your pen drive, you try it, not connect, you invert, you flip it, not connect, you flip again, oh, it's connected.
Yeah, let me. I will try to rejoin, guys. Just a moment.
Sure, no problem. So let's see the chat. Maju, are you around? We need now the form for this new presentation. If you can.
Yeah, I am waiting to start to send the.
Okay. If you want, because he's just organized thing, maybe we can. What do you think, Ali? Is better to wait, or we can put it in the chat already?
I think that we should put it. It saves some time.
Yeah, so maybe people can get have more time to.
Sure. No problem.
And feel free to choose a secret word as well. Yeah, now it's working. Okay, perfect.
So
yeah, just put in 16. Yeah.
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 Well, everything is working now. Seems to be working now.
Yes.
Okay. So first of all, thank you for the Netx community for the opportunity to present again to the Netx International Workshop. I will run on a short talk regarding how to offload and processing using the Sonus Presence and its ASMP framework and the Netx. Currently, heterogeneous computing and asymmetric multiprocessing is a subject that caught my attention the last months. As Alan said, I'm an ex-expressiver. I have been working there for last 3 years, and right now I'm moving to ARM, so where I deal with some sort of asymmetric multiprocessing stuff for microcontroller side, and I built some years ago on a Hackster context. Motor control based on this Sonus Presence board using the ASMP. So I would like to bring the work I did on the past year and show how to take advantage of Sonus Presence SDK and the ASMP, and of course the NuttX RTOS to help you to defer some have processing to other core, to the another free core that your CPU might have. Before we can get started and show some sort of coding, why we need to do some sort of offload processing? Typical case that come in my mind is to defer some sort of have mapping processing you will have on your software pipeline or your software control systems pipeline. For instance, let's think about sensor fusion algorithm and baked by a extended Kalman filtering. As most of you might know, the Kalman filtering does a lot of matrix operation, and the most have operation in this algorithm is the matrix multiplication. So we have a lot of these multiplications, and in some kinds of Kalman filtering implementations, you have a lot of sequence function call, consuming a lot of stack. And the typical flow you build for that is talking about the NuttX context. Is open a I2C or a sensor driver using NuttX device drivers, gather the EMU samples, and call your common filter implementation blah 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 function, and get the results and do some sort of processing. So render the object orientation, use it for in robotic scenario to calculate the robot's heading and things like that. So the common filter itself will consume a lot of processing from your main CPU or supervisor CPU, and this will add high latency to your pipeline. So when you have tight timing constraints, for example, action robot pipeline, we will have a fixed time step to occur. In most of the cases, it will be 1 to 5 milliseconds to receive the telemetry, receive the motor commands, perform the odometry calculations, and run the inverse kinematic server, and then run the motor control. So if we start to think, the only hardware-dependent part here is to gather the sensors and update the actuators. So all other calculations are platform independent. So you can do it on, for example, on a Raspberry computer. So you connect the motor controller to the Raspberry computer using the serial port. They have processing on the Raspberry, and receive the commands and update the motors. And if my microcontroller or my local processing unit enable for me some extra CPUs in order to avoid the computing step. So the idea is to defer all this having processing to these local cores and use all the bandwidth of this other local cores to do the multi-processing while your main application runs and do other stuff like communications, like timely running your processing pipeline. The common filter is one typical case, but there are other domains that the offload could be very desirable. For example, in the safety critical applications, we have a typical black box software where you must guarantee the states and the comments and all other information of that piece of software should not fall into an invalid state. So when you will pick that certified piece of software to your main application, you have two works to do: certify the piece of software itself and certify your main application in order to avoid that will push some invalid states for the critical application software. The offload in this case could be very beneficial because you can just extract the critical part of your software, move to another core you have free there, and do all the platform independent coding in a bare metal mechanism without any other piece of software with my difficult the certification, and leave your application to do the business rule. It will be will be developed for typical scenarios of this kind of offload processing is when we are talking about our trusted firmware. For example, we have the two applications, non-secure application which carries the operating systems and device drivers, and we have a secure application which runs with all the privileges of of that course and is responsible to do a very specific task. For example, a neural network would run in a secure domain with limited privilege of access in order to prevent hyperparameters modifications by malicious software. So I just would like some scenarios to perform offload processing. And talking about NuttX, what it currently offer for helping you to do some sort of offloading processing. Of course, the first thing you need to know when doing some sort of offloading processing on NuttX is your microcontroller has another free CPU to do that. So we are talking here about multi-core microcontrollers. Of course, nothing of what I would present today will apply to a single core microcontroller, but it could be applied to multi-core microcontroller like ESP32 or ESP32 S3 with both of them have two extensive CPUs, and the Sony's Presence have 6 ARM Cortex M4F CPUs. NuttX currently offers the symmetric multiprocessing, aka SMP. So we have a single NuttX image, and all the threads running on NuttX will be distributed across the 2 physical CPUs. How could you take advantage of SMP here? So one of the typical scenarios is to pin one of the CPUs or set the affinity of one CPU to the non-secure code and left the one CPU to run only that part of code. And one thread, which typically could be your critical part of software you might want to offload, you typically pin to the other CPUs. What's the one of the problems with that? It's you always need to link your applications, your critical and your non-critical applications in the same image. So you might not have the ability to develop them independently. So you cannot validate it independently or add features independently because you need to link everything in the single image, and the critical application will depend on the host application. The other alternative, which is very new for me on the NuttX side, is the OpenMP support. OpenMP is a project that offers some sort of primitives and protocols to perform asymmetric multiprocessing. So it typically offers to you the ELF file loader and shared memory and message queues primitives to send messages between 2 CPUs, and a standardized way of message formats in order to replicate the communication medium between the two CPUs. In this case, you get the ability to independently develop your critical application on your remote core, and in the host core, you typically other team will develop the code for the business rule and other things that's related to the non-secure domain. The main drawback of the OpenMP is the project itself. It's very complex, and this initial setup could take lots of time in order to get the things running, because it offers lots of primitives. So the initial question you might have is, what's the right protocol for me? So for microcontrollers, we typically go to remote the ARP message protocol, and run the ARP message on the both sides of the CPU, and by using the virtual the virtual rings and virtual queues, you defer some data to the another CPU, and use other receiving virtual queue to receive the computation result. The ASMP that Sonus Presence SDK offers could be treated like a very simplified way that OpenAMPs work. That will illustrate. But before of that, I think it's worth to talk about of the Sonus Presence microcontroller, which is based on the CXD 56 SoC, which carries six ARM Cortex M4 cores, each of one running at above of 100 megahertz. So this for a microcontroller, it's a lot of processing power. And when you build the SDK for the Sonus Presence, it will run only in the supervisor core, which is the core 0. All the other 5 cores, except if you are using the GPS or the audio subsystems, will be free to using. Other than that, things that caught my attention is the high amount of memory RAM on chip, with above 1 megabyte of, and 8 megabytes of flash memory, where you can put some sort of executable code and some sort of non-volatile storage like file systems, for example, and offer the typical things that we expect on the microcontroller. So a GPU, a GPIO controller, SPI, I2C, and for the specific case that I brought to you is the PWM. Oh yeah, we will talk about. So here we have a simplified block driver extracted from its datasheet. So looking at the application domain, where we'll see the 6 CPU, we will note something very interesting, different from the majority of asymmetric multi-core microcontrollers that typically carries a M0 or a M4 processing. All the CPUs on the Sonus Presence has the same privilege of access on the microcontroller bus. So it would be true to say that it's possible to build 6 different NuttX images and load one image to each CPU. It's possible, and all the images can access the subsystems of the microcontroller, like the peripherals and other more complex subsystems like the USB, SDIO, and audio subsystems and things like that. We typically call the CPU 0 supervisor CPU, and the other CPU we call worker CPUs. Because when this microcontroller starts, the only CPU alive is the supervisor CPU. All the other CPU, the software will be responsible to activate and load the firmware to those CPUs. One interesting thing to note is the Arduino SDK of the Sonus for the Arduino core for the Sonus Presence actually builds one NuttX image for each CPU. So when you open your Arduino sketch for this Presence board, you can develop independently 5 different sketches and link the final image into a single one and flash to the microcontroller, and the 6 CPUs will be running a NuttX image on its own. But talking to the only presence SDK, it's based on the NuttX RTOS. So all the upper half drive, it uses the upper half drivers infrastructure for NuttX, and and Sun provides the lower half drivers for the microcontroller to be plugged to the NuttX OS. But on top of the drivers, we will have some very interesting middlewares besides the sensor framework and power management and audio middleware, which have been mentioned on the previous presentation. We have the two interesting for your application, which is the memory utility and the ASMP framework, which is the point of interest of this presentation. The ASMP framework plus is responsible to perform the loading of the worker core or the offload core image to its memory, initialize it, and provide to the supervisor core some primitives to communicate with the worker core. And the memory utility is some kind of executable space partitioning. So you reserve some memory to the supervisor CPU, and before loading the L file to the worker CPU, you pick some chunk of memory for using the memory utility, reserve for that CPU, attach to it, and load the firmware. And some part of the memory utility, the ASMP framework use to construct some sort of shared memory space where you can, fast as you can, copy and read data to a memory which is shared to the work CPU. The ASMP framework also provides synchronizing mechanism and lock protection, mainly because of the shared mechanism. So you typically own the memory area, do your operation, your read, write, modify operation, then you release that memory area. The worker CPU will do the same thing. This is this is a simplified block diagram that we will see on the ASMP typical application. This was extracted from the documentations of the Presence SDK. So we have the main CPU and the kernel running NuttX, and we have in the middle the ASMP framework and the coprocessor, which is the worker core, typically running a bare metal application. And the ASMP framework is responsible to load the image and manage the state of that processing. The communication between the CPUs could be in a very POSIX way, because the ASMP framework offers offers the communication primitives very similar to the POSIX API calls. So when you need something more, when we want to transfer just a nut of bytes to the worker CPU, you can use the ASMP message queue, and all the synchronization will be done by this mechanism. And the last two is when you need to share high amount of data, for example, a chunk of message of 1 or 2 kilobytes, or let's say you would like to share the matrices of a common filter between the two CPUs, where the worker CPU just update the inputs of that matrix and grab the output state of that matrix, and the worker CPU just make a copy of the inner states of the common filter matrix that's represented on this shared memory area. So you might use the shared memory to perform the read or write, but before do any kind of operation to avoid corruption, you protect using mutex subsystem provided by the ASMP. So when the as I said previously, the supervisor CPU takes them, owns the mutex, and when it gets the mutex, do the operation of the shared memory, then release the mutex. The worker CPU also will do the same thing. If the mutex is not being held, it's probably because the worker CPU, the other CPU, is doing some sort of the operation. And once that CPU finishes its work, the next CPU could be owns that area. Some points, some drawbacks I figured out when developing with the ASMP of Presence SDK. It's a very bare metal application without the example offered on the SDK just simply does not provide a libc or a libmath, so which was very frustrating to at the first instance, because one of the things that we would like to is to do some sort of offloading. Since you have all the CPU available to your hands, it's very natural to avoid to build some sort of the optimized cosine and sine functions or arctangent functions. You typically might think, wow, I have the libmath functions available, so I will use them because I have a lot of CPU, and my CPU is responsible to do only that specific task. This is something I found a bit problematic which is the initial example, does not tell you how to load a more complete bare metal C application with support of libc and libmath. I will show you how I overcame that by looking on the more complex examples, because this caught my attention, because when I use it, the Arduino SDK, I had the complete NuttX on the microcontroller. So I started to think, if Son made it in somehow, so I'm not asking too much to have at least a complete bare metal application in C for my application. And other drawback I found of this Presence ASMP is the lack of support of libraries for the worker CPU. So libmath is a thing that I could bring because it's included on the C toolchain, but the worker CPU does not have any kind of access to the NuttX, and the ASMP does not offer a way to build a local NuttX image to its for usage on the worker core. So you need to pick the ASMP worker project and do everything by yourself. So you need to provide your makefile, provide the libraries you might to use, or you need to copy the register header files for the CXD SoC if you would like to run the PWM on the worker core. But besides of the drawback, I could bring to you one of my favorite use cases for asymmetric mode processing. It's field-oriented control of a BLDC motor, where I'm using the supervisor core to run NuttX read sensors and just to update the PWM. And I wrote a wrapper to have called the FOC accelerator, where I send data to the worker CPU and pick and grab the duty cycles for the PWM. And the worker CPU is responsible to pick the encoder position and the quadrature and direct voltages and perform all the FOC calculations, which includes to calculate the electrical angle, perform the inverse spark transformation, and do space vector modulation, saturate everything, and calculate the mod operation of the UVY frame, and normalize them, and provide them as PWM duty cycles. I forgot to put on this slideshow the math operations involved, but to giving you an idea on typical FOC computations that runs on the Cortex M3 in a fixed point or soft floating point. Operations involved are cosine and sine operations, and modules operation, square root, and things like that. But the FOC control loop should run in the real time. So in this case, I'm completely offloading the FOC to another CPU, and I can do in timely just the sensor capturing and the update control signals in order to have a strict timed loop to make the motor spin. So I think we are done to say. I would like to show you some code before we spin the things here. I will stop my screen and start again. So, folks, do you see my VS Code here?
Yeah, go ahead.
Yeah, the font size is okay to you?
Yeah, it's fine to me. Let's see in the internet. Yeah, it's okay. It's good.
It's good. Okay. So what I did an out of tree project. I need to update this. And here we have this Presence SDK. When you install it, you see something like that, composed by externals, the examples, firmware, and NuttX, and the SDK here. The best way I found to start a project with this SDK is to copy one of the projects on the examples and paste here and start to fill with the things I need for my specific project. So for ASMP projects, let me show the most simple project. You have two environments of development. You have the worker environment and the supervisor environment. The worker environment, for instance, could be a submodule where the worker responsible team develops separately its features and tasks with their own code and provide a submodule that you could just clone inside of your ASMP folder. And by just adjusting the make files, you can build everything together. So inside of the worker, you have your application folder with the worker related code, a proper make file, and your main application, which needs to do some extra steps. You need to provide when you build the worker image, it will be linked with the final NuttX image as an image file where you can access it by mounting as a disk driver. After you mount the disk driver on the ROM FS, you can load the firmware by passing its full path. And what's that full path? The full path is the output application you generate. And here when you go in the worker name, for example, here it's a hello application. So when loading your device, you pass the name of the executable, and just let do the ASMP to do its work. This is the example provided by the SDK, and now I will show you how it will do for some sort of more real application. Here I have the previous FOC firmware, and here I have the main application, and I provided some wrappers, and here where I can get the encoder and update the PWM. This one is very simple, very straightforward, not different for any NuttX developer. Just open the drivers for the I2C, for the PWMs. Since it's a BLDC modular, I need of 3 PWMs with shared time base. Just open it using the default paths. For the encoder, I have I2C encoder, so I just use the standard way of NuttX to hear the encoder by using the message concept and the IO CTL. And to set the PWMs, the same things applies to the NuttX PWM drivers. Just use the PWM info, set the frequency, set the duty cycles, set the characteristic, and finally set the IO control to start the PWM. There's nothing interesting to show here. But here, where is the FOC accelerator? This is the wrapper that the main application see. I will initiate the coprocessor and set the encoder offset, since it treats for this is absolute encoder. And here is the 2 main routines that I typically order a new duty cycle for the accelerator. So what I need to input: the encoder, the current encoder position, the directive voltage, and the quadrature voltage. These 2 DC voltages are the voltages used to command FOC, the FOC engine, and it's proportional to the speed desired for the motor. And the get outputs will provide me the duty cycles as soon the computation occurs. So what I typically do is some sort of asymmetric asynchronous processing. So I just call the input by passing the voltage desired and the position of the sensors, and get the current, and then update the PWM. Oh, okay, but it might work that I set the input, but I did not actually receive the duty cycles corresponding to that output, which is fine for motor control, because these 2 operations acts like a zero order hold. So as soon I need the data's change, while the data is not changing, the output should keep the last state. So this will just add the quantization error, not and will not introduce any other kind of distortion for the waveform for the motor. And here I just simulating a timed loop of 1 millisecond for the iteration. I can just remove that depending on how fast you would like to calculate your FOC, but this depends. Since I'm showing to you a voltage mode FOC, there's no closed loop PID controllers, and I prefer to keep the timing of the loop more under control. On the accelerator is the thing that I would like to show you. So you see the header file is just a wrapper to abstract the ASMP operations on the supervisor core side. So here I just mount the files, the disk image of the worker CPU. I gave the name of FOC accelerator, and by calling the multiprocessing task init with the firmware path, it will access the disk image, will load the CPU, and will start to execute the worker firmware. I also created a mutex and a shared memory, which I used to protect and exchange data between the worker CPU respectively. And the FOC shared memory has this format, which typically the data needed by the FOC engine. The aligning flag, the read to use is a flag used by the worker CPU to tell me okay, I'm ready to use it too, so you can start to send data to me. And things that you typically expect for FOC. So the pulse per revolution, the electrical angle in radians, the number of pole pairs of the motor, and the common voltage and the output PWM. So when I initialize everything, I will exec that the worker CPU, wait it to be ready, and it's done. The CPU initialized. The FOC algorithm has a motor-rotor aligning procedure, and it will, when the CPU is done of its startup, it will enter on aligning status. It will start to continuously calculate the FOC duty cycles for minus 90 degrees in order to provide an initial rotor position. And when it's done, I just read the encoder and provide that reading to the FOC. When I do that, the aligning flag will be cleared and the FOC accelerator will start to compute every encoder position I send with the direct and voltage quadrature. We just update the shared memory. We don't do any special operation and then unlock the mutex. And to capture the data, we just hold the mutex again, capture the duty cycles for the shared memory, also the electrical angle, which I was using for the purpose, and unlock the mutex. Just like occurs here in this loop. Look at the worker code, which the more I consider this the most interesting part of the code. It's a bare metal, but it has the access of the same ASMP API that the supervisor CPU has. So I added the CMath. I figured a way to add a math and the libgcc. How I did that? By using some things I found lost on the examples. By picking the ARC CPU, I was able to find the GCC and the libc and the libmath. And after getting these two, I just added to the final build step command the libraries of interest and the libgcc and the libc in order to have the access to the math functions. So in this side, I just represented the same structure that we have on the supervisor CPU and the same keys for access the mutex and the shared memory. On the accelerator, I will show you the main function, which is very like it's very like a bare metal application. So when the CPU starts on I just starts the mutex, the shared memory, grabs the location of the shared memory, and performs the rotor alignment. Once this is done, it will calculate the FOC, which is involved to first lock the memory area, make a copy of the shared memory state. Why to do that? To release the mutex as soon as possible in order to avoid the supervisor CPU to stall too much time while it waits for this one to complete. The idea is to reduce the latency most as possible. And it will calculate the electrical angle and do the inverse Spark transformation, which is located here, to map the direct and quadrature voltages to a rotating frame, 2D frame. And the last one is to perform the space vector modulation, which will compute the module of this frame in order to avoid the saturation distortion, and map it into a 3-phase vector and scale it for between 0 and 1. And after that, the worker will hold the mutex, compute the duty cycle, update the duty cycle and the electrical angle. So this data will be available for the supervisor CPU. And this will be done continuously. So there is no any other latency. This loop will be running every time. So the calculations will do as fast as possible. But while the calculation is not done, the shared memory will keep its last state to avoid distortion. So the worker, the supervisor, or other worker CPU could grab safely the output data from there and update the system to be controller. In this case, is the molar. So let's see this thing. Could you see my webcam here? Just the VS Code, right?
Yes. No camera yet.
Yeah. So, and okay, of course, when I configured, when I put this project inside of the examples, I just made a procedure of renaming the variables of the interest and added the source files that I needed to build. Added entry on the menu config in order to enable or disable this application, because it will take the same way that NuttX sees its application. On the NuttX apps, you typically drop your application folder there and create a menu config entry for that. And on the menu config, you can enable or disable that application. And you see that you can see the application on the NuttX shell and execute it from there. Just to show you, if I run tools. Yeah, it will. I hope someday NuttX will update the menu config to the newest form that Zephyr typically uses to avoid this problem with the menu config size. And here on the application configuration examples, not the NuttX, you'll find presence. This is the configuration of the SDK. And here we have the examples. And here is our FOC offloaded example. I could enable or disable it. In the same way, I can enable or disable the ASMP or other things properly. One thing that I noted, it's not enabled by default in the experience is that it's PWM regardless the configurations. So to enable that, I had to do the NuttX typical path, which is going to the system type, find the SOC options,
and go through the peripheral support and search for the PWM device. So it was enabled, but the outputs were not. So I just added it and mapped it to the shield, to the FOC power shield I have here. Once the application is configured, remember you have all the operation of the SDK will be done inside of the SDK folder, which is on the top left directory, DS1. Once the application is configured, you just build as you usually do for NuttX. Okay, so if this very fancy name, very fancy format of file is created, which is SPK, so everything going well. So I will flash my board using, let me do something. To flash the board, you will execute the tools flash shell -c using passing the port where your presence board is connected and the default name of the SPK. I also appended my serial terminal command here in order to have a quick get started of NuttX shell. Okay, I will build everything again. That remembers the SP2 from SP32 when it used the 100 kilobytes flashing baud rate speed. I hope this could be updated on some presence as well for a more higher bandwidth. Okay, so the terminal is ready. So are you seeing my nutshell here?
Yes, okay.
So here we have the built-in apps. We have this presence FOC. Load the autocomplete. So the parameters I made here is to pass the polypars of the motors. The motor I have here has 7 polypars. My encoder has a resolution, has a count per revolutions of 4K, and I will use a very small voltage in order to have a very slow motion on my webcam. So before I go to the webcam, I just put some. This is the alignment command, which is the electrical 0-degree rotor position found by the FOC engine. And here we can see some logs of what's happening on the accelerator. It uses the flag sent by the accelerator CPU for that. This is the calculated offset of encoder. Oh wow, it was aligned. I will stop sharing it again, and I will show you my webcam. Where's my webcam? I think I will use my enter screen. Okay. So now you are seeing my webcam. So this is the VLDC running at I think it's almost 1 rotation per second, based on the millivoltage I applied to its terminal. This is a power shield, which is very cheap. You can refer for simple FOC power shield. It's a Arduino compatible shield for doing FOC, and it figures lots of interesting features like the inline current sensing for closed loop control. And below we have this presence board here. Yeah. And I just added. I will invert the rotation and use it. I think it stopped it, right?
Yeah.
I just building everything because when I attached the shield to the BLDC motor, my reset button was not reachable. So I prefer to do a rebuild and reinstall the firmware and run the FOC command again.
Okay, it was running clockwise, right?
Yeah. So as you might suspect, to run it counterclockwise, I just need to provide a negative voltage for that.
Nice.
So I will just use it.
Just a comment. You can
here's it.
You can enable the Control C in the menu config, so you don't need to.
Even for infinite loop applications, or you need to configure a SIG handler on the application. I did this before, but I needed to code a signal handler for that.
Yeah, you need to.
Got it.
To handle it.
Got it. I will add that because I missed the Control C. And here's it. We have on the counterclockwise. And what could be the next steps here? Other things that could be done is the closed loop speed controller. So for calculating the speed, there are lots of PLL-based soft observers that's very superior, has superior performance when you just calculate the derivative of the encoder readings. Also, the same could be applied for the position closed loop. You can just use other CPUs to offload this control task for there and just use the main application to glue the processing of pipeline. Let me get back to my presentation. Well, folks, this is the thing I would like to show you for today. So, do you have questions? Do you have something to discuss? So please go ahead, and then, or I can simply read the chat. So. No questions?
Okay, let's see for the questions. We have only one comment from Andre. Yeah, Maju just put it. He said it's amazing. Yes, these as all your presentations about the motor control, they are very nice, and yeah, this one is very powerful because you are doing you are unloading the main CPU, right? So you can distribute the offload with all the other CPUs. Did you run some like some benchmarks to see the CPU usage running it in a single core and running it in multi-core on Netx? How the workload decrease for each CPUs?
Yeah, I don't have the results here, but I did that when I was doing this motor control interface for the context on last year. By running in the hard real time the FOC controller in a dedicated high priority speed thread, I achieved on the single core almost of 7% of the CPU by doing by doing all the controls and the FOC engine. By offloading the control and the platform independent, the CPU usage dropped to something about 25%.
Nice. So
which was very good because I could bring this the saving of bandwidth and spend it into the ROS communication, which was a bit half because we did not have the micro ROS transports in that time.
Yeah. Okay. We have another question. Maju, if you can put it online. The question is from Andre Almeida. Was there a need to create device driver or change some device driver, or it was mostly using what already existed?
Yeah, sure. This is one of the advantages I see on the embedded RTOS like NuttX, which is our true operating systems, not like free RTOS. Okay. When your SoC is supported on NuttX, it's very typical that it has at least the basic device drivers. On the CXD and Presence SDK, all the device drivers were already there. So I just needed to figure out where to open them by using its default path and just use it. So there's no need to change anything. The only strange step I did was to enable the individual outputs of the PWM, which were not enabled by default.
Yeah, maybe the kconfig need to be modified to enable by default when you the PWM.
Probably one of the dev configs are missing the setting because I tried several configurations and no one of them typically enable the outputs. The driver itself it's enabled and the lower half it's enabled, but the individual outputs were not.
Mm-hmm. Yeah. Other thing that is nice to you try later, like because you like to more of control, is the NuttX zero latency high performance interrupt. It bypass the kernel and run like a timer interrupt that run in few microseconds or maybe depending on microcontroller. If it's very powerful, you can even
you can grab all the bandwidth for that part of processing.
Yeah, it's very useful, and people using NuttX for CNC controllers and motor controls use these features. I will put the link later.
Got it.
Yeah,
I will check that.
And other suggestion for you to the next NuttX workshop was that idea that you told me some time ago but it should be for ESP32 S3, for example, to run NuttX in the RISC-V ULP.
Yeah. I think it should be very straightforward. I think you just need to map the LG files to the ULP dedicated memory, and because doing something there is just a matter of memory copy. The only thing that should be noted by the ULP, it's interrupt controller is not a standard one. It's a custom instruction. So probably some part of the Arch RISC-V or a folder arch RISC-V ESP32S3 ULP must be added there by providing some wrapper for that custom instructions.
Yeah. Okay. Nice. It's I think it's something interesting. Do you think it's possible to use it with Open AMP?
Sorry?
Do you think it's possible to use it with Open AMP?
You mean the presence, or you mean the?
No, I mean for example, the ESP.
No, I'm afraid no, because as I said to you, the most problematic feature of the OpenMP it's overhead, because ARP message protocol it's a bit heavy. Even with features capped, it will consumes easily tons of kilobytes to implement the basic ARP messaging, and the ULP target memory, which is shared between the data and the code, is about 16 kilobytes. So I'm afraid that will not fit, or if it fits, you will end up with 10% of code free for your application, and the other 900% for ARP messaging and the NuttX.
Okay, understood the point. And about this demo, the model demo is good. And do you think it's possible to make it generic to any Open AMP and microcontroller and integrate it on NuttX mainline? Because okay, go ahead. I think you got the idea.
I think should be very generic, because as I said to you on the accelerator side, the code is almost platform independent. The only platform dependent part is just the part of copying the data from the remote for exchanging data between the remote CPU, which could be replaced to the ARP message protocol for data exchanging. This is something I'm missing on the NuttX samples. I think some example of your OpenMP would be very useful for since it's very common that the multi-core asymmetric processor, asymmetric microcontrollers, it's being very common.
Yeah, should be nice to have this kind of example to let other people base on it.
Maybe some interesting stuff for the next workshop.
Yeah. We have now other. Okay, Andre Almeida just remove it, but he just said that should be nice to have the high performance implementation for the next event.
Yeah, sure.
So just to confirm with Maju, we finished the form to receive presence list for this presentation, right, Maju?
Yes, that's right.
Okay, so thank you very much, Philippe. Your presentation was really nice. By the way, your screen is shared, so people will
Please stop sharing.
Yeah. So thank you very much for your presentation. It was really nice to see the motor control using OpenAMP, and thank you very much for joining us for this event. I know the original idea was other talk, and you decided to do that. I think that was really nice and was really good as well. So
okay, thank you guys. Thank you, folks.
Thank you.
That, and I hope you see next year for these other ideas.
Yeah, sure.
Thank you very much.
Thank you.
Thank you. Bye bye. Okay, Ali.
Yes, thank you, Alan. The next presentation comes from Lup Yuan, and he will present the NuttX on RISC-V for an IoT target. Lup, can you play the video?
Yep, I'm doing it now. Hang on. Let me switch to full screen. Change the audio source.
We can see your presentation.
Hello, everybody. I'm Lup from Singapore. Today, I shall talk about a fun new gadget, Stack BL604, and how it ported NuttX drivers and apps to this device. Stack is a gadget for IoT developers that talks to the LoRaWAN IoT network. In a while, we shall explain the drivers and apps that we have created for LoRaWAN and the touchscreen. Building these apps in C might get too complicated, so we plan to build them in Z. Z is a newer programming language that works well with C, and it feels highly suitable for building IoT and touchscreen apps. We welcome developers from the Netx community to help create drivers and apps for Stack. We've done many interesting things to make the onboarding experience as smooth as possible. I will explain in a while. If you would like to download the presentation slides, please head over to this link, login.github.io/Netx. That's the letter L, not the digit 1. And all my presentations, articles, and source code are available at that link. So what is Stack BL604? Stack is a new IoT gadget by Pine64 that's packed with goodies. ST7789 display, I2C touch panel, Semtech SX1262 LoRa transceiver that will talk to LoRaWAN networks, GPS power management unit, accelerometer, compass, SPI flash, JTAG, push button. On top of all that, we also get Wi-Fi and Bluetooth LE. So Stack is an incredible IoT gadget in the form factor of a chunky watch. Looks like a smartwatch, but thicker. In fact, my good friend JF is building smartwatch firmware for this gadget. But do not rush online to buy this yet. It's not available right now. I will talk more about this. Here is Stack BL604 running an LVGL touchscreen app on NuttX. We can see that the ST7789 LCD display works great with NuttX. The I2C touch panel responds correctly to touch input. We're looking at the touch panel calibration of our touchscreen app. The screen refresh looks laggy due to an issue with SPI DNA. I shall explain why in a while. So what powers the Stack? Inside our IoT gadget is a Buffalo Lab BL604 SoC, 32-bit RISC-V with Wi-Fi and Bluetooth LE. Plenty of GPIOs, 23. This is the first RISC-V SoC by Buffalo Lab. No legacy stuff, though there are some SPI and I2C quirks I shall explain later. The RISC-V core is based on Sci5E24, and it supports hardware floating point, which makes it quite unique among RISC-V microcontrollers. But it also causes some interesting problems, as we shall soon see. BL604 is already supported by Netx today, so most of our work is in creating the drivers and the apps for Stack. I am very happy to report that the ST7789 display works perfectly fine with Netx, right out of the box. Graphical apps coded with LVGL library work okay too, just that we had some issues specific to BL604. SPI mode works differently on BL604, and MISO and MOSI are swapped strangely. Sadly, the rendering looks laggy today because SPI DNA isn't supported on BL604 yet. I'm really hoping that SPI DNA will be available for BL604 someday. Now, before testing on Pioneer Stack, I actually tested the ST7789 display on BL602. BL602 is a smaller sibling of BL604 with fewer GPIOs. I'm so glad that I had a logic analyzer. Some of the SPI and I2C quirks can be really tricky to troubleshoot on BL604, like MISO and MOSI getting swapped, SPI modes that work differently on BL604, or when the I2C sub-address doesn't get sent correctly. A logic analyzer is a great investment for any kind of embedded development. Things get challenging when we created the touch panel driver. Pioneer Stack has a high nitron CST816S touch panel based on I2C, which has zero detailed documentation. We don't really know anything about the I2C registers that it uses. All we have is a reference implementation of a CST816S driver that we reverse engineered to build a working driver, first for PineTime smartwatch and now for Pioneer Stack. I'm so glad that we have a touch input driver that works with LVGL apps on Netx. Though I2C on BL604 has some issues on Netx. You know, when we talk to I2C devices on an I2C bus, you need to send the register ID inside the I2C request. BL604 calls this the I2C sub-address, and it mandates that we send the I2C sub-address through a dedicated hardware register. But Netx assumes that I2C sub-address is part of the I2C data. So right now, Netx extracts I2C sub-address from the I2C data. Under some conditions, it doesn't quite work correctly. Perhaps we might need to extend the Netx I2C interface to support I2C sub-address as a separate parameter.
I think we are missing audio.
Yep. Hang on, let me fix this. Let's see. Sorry about that. Let me fix that. Let me fix that. Okay, my screen is a bit unstable. Hang on.
No audio yet. Yeah, maybe you need to do like Felipe did. You need to close and enter again.
Okay, sorry about that. My system is getting a bit unstable. Can you hear me?
We can hear you. Please close the presentation and start it over.
Unless we tap the touch panel and wake it up. Thankfully, we found an existing NuttX driver that works the very same
Look, please just
for the Cypress NBR 3108 touch panel. So we copy the logic into our driver and it works. BM604 supports only one single SPI bus, so we have a complication on Pioneer stack. The SPI bus is shared by three devices: ST779 display, SX1262 LoRa transceiver, and SPI. So this sounds really weird, but MISO and MOSI are swapped for the ST779 display. So we built an SPI device table that maps SPI device ID to GPIOs so that we can manage the chip select pin. And the table tells us whether
okay. I'm sorry. This is quite messed up. Let me see what's going on.
But it seems to be fine now if you just click play.
Okay.
Audio was back.
Okay, let me play it. Is it okay?
We are just asking to return a little bit because
got it.
It stopped. It followed one page before that. Yeah, that. Yeah.
Okay. Yeah.
Yeah. That.
Is audio okay now?
Yeah.
Can you increase the volume a little bit?
How about now? Is it better?
In case we are curious how the LCD display and touch panel are connected to Pioneer stack, here are the two ribbon cables. One for SPI display and backlight, the other for I2C touch panel. Now we might think that creating a touch panel driver should be as easy as any other I2C driver, right? Well, be careful. Touch panels are designed to consume as little power as possible. They won't respond to I2C commands unless we tap the touch panel and wake it up. Thankfully, we found an existing NuttX driver that works the very same way, the I2C driver for the Cypress NBR 3108 touch panel. So we copied the logic into our driver and it works. BM604 supports only one single SPI bus, so we have a complication on Pioneer stack. The SPI bus is shared by three devices: ST779 display, SX1262 LoRa transceiver, and SPI flash. So this sounds really weird, but MISO and MOSI are swapped for the ST779 display. So we built an SPI device table that maps SPI device ID to GPIOs so that we can manage the chip select pin. And the table tells us whether MISO and MOSI should be swapped. At the left is our implementation of the SPI device table. ST779 display, LoRa transceiver, SPI flash, and their device IDs, whether MISO and MOSI should be swapped, and their chip select pins. This is how it looks inside our SPI driver. It's essentially the same table, but flattened into an array. And we validate the SPI device table at startup in case we goof up and make a mistake. We might think that too many GPIOs is a good thing, right? Well, having too many GPIOs can bring interesting challenges. BL604 is essentially a big bag of GPIOs, 23 GPIOs in total. This sounds unbelievable, but all 23 GPIOs are used on Pioneer stack. ST779 display, compass, GPS, accelerometer, touch panel, JTAG. Because with so many features on Pioneer stack, 23 GPIOs are simply not enough. Some GPIOs are used by multiple features, so we need to manage them carefully. We have implemented a GPIO expander that might help for the development of drivers and apps for Pioneer stack. Let me explain. The standard behavior on NuttX is to allocate GPIOs sequentially. GPIO 0, 1, 2, and so on. Suppose I'm building a LoRa driver for SX1262. Now, when we have 23 GPIOs, this gets messy. Suppose I'm building a LoRa driver for SX1262. Which GPIO should I use? Will this GPIO change as we add more drivers?
There's some issues.
This is why we built a GPIO expander that allocates GPIOs according to the actual GPIO number. So if I'm building a LoRa driver for SX1262, I only need to concern myself with GPIO 10, 15, 18, and 19. It feels more friendly for building drivers and apps. Lately, we've seen an explosion of GPIOs on newer SoCs. BL604 has 23 GPIOs. CH32V307, also based on RISC-V, has 80 GPIOs. I'm now porting NuttX to PinePhone, which has 116 GPIOs. Perhaps this might be the better way to manage GPIOs for devices that have way too many GPIOs. Here is another consequence of having too many GPIOs. BL604 will let us designate any GPIO for UART port, I2C port, SPI port, PWM, or just a plain GPIO. But when we designate a GPIO for a specific port, like SPI, the GPIO is stuck to that specific function for the port. Suppose you designate GPIO3 for the SPI port. Then GPIO3 must be SPI clock, not MISO, not MOSI. Now a BL604 developer might configure NuttX, such as GPIO3 is assigned to the SPI port, and assume that GPIO3 works okay for SPI MISO, but it won't. Can we prevent such mistakes? We might have two solutions for this. GPIO expander could validate the GPIOs at compile time or at runtime. The first solution is to define all possible choices of, say, SPI MISO. At compile time, we shall verify that GPIO0 is supported for MISO. If we try to designate GPIO3 as MISO, the compiler stops us because there is no definition that matches GPIO3 or MISO. That is one way to prevent our developers from picking the wrong GPIOs. The second solution is to verify the GPIOs at runtime. When our GPIO expander is loaded at startup, it checks every GPIO and the function that it's designated for. This simple implementation assumes that our GPIOs are listed in a predefined order. UART receive, then transmit, receive, then transmit, I2C, SCL, then SDA. Our GPIO expander verifies each GPIO according to the predefined order. We haven't implemented GPIO validation for Meadow Stack, but this feature might be super useful for devices with many GPIOs. Let us talk about the most interesting feature of our IoT gadget, LoRaWAN. LoRaWAN is a low power, long range, low bandwidth, wireless network IoT sensors. By long range, we mean 5 kilometers or 3 miles in urban areas, and up to 15 kilometers or 10 miles in rural areas. But LoRaWAN is also constrained by low bandwidth. Depending on data rate and radio interference, we might expect to send 50 bytes in a packet. To minimize packet loss, it's probably safer to send 10 bytes in a packet. Pioneer Stack has an onboard Semtech SX1262 LoRa transceiver that supports LoRaWAN. Semtech has a reference implementation for the LoRaWAN network stack that we ported to NuttX. LoRaWAN devices at Pioneer Stack will send packets to a LoRaWAN gateway. We have tested two types of LoRaWAN gateways: a private gateway that is chirp stack running on this black box here, and a public gateway, the Things Network, which is a public LoRaWAN network that is free to use worldwide. Our LoRaWAN stack also works on ESP32. Some folks in the Netx community have confirmed that it works on ESP32. Earlier, we said that Semtech, the maker of the LoRa transceiver, has a reference implementation of the LoRaWAN network stack. There are two parts in the LoRaWAN stack: the SX1262 library that controls the SX1262 LoRa transceiver, and the LoRaWAN library that implements the LoRaWAN protocol. We ported both parts to NuttX as NuttX libraries. But shouldn't networking protocols be implemented in a NuttX kernel as NuttX drivers? Well, the LoRaWAN specification is still evolving today. It defines new geographic regions and the radio frequencies permitted for each region. That's why we kept changes to a minimum, and we run the LoRaWAN library as is, nearly identical to the reference implementation. So if the LoRaWAN specification changes, we only need to merge updates from the reference implementation. It's easy to do this in a NuttX library, harder to do in a NuttX driver. Our LoRaWAN library calls Nimble Porting Layer, an open source library that provides multi-threading, message queues, and timers. Could we have done this by calling NuttX directly? Most certainly. Just that I'm more familiar with Nimble Porting Layer, having used it in a couple of projects. By the way, Nimble comes from another Apache project, the Minute embedded operating system. We tested the LoRaWAN stack in 3 ways. First, we use a software-defined radio as a spectrum analyzer to verify that our LoRa transceiver is transmitting at the right frequency and with the right power. Here we use AirSpy as the software-defined radio to capture the packets transmitted by our LoRa transceiver. LoRa packets have a distinctive shape. We call it the LoRa chirp. Maybe because it works like a bird chirping across frequencies. When we see the LoRa chirp, we know that LoRa works. LoRaWAN builds upon LoRa, so we test LoRaWAN next. This black box is a LoRaWAN gateway that I bought from Rec Wireless. It's actually a Raspberry Pi inside. In the LoRaWAN gateway, we run ChirpStack, the open source LoRaWAN stack for private LoRaWAN gateways, and we transmit a LoRaWAN packet from PioneerStack. We verified the packet was received correctly by the LoRaWAN gateway. ChirpStack shows the packet received by Netx. From private now to public, we test with a public LoRaWAN gateway, the Things Network, which is a free-to-use worldwide LoRaWAN network. This white box is the new prototype LoRaWAN gateway from Pine64, which we have configured to run as the Things Network gateway. So this white box becomes a base station for the global LoRaWAN network. On PioneerStack, we transmit a packet encoded with CBOR. More about CBOR in a while. The Things Network receives the packet, decodes the packet, and shows the packet data in text. Yet, PioneerStack works great with the Things Network. Now, LoRaWAN is super interesting, but also super complex. Our LoRaWAN app needs to handle multi-threading, since the LoRaWAN protocol is asynchronous. LoRaWAN is also time-sensitive. We have a 1 second window to receive the response. If we miss it, we can't send any data. Our data should be encoded with CBOR, that's short for Concise Binary Object Representation, a binary compressed form of CBOR, since LoRaWAN packets are so tiny. To manage all this complexity, we propose to build IoT apps in the Zig programming language. We tested it. Zig works seamlessly with Netx and LoRaWAN, and Zig might actually make it less painful to maintain and extend a LoRaWAN app. To learn more about this, please check out the presentation, Visual Zig Programming with Netx Sensors. What do we hope to achieve with LoRaWAN on Netx? Someday we could send IoT sensor data to the Things Network and ingest the data into a Prometheus data store and visualize the sensor data with Grafana, like this. Prometheus and Grafana are both open source tools that we can run locally on our own computer. This works really well with multiple devices, multiple sensors. Imagine an IoT sensor network running on NuttX devices. Our IoT gadget won't be so fun and interesting unless we create touchscreen apps with little effort. Today, we can build touchscreen apps with the LVGL graphics library, but the code looks kind of messy, lots of repetition and clutter. Maybe we can build LVGL apps the simpler, safer way with the Zig programming language. Please check out the details in this presentation. Simpler, safer LVGL touchscreen apps with Zig and NuttX. At the left is a typical LVGL program in C. Lots of LVs, long function names. At the right is our proposed LVGL program in Zig. Tidier, less repetition, shorter function names. Zig might become the preferred way to build IoT apps and touchscreen apps for Pioneer Stack. This is a demo of an LVGL touchscreen app running on Pioneer Stack BL604. We will see the Zig version of the touchscreen app, which looks just like the C version. We have compiled the Zig touchscreen app into the NuttX firmware. Pioneer Stack is now booting the NuttX firmware. The screen turns pink when NuttX boots. There is a reason for that. Check out my article on ST7789. Uname says that this is a recent build, NuttX version 10.4.0. Let us check the NuttX devices. We see the GPIOs listed according to the actual GPIO number. That is because we created a GPIO expander, specially for Pioneer Stack. We see the LCD device, LCD0, that is connected to the ST7789 LCD display. Our touchscreen app will render graphics to that device. And we see the touch input device, input 0, that is connected to the CST816S touch panel. Our touchscreen app will read touch input from that device. Let us run the touchscreen app. Remember, this is a Zig app that we have compiled and linked into NuttX, though it still contains some C code. The touchscreen app begins with the touch panel calibration. We need to tap all four corners of the screen to complete the calibration. The screen refresh looks laggy. Hopefully this will be fixed when SPI DNA has been implemented for BL604. When we tap the screen, our I2C touch input driver captures the touch coordinates and passes them to our app. Our app computes the calibration and renders a simple text label. Hello, Pioneer Stack. This is done in Zig. And that was a demo of our LVGL touchscreen app in Zig on Pioneer Stack BL604. One of the toughest challenges for Pioneer Stack is to keep it in sync with NuttX mainline. Because as we build new drivers and apps on Pioneer Stack, NuttX continues to evolve. Today, we're not quite ready to push Pioneer Stack up to NuttX mainline. So the onus is on us to make sure that Pioneer Stack runs on the latest mainline code. At the same time, we also need to be sure that any new drivers and apps contributed by Pioneer Stack developers won't break the existing code. Our solution is to use automated testing. In this photo, we see Pioneer Stack controlled by a Raspberry Pi that will flash the NuttX firmware to Pioneer Stack and test the firmware. The two tests that we run automatically on Pioneer Stack are LoRaWAN and touch panel. If the two tests succeed, we can be sure that LoRaWAN and touch panel are okay, which means that SPI, I2C, GPL interrupts, timers, message queues, multi-threading are all okay. So it's a pretty comprehensive test for Netx features. At the bottom here is a Pinecone BL602 connected to a LoRa transceiver, which is also tested automatically. We say that the test is mostly automated because right now I need to tap my finger on the touch panel for the touch panel test. Maybe someday we can do that with a robot finger. You can watch the automated testing on YouTube here. Let us watch a quick demo of automated testing on PioneerStack BL604. We are now running the automated testing script on a Raspberry Pi that controls PioneerStack. The script downloads the Netx build that was auto-built by GitHub Actions. It switches PioneerStack to flashing mode and flashes Netx to PioneerStack. After flashing, it boots PioneerStack. Netx begins booting. When it sees the NSH prompt, it checks that the SX1262 LoRa transceiver is okay. Then it sends the LoRaWAN test command, which connects PioneerStack to our LoRaWAN gateway, waits for the response, and sends a data packet. That's the data packet. And yes, we have successfully completed the LoRaWAN test. One more test to go. Our script reboots PioneerStack and starts the touch panel test. So far, everything we've seen is running fully automatically, no human intervention needed, except for this. You see this message? Hello, human. Touch PioneerStack now. This is when I run over to PioneerStack and tap the screen. This registers a touch event on the touch panel. Our testing script detects a touch event and records that we have successfully tested the touch panel. Our testing script uploads the entire test log to the GitHub release notes as a public record. And that's how we do automated testing on PioneerStack. The logs for the automated testing are also uploaded to GitHub release notes. So this becomes a public record that this Netx build works for PioneerStack. And it works okay with LoRaWAN and the touch panel. In the center, we see the LoRaWAN stack submitting a packet to our LoRaWAN gateway. This is only possible after you have successfully joined the LoRaWAN network, which means that PioneerStack has correctly processed the joint network response from the LoRaWAN gateway. At right, we see the PioneerStack responding to the touch my finger, which means that an I2C touch panel driver is working okay. How often do we run these automated tests? Well, we target to merge and test the updates from Netx mainline every 2 weeks, so that PioneerStack developers are always working on the latest and greatest version of Netx. We auto-test Netx on 2 devices, Pinecone BL602 and PioneerStack. That's because there are many more BL602 devices out there than PioneerStack. What if there's a problem and PioneerStack won't boot? Well, that's why we run a daily build and daily test for Netx mainline, triggered by a scheduled script at GitHub Actions, which means we can backtrack to the last daily build in case there's a problem, and find the last build that boots okay on PioneerStack. So feel free to check out the GitHub releases from the Netx repo. You'll see a fresh new report every day of Netx booting on BL602. We talked about automated testing, building simpler and safer apps in Zig, We're doing all we can to help developers get on board Pioneer Stack the quickest way possible. Instead of dry reference documentation, we have articles with stories, photos, and sketches. Over the pandemic, I wrote 60 articles on BL602 and BL604 and compiled them into the RISC-V BL602 book, covering all kinds of topics. I hope our developers will find them useful. We are eagerly waiting for our developers, but we hit some difficult challenges beyond our control. Sadly, Pioneer Stack is not on sale yet, which I perfectly understand because of supply chain constraints and the pandemic situation in Asia. LoRaWAN is also a tough problem to crack. How will developers get access to a LoRaWAN network? Maybe we need more LoRaWAN gateways in schools, or we contribute more public gateways to the Things Network, or should we switch to Wi-Fi or Bluetooth LE for sending sensor data? We are working with plenty of new and unfamiliar hardware in Pioneer Stack. Should we work with existing hardware that is a little more familiar? While waiting for Pioneer Stack to go on sale, I'm now taking everything that I've learned on Pioneer Stack and applying them to the existing familiar device. PinePhone, the mobile phone based on all-winner A64 SoC. This thing here. Why port NuttX to PinePhone? Why not choose a single board computer like Raspberry Pi? Well, I think it's highly educational to document the process of running NuttX on a real phone that we might use every day. And someday we might even use PinePhone to teach our students about the internals of NuttX. The progress has been great. NuttX now boots OK on PinePhone all the way to the NSH shell, as we see in the photo here. We have plenty of drivers and apps to build for PinePhone. Zig drivers for NuttX might be super interesting to see on PinePhone. Check out my articles and progress here. By the way, LoRa is available on PinePhone. Just get the LoRa back cover that attaches a PinePhone. Maybe the work that we've done on LoRaWAN will port easily to PinePhone. In this presentation, we have covered many topics. Everything that I covered is explained in these articles, including the source code, Pioneer Stack BL604, the GPL expander, the touch panel driver, LVGL graphics, automated testing. If you would like to download the presentation slides, please head over to this link, lapyuan.github.io/NuttX. This is the letter L, not the digit 1. All my presentations, articles, and source code are available at that link. But wait, there's more. LoRaWAN is super complicated, so we need a few articles to cover the LoRaWAN transceiver library, the LoRaWAN library, and how we build a LoRaWAN app with Zig, plus another article on touchscreen apps with Zig. NuttX is perfect for IoT gadgets like Pioneer Stack BL604. NuttX has everything we need for creating our own LoRaWAN and touchscreen apps. These apps might get too complex for C, but no worries, we can create IoT and touchscreen apps in Zig too. We are all set to welcome NuttX developers on board Pioneer Stack as soon as the devices start shipping. In the meantime, we shall continue porting NuttX to PinePhone and apply all the valuable lessons that we have learned from Pioneer Stack. Thank you.
Okay. Thank you, Lub. Yeah. So,
maybe I should clarify the questions that were asked about the GPL expander.
Yes, please.
Yes, so there was a comment on YouTube. Robert, by the way, is my collaborator on Pioneer Stack. We actually work together on these drivers. Yeah, so the thing about Netx on BL602 and 604, by default, it numbers the GPLs like this, 0, 1, and 2, right? But because we got so many GPLs here, and we have potentially different developers working on different drivers with different GPLs, so we thought maybe for now, it might make better sense to just number the GPLs like this. So the GPL numbers are actually the actual GPL numbers in hardware. So if I'm building a LoRa driver, I'll just use GPL 10, 12, and 14. If I'm building a accelerometer driver, I'll just busy myself with another GPL. So that way, the developers don't have to clash, don't have to worry about which GPL numbers that will eventually be there. They just use the actual GPL number. And to implement this, we actually built a GPL expander. So this is actually an add-on on top of NuttX that treats all the GPLs like a huge GPL expander. I get a point about Alan. Yes, this is something that we could actually improve in the architecture for BL602, BL604. Eventually, when we roll this out for BL604, we could do it in kconfig, a nicer way to organize these GPLs. But right now, as we're waiting for developers to come in, this is probably the best way to do it for now.
As I comment in the chat, I think this kind of policies need to be done in other level, not in kernel, because in the kernel you cannot forbid. You cannot change this GPIO config, this MUX config, because it will impact in other pin. The kernel is not supposed to have this kind of intelligence or this kind of control. It needs to be done in other layer, a little bit upper than the kernel. For example, we could use the kconfig itself, like Robert Lee said, or device. Now, I think now it's with you. We have some more. I think we don't have more questions. Okay. We saw some questions.
I do have a question. Sorry.
Okay, go ahead.
Yes, Michael.
Hi, Lup. You talked about automated testing of your code, basically. Did you already look into code coverage analysis using Chekhov or something to analyze how good the code coverage from your test suites is?
No, not quite. So my automated testing is more on testing the actual hardware, the actual drivers. So it's more like an end-to-end test. So it's testing from from a device to a LoRaWAN gateway or to a touch panel. So making sure that the end-to-end stuff is working, but not the internal. So this is not a coverage test and all that. But I guess that could be something that we should explore. Yeah, coverage testing, unit testing. That looks like a good way to do parallel testing. Yes.
Anybody else having any experience with collecting coverage data from a microcontroller?
Not for microcontroller. I remember in another automotive company I worked some years ago. We used I can't remember the name. It's a tool from Google. It was a company that Google bought to do this kind of coverage. I think it's used mainly for Android. When people are using Android, the idea was mainly to see which functions most users are using. So I think it should be nice to have something like that for microcontrollers to see what peripherals or what features they are using. Right? That's something you are looking for, correct?
No, I'm looking for testing the firmware. And I want to see which lines of code have been executed by my test cases, which is easy on a PC. You have the GNU compiler has everything in it to create coverage reports. So you run a test suite, and then you can look at the result, and it says this line of code has never been executed by your test suite. And then you can add a new test to make sure that all code is touched at least once by your test suite. And this is easy to collect on a normal PC where you have lots of memory, and you can just instrument the code to collect the coverage data and write it to a file, basically. But on a microcontroller, you typically don't have the additional memory that you need to instrument the code with collecting coverage data. So I was just wondering if anybody had.
Yeah, I think we only have the Unity, the True Suite software that is used to only for tests, but not for this kind of coverage.
Okay.
Yeah.
I would guess that something like this is also possible with QEMU, so that QEMU actually writes out the addresses that have been fetched, instruction addresses, but I'm not aware of this use case.
But it's still, sorry, Ali, but it's still you keep using the computer because you are running QEMU, right? So it'd be nice to have something running directly in the microcontroller.
Yeah.
I personally think that we should open discussion on the dev board regarding this, because it has a better chance of getting some answer, Michael. So if you can send an email to the dev board, if somebody encountered this, I'm also interested because I do not know.
Okay. Yeah, I will write an email.
It would be interesting because on Linux you can do this coverage, but on microcontrollers I never saw one.
Yeah. I think Dave Marples in Gouda talked about a tool called Orb. What was it called? Where you could basically trace the instructions in real time while the processor was running via debug output pins. And he had an FPGA setup where he could collect this data.
Orb trace.
Orb trace, right.
Thank you,
And this is probably, then you don't need any additional memory. You can just...
I think he posted they developed the tool, I found it, the trace here, orbcode.org. I'll put the link in the YouTube chat so people can see it.
Okay. Okay, thanks. I will write an email to the developers list. That's a good idea. Thank you.
Thank you, Michael.
I think Orbitrace can do it, but again, it's not something that you use without computer. It's not like these tools that we have in Android or other high-level platform that analyze the code and submit users information to some server to something else. Yeah, okay. We also have some questions about people here in Brazil asking if we will have some break time. Unfortunately, we our idea is to keep running all the time. We know we have many people from Brazil here, but it's lunchtime here for us, but in other place, in other country, it can be early or night. So our idea is to keep the day long, all day long, even. So we need to find some time to eat some sandwich or something, some lunch very fast to not lost any nice presentations. By the way, I am going now. I think Maju just returned from the lunch, so I will lunch now very fast, and I will just return here. I will keep watching here. Okay?
Yeah, don't worry, Alan. Thank you. We will continue today's schedule with the next presentation from Yuka, and he will talk about NuttX running on the microchip polar flare FPGA.
Okay, just let me share my screen.
And here you are on full screen.
Okay. Okay, please let me know if you can see my first slide and here.
We can see your slide.
Okay, great. Thank you for joining. My name is Jukka Laitinen, and I'm acting as a lead software developer and software architect in this Secure Autonomous Drones project in Secure Systems Research Center in Technology Innovation Institute. I'm not going to talk much about the organization, but just a few words about the TII. So it is a state-funded research organization based in United Arab Emirates in Abu Dhabi. And it's an umbrella for several research centers who are funding and running research projects, for example, public university research all over the world. And more information about TII you can find from the webpage tii.ae. But now I'm just going to talk about NuttX and microchip polar fire SoC FPGA. So these are my topics for today. I'm not going to dive into very deep detail, technical detail on anything, but give an overview of the project and what is the polar fire SoC about and what are the hardwares that we have been using to do the port and what we have contributed and what is available there in NuttX port and so on. So first I will give a short project overview and why we did the NuttX port. Then I will talk about the polar fire SoC. Then I will talk about those hardwares that we have been using and what features are there available and so on in our NuttX port. And then we also delivered some generic RISC-V related improvements to NuttX. I will go through those. And then in the end, I will also talk about some of the challenges that we faced. Okay, so first about the project overview. So the main use case is autonomous secure drones. We have been developing technologies to make drones more secure and safe and resilient so that they can be used without worry in different use cases for private hobbyists or for professional use or state authorities or rescue or any of those use cases. And our system that we are securing ranges from services running in the cloud to web-based operator UIs, drone fleet management for several drones, some autonomy and machine learning things. And then down there is the single drones, which have the software of their own. And the piece of software that makes the drone really fly is the firmware called flight controller firmware or autopilot software. And when we decided to do this secure system, of course, the flight controller is also part of the system. So we decided very early that we are going to secure that as well. And very early in the project, we identified PX4 as the most feasible open source flight controller software for the project. PX4 is based on POSIX interfaces. So it's typically run on NuttX, on real drone hardware, and typically run on Linux, on simulator, and some things like that. So this is already great that it's running on NuttX. It's a good reason to select PX4 alone. And also very early in the beginning, we had an idea that we may need to build a hardware of our own at some point. And NuttX was seen as straightforward to port to new SoCs and new hardware because NuttX is so mature and modular and has been already ported to so many hardware architectures. Now, we started the project using off-the-shelf flight controllers that you can buy out of the shops, and they are based on STM32 microcontrollers, which are great. But very soon you find out that if you want to add some more complicated things into the software there, like crypto algorithms, if you want to enable some memory protection functionality or things like that, you will soon run out of CPU power, you will run out of memory, and you don't have proper memory protection. Those STMs have MPU, which is very difficult to use for more complicated software stacks. So we saw that we will probably need to do some hardware of our own that enables those things. And when we started to enable our own hardware, we also wanted our own hardware to be able to run different operating systems, both trusted execution environments and also rich execution environments such as Linux and real-time operating systems. And while on it, we also wanted to have hardware security and crypto capability. Now, Secure Systems Research Center is also working on some SoC projects of its own. So they are building their own SoCs as well, and they are based on RISC-V. So when we started to do our own flight controller hardware, we also wanted to have synergies with those upcoming SoCs. So we wanted to select the RISC-V CPU that has all those features listed above. So from there, we ended up with this microchip PolarFire SoC. There were many steps in selecting that, like availability and so on. But it was seen as a good choice for this project. So this is the SoC, how it looks like. In the top middle, you can see the CPU cores. So there is one E51 monitor core, which is a 64-bit RISC-V heart, which is somewhat stripped down, so it runs only in machine mode. It doesn't have MMU, it doesn't have floating point unit, but it's a monitor core that is responsible for example, booting up the device and doing some simple monitoring during the runtime and that kind of things. Then there are 4 pieces of application cores, RV64 cores. It's a U54 core, and it has got an MMU and floating point unit and everything that you typically find in application processors. Then we have a 2 megabyte memory, internal SRAM type of memory, which is configurable as either L2 cache, or you can use it just as like an SRAM, or you can also split it to be used as both. For example, we are using it as 1 megabyte for L2 cache and 1 megabyte for internal RAM. Then the SoC has got a DDR controller and DDR5. So when you need loads of memory, you can just drop in an DDR chip right next to the SoC to get gigabytes of memory. Then on the right side in this picture, you find the typical microcontroller blocks, like you have got 2 gigabit Ethernet blocks, MMC SD block, 2 CAN blocks. They are CAN 2.0 blocks actually. Then QSPI for execute in place NOR flash integration. You've got 2 SPI buses, 2 I2C buses, 5 UARTs, some GPIOs, real-time counter, and USB. And then you have also got a crypto processor. And in addition to those, you have got a pretty big FPGA fabric integrated into the same package. So whatever you are missing in those
hard IPs, you can drop in a soft IP to the FPGA fabric. And here is the same, more or less the same thing written down. So for application processing cores, we are running them at 600 megahertz, 32 kilobytes of L1 cache, MMU, PMP. So PMP is the memory protection unit, similar to STM's MPU. And then the monitor processing core, 2 megabytes of SRAM, and DDR controller. And this is a very nice feature, the cache coherent CPU bus matrix. Basically, you never have a need to do cache invalidate or cache clean with the CPU. It's always coherent, no matter whether you are dealing with some external peripheral or DMA or anything. The hardware takes care of that. I'm not a hardware engineer, so I can't explain how it works, but it's just like magic. It just works, and it's really nice. It has got some 128 kilobytes of embedded non-volatile memory, so internal flash or bootloader usage. And the list of those peripherals that I already went through. And some security features which we like. So it supports secure boot, some anti-tamper functionality, so you can actually make a mesh over your hardware which triggers something if you go tampering with the device. There is a high-end crypto core processor which is a Athena Terafire. There is secure storage for keys, unclonable function, and so on, and then the FPGA. Okay, so now I'm going to talk about the actual NuttX porting thing. So these are the hardwares that we use to do the port. On the left, there is the microchip PolarFire Icicle kit. We picked this because it was easily available. You could just buy it and it came in days. So it's a big board which has the PolarFire SoC soldered on and all the peripherals also soldered on the same board. All the everything exposed on connectors. You've got the Ethernet ports, SD card, eMMC, DDR, everything single board. And actually, we in the very early phase in the project when we got the first versions of the NuttX board ready, we also made a sensor board which contains some gyroscopes, accelerometers, barometers, and other things like what you need for flying a drone, and plugged it into this, and then we bolted this whole thing into a drone and just flew it for fun. It was quite a Frankenstein monster for a drone, but really cool. And then after that, we moved to this Aries board on the right. So there is a SOM module in the middle, the white one, which is approximately the size of, say, 4 times 8 centimeters or so, which has got the PolarFire SoC and the memories and clocking and powering all in one SOM module. And the idea of this is that you can then take only this SOM module and design your own carrier board and make a real nice flight controller out of that. And we actually did that then too. This is the big green one is just the development board where you can plug in the Aries module for development purposes. It's more or less the same as the PolarFire Icicle kit. In the end, it's just that, well, the DDR is different, but other than that, it's exchangeable. And now to the software setup that we are using this with. So this is the most complex software setup that we are running, the PolarFire. We are also doing sort of only parts of this configuration, but we are also running this whole stack here. So starting from the left, we have got the E51 monitor core, which runs one version of one build of NuttX. And there we have our own bootloader application, which is started by NuttX instead of NSH shell. This is basically a new PX4 bootloader, which is a little bit enhanced. So we have added some features to it. And what bootloader does here is just that it reads out software images from eMMC, writes them to the DDR, and then it uses IPI interrupts to other hearts to start executing those software images on them. And we have done a static allocation of resources for each piece of software. So we are running on one heart, we are running operating system called SCL4. It's basically a formally verifiable operating system, and we are running some trusted execution environment on that. It's maybe not so interesting in this context. But then on one heart, we are running another instance of NuttX and PX4. And this is the thing that makes the drone fly. So it has access to some of the memory and the sensor buses and everything that PX4 needs. And then we have got two more hearts where we are running Linux. So all of these are running in parallel. And these things are communicating with each other over OpenAMP RP message communication. So, for example, between NuttX and Linux, we are setting up a IP network. So there is a UDP IP communication between PX4 and Linux ROS2 here. And on the FPGA, we are putting some blocks that we needed in addition to what is already there in the SoC, like PWM and some I/O configuration and so on. Now the features that this port supports, there is a code boot support. So we don't need any external bootloader to configure the hardware. The project started with using HSS from Microchip. It's a hard software services, basically a bootloader that can configure clocks and DDRs and those things, and then boot some application payload. We started the project with that, but eventually we decided to use NuttX also for the bootloader. So we built clock configuration and DDR training and those things into NuttX drivers. So NuttX can then boot out of the power on reset directly. And it can do that on any of the cores, both on E51 and on any of the U54 cores. It's configurable by the dev config. Then we have done the peripheral drivers, the serial driver. Of course, the first thing that you have to do to get the NuttX shell running, the most exciting part is to see the NuttX shell for the first time. Then, of course, IRQ, DMA, and the SPI and I2C drivers, which are needed for all the sensors for PX4, those gyroscopes and accelerometers, barometer, compass, and so on. And then USB, where we did the composite CDC ACM, that is the TTY serial communication over USB, and then the mass storage support. And mass storage support we are using in our bootloader so that we can just plug in the USB cable and the internal eMMC of the device comes visible on your PC. So you can just then, for example, partition the eMMC and format the partitions and copy the software images there and so on. So it's easy to use. We have the Ethernet driver and eMMC and SD card drivers, of course, and GPIO. And then the PWM, which is typically used in at least in hobby-grade drones to run the motors, is not part of the hard IPs on the SoC. So, but luckily there is this core PWM as a soft IP available in microchip libraries, and it's free to use. So you can just do your FPGA design and drop in the PWM block there. And then we also made the NuttX driver for this PWM to fly the drones. And also CAN driver. We actually wanted the CAN FD, and there is no hard IP for that either. So we have used our own FPGA design for CAN FD block and made a driver for that. The CAN driver is not upstream yet. We have to little bit think about whether it's usable for others or not. Maybe if it supports the existing CAN 2.0 blocks that are there, then maybe it's worth upstreaming that. Then IHC, it's an abbreviation from Inter-Heart Communication. It's basically the OpenAMP RP message driver used for heart-to-heart communication, as I mentioned, between the NuttX and Linux. And these basic baseboard and drivers is mostly done by Eero Nurkkala and Janne Roosberg, who we got to do the basic baseboarding. Eero especially has done a lot of drivers for us. Now this baseboard for MPF also supports all the build modes. So we are running it in all config build flat, config build protected, and also config build kernel on real hardware. Everything related to config build kernel is not yet upstreamed. It requires integration of some SPI implementation. I won't spend time now describing those RISC-V privilege modes and SPI because Masayuki did that very nicely in the first presentation already. But we have had 2 SPI implementations basically in use, both OpenSPI and then something that we made ourselves only for NuttX. But config build flat and config build protected work out of the box, and there are actually ready-made configurations for both Icicle board and RES module for those in the upstream. And we decided to do the protected build using the MMU instead of the PMP, which we did just because we want to leave the PMP unit. PMP is the physical memory protection, and it's similar to the MPU, so it's the simple memory protection unit. So we are using PMP for this AMP usage so that we can do the static allocation of memory for these different operating systems so that they cannot mess with each other during runtime. SMP support we didn't do yet because we didn't do it. It's possible that we will go there as well, but I can't say yet. Now, some generic RISC-V NuttX improvements. Most of this page is done by Ville Juveen in our team as well. So we wanted to run NuttX in kernel mode. We saw that it's really, and it's actually something that NuttX has ready-made concept for the thing, but it was not yet there for RISC-V. And we wanted RISC-V, and we wanted the MMU, and we wanted kernel mode as well. So we did the SV39 MMU driver so that we can use MMU and PolarFire. Configuration option for running NuttX in S mode. And, we also did some PMP functionality improvements, just checking that PMP is properly configured. And then a load of things to make kernel build work for RISC-V. So we did Ville did the address environment for RISC-V and page allocator, and some fixes for task environment initializing and corrections to ELF loader, CRT0 compilation. So this is the entry point for applications in kernel build. For RISC-V, it didn't work. Some libc improvements, basically exit functionality, and then some glue logic for SPI integration. Some of this is not yet upstreamed. And then we have this minimal SPI implementation as well, which is capable of running NuttX in kernel mode without any third-party SPI, such as OpenSPI. Masayuki actually explained it already quite nicely, that NuttX actually only needs the machine mode timer handling and hard ID reading and some IPI support, that is interrupts between the hearts. And to implement those directly into the NuttX is just a very little amount of code. So we made a small SPI implementation, which we call NuttSPI, so that we can easily run NuttX in kernel mode in that case that we don't want to run any other operating systems there. If we want to run also Linux and SCL4, then we are using OpenSPI, but I will also talk a little bit more about that later. Now, some of the challenges that we face. It had some peripherals missing, something that we really needed. So typically, drone flight controllers have several sets of sensors redundancy, typically triple redundancy, for example, 3 accelerometers, 3 gyroscopes, and so on. But there are only 2 SPI buses. It's always nice to have a dedicated bus for each sensor so that if the sensor breaks, it doesn't break the whole bus. But we have to actually share now the buses with several sensors, and same with I2C. We also needed both eMMC and SD card, but there is only one SDMMC block in the hardware as hard IP. Also, there was no PWM and no CAN FD, which we needed. But we mitigated these issues by instantiating the missing blocks on the FPGA, and also some of the problems about sharing those buses. Of course, we could instantiate more SPI blocks as well, or I2C controllers on the FPGA, and we could instantiate also another SDMMC block on the FPGA, but we didn't need to do that yet because, for example, with the SPI buses, those SPI buses go through the FPGA matrix. So we can actually do some muxing in the FPGA so that one SPI bus is only connected to one peripheral at the time when the peripheral is used, by using the chip select signal as a control for the mux. Something that was funny to find out was that there is a real-time counter supporting calendar functionality in the PolarFire, but real-time counter is powered from power domain as the whole SoC and clocked from the same clock tree. So if you power off the device, the RTC goes off, and using backup battery is not possible because if you have got the whole SoC alive, it eats up the backup battery very soon. So only thing that we managed to go around of this issue was that we put an external RTC chip into the hardware. Of course, documentation is always lacking. It's really great in some STM chips, for example, but for many other SoCs, there is always something missing. But luckily, Microchip provides a very good open source example code with permissive license. The hard software services bootloader, which I talked about, and some bare metal drivers and examples, which are all free to use pretty much as you wish. So you can read it and use it to write NuttX drivers. Also, some drivers turned out to be complex and time-consuming to develop. DDR training, for example, it was rather big bunch of code and took several weeks to complete. Ethernet driver, well, that was not a surprise for me because I have done some Ethernet driver for NuttX previously already, or STM32H7. And USB driver was big because we wanted to do the composite DDC, ACM, and also mass storage. So it turned out to be big. But it came out really nice. So these are working nice on the platform. Internal flash turned out to be really small for our purpose. So just 128 kilobytes. If you look at some of the very tiny STM chips again, for example, they typically have like 2 megabytes of internal flash. And this is a big quad-core SoC, and it only had 128. Okay, it's just enough for our bootloader. We have to, we want to use OpenSPI there in the case that we are also running Linux and SCL4 and NuttX, so they can share the same SPI, and we are putting that into the bootloader. But we have to actually cut off pieces of that. OpenSPI is great, but it's also really big. It's tens of kilobytes, just because it's built to support all possible RISC-V SoCs, all possible operating systems, and it also integrates lots of utilities that you can configure away, but you have to actually go modify the OpenSPI code to get rid of things. For example, console, which is not really needed for anything in the end product. But we managed to actually put in NuttX and mass storage support and USB, TTY ACM, and OpenSPI into this flash space, and configuring the DDR and all that in the end. No, that was the quick overview of our NuttX PolarFire ports. So I thank you for listening, and please ask questions. I'm now putting away those slides so that I can see the YouTube channel. Thank you.
Thank you, Yuka. We don't have any questions on YouTube channel yet, so let's wait a little bit. We have one from Ken. Ken, if you want to ask directly, he is asking if did you have to add RISC-V RV64 support on NetX?
No, that was already there. Just the MMU driver and fixes to kernel mode.
Okay. Yeah. I noticed on your diagram, I noticed in the diagrams for the SoC, they're using a U54 core, which is an Open 5 core, kind of a standard. So it sounds like it already has support for the Open core, Open 5 core.
Yeah, I think it was Masayuki, right?
Yeah, actually I added. Yeah, RV64 support I added. Yeah.
Yeah, and there was actually some very nice collaboration there because we had a long list of things that we need to fix to get the kernel mode running. And then on a few days, Ville came to me and told that, hey, we don't need to fix this anymore. Masayuki already did it for us. So we were working on these things at the same time.
That's actually good to know because I'm looking at putting that U54 core from Open 5 in one of my ASICs. This actually probably later this year or early next year. So it's good that it already has NuttX support.
Mm-hmm. Yeah.
I do have a question. How good is the separation of this 4 execution domains for the bootloader, LX4, NuttX, and Linux? I mean, are the DMA controllers, for example, separated, or can one domain do DMAs into another domain or something like that?
They are protected against the DMA transfer.
Okay.
Yes, there are some holes, but again, this is not It's not perfectly separated, I would say, but mostly.
Okay. But the PMP in RISC-V is very close to MPU in ARM. Yeah. Okay.
Yes. It's very close. It has similar restrictions even. So, for example, the alignment of the areas and so on, which make the usage very difficult.
Okay, thanks.
Do you know what is the power usage for the FPGA and both when running and idle?
I don't remember the figures. FPGA is surprisingly low power, but again, I cannot say now out of my head any exact figures. Of course, we are running in drones, and in drones, especially in big drones, the motors eat up so much power that it's sort of insignificant how much the CPU takes. But this SoC is definitely not usable in battery-powered devices. It needs some bigger, or at least it needs some bigger batteries, such as what you can find in drones.
Are we talking about amperes or hundreds of milliamps?
Hundreds of milliamps. So if you are running it, I would say that it runs somewhere around 400 milliamps or something from you. So you can power it from DC USB if you are not doing something extremely heavy.
Mm-hmm. Okay, thank you. Alan, do we have more questions or over YouTube, or should we move to the next presentation?
No, I think we don't have more questions. We have a comment, but no question. By the way, Greg Nutt just entered in our chat. Hello, Greg. Are you listening? Yeah, let's see.
So it's my turn.
Yeah.
Yeah.
It's your turn.
Okay.
I can introduce you, no problem. So next presentation is from Guiding Lee, and he will talk about the RPTAN frameworks and services between multi-CPUs. Thank you for your presentation. And now let's see if we have some questions on the channel.
I like to show the real usage in the board. Hello? Can you see my screen?
Yes.
Yes, we can see.
I like to show some demo.
Super. Please continue.
Yeah. First, let's see the UART message command. Okay. You can see currently we are in an AP shell. 然后 then we use CU. Then we come to the CP shell. We can see your name .a. This is CP. Then we use Control C back to AP. Then we come to audio shell. Okay, you can see this is audio shell, and the arc is the sensor. Then we use Control C back to AP, and we can enter the sensor shell. This is present compared to the uname. But this is the sensor from the header. Okay, this is syslog message. Okay, let's see the syslog message demo. First, we enter to CP. Then back to AP, and the message also come out to AP. That is the syslog message. Also, let's go to the audio. Back to audio, and we can go to sensor. Okay, this is the syslog from sensor. Next, I will show you our message FS. So you can see current AP mounted data is FATFS, and it is a flash. And we create a file called A. Okay, this is AP. Then we come to CP, and we come to first we see the mount, and the date will use our message FS, and this data is corresponding the AP date. So let's see. We can see the A file. Then we delete the A file. Then we back to AP and enter to the date to see. We can't find the A file. That is our message FS. The AP folder, the data folder in AP and the data folder in CP is the same folder. Okay, I will show you other tools called EXEC. We can use RESEC in the AP to operate the CP shell. So you can see the H means which CPU, R means which command. So this command is operated CP shell from the AP called RESEC, and then we can see another audio. So this is execute the audio shell command from AP. PS is the same thing we can PS. This is the same. Both have meter D. Okay, I will show you another command called kvdb. kvdb has a command called setProp and getProp. This is getProp. You can see there's a lot of kvdb value. So let's create a new. You can see this. This is just created. Okay, let's go to the CP and get prop. So we can also get the kvdb value. Okay, my demo is done. Thank you. And if you have questions.
Thank you very much, Gitling. Yeah, this is a very nice project and very nice demonstration of the Netx features. And let's see here in the. Okay, I think we don't have questions yet. Actually, I have some questions about it. For example, for this smartwatch, you are using some ARM microcontroller and the extensor. So I suppose the ESP32. Why Xiaomi or your team decide to use this configuration, two different microcontrollers for this kind of product?
Okay, your question is how to connect it for example, ARC arm and extensor arm, or with 5 ARC.
Yeah, because they are not only asymmetric, but they are completely different architectures, instruction set, and so on.
Yeah, but the same is they both support OpenMP, and my service is based on OpenMP, and it's the same model. And the OpenMP don't depends on the specific CPU arc. I think this can answer your questions.
Yes. Actually, just a second, Michael. Sorry to interrupt you. Actually, my question was also why to use two different kind of. Actually, my question was also why to use. My audio different kind of. Actually, my question was also why to.
Okay, I fixed it. Alan, please continue.
Okay. Yes. It was more why to use two microcontrollers like this, ARM and extensor, in the smartwatch. Why not, for example, 2 arms or 2 extensor? It's about the power consumption. What was the main reason?
So your questions is why use this too much CPU? Am I right?
Yes. For example, for a smartwatch, maybe powerful microcontroller was too much. So I suppose you decide to use 2 CPUs because the power consumption, right?
Yeah. Let me explain. Okay. Let's see this picture.
Okay.
In this picture, this is CP. This is CP, and this is audio. And I think the professional call for the professional thing. And this is audio CPU. And it has some codecs on it, audio codecs or encoder. And this is communication CPU, and is BLE, BT, and Wi-Fi will run on it. And in this CPU, it has the Wi-Fi controller and BT controller. So there are these CPUs.
Okay, I understood the idea. Okay, so that's all from my side. So, Michael?
Yeah, I would like to ask. I'm not very familiar with OpenAMP, but how much of what you presented is actually standard compliant? I mean, something like the RP message file system, is that something that is specified in OpenAMP, or has that been invented by Xiaomi?
Could you repeat the questions?
Yeah, okay.
I didn't understand.
I'm not very familiar with OpenAMP, so my question might be pretty basic, but how much of this stuff did Xiaomi invent, and how much is already specified in the OpenAMP standard? As an example, the remote file system that you were showing, the RP message file system stuff, is that something that is standardized by OpenAMP? So could you also access a remote file system on a Linux host via RP message FS?
Yeah.
Yes.
Yes, we can. Because the Linux has integrated the OpenAMP, and in the Linux we can create a corresponding message FS service. Then we can access the Linux file system.
Okay.
We have already used in the product. You can see this.
Oh, okay. So a standard Linux kernel, a modern Linux kernel already has this RP message file system support included?
No, Linux already integrated the OpenAMP.
Okay.
But because it is the standard usage on the virtual IO, and the OpenAMP already on the Linux kernel, but the RMSFS actually is a command. Actually, is a command calls the CPU, and the Linux should run a service called and the Linux should
Okay, but there is no such service in a standard Linux system. You would have to implement it to make it work. Or Xiaomi has implemented that to make it work. Yeah.
We haven't set up patch to the Linux kernel.
Okay.
But I think we can send a patch later.
Okay. Yeah, thank you. Very good. Nice presentation.
We have a question from YouTube. I am putting the question on the screen. The question is KVDB open source?
Yes. The KVDB we based on the. Let me have a see. I think we will open it.
Sorry for interrupt. About the KVDB issue is about the company issues, so maybe we will talk about it later to the community. Currently, we can't give some certainty answer on it.
Okay, thank you.
Okay, and also for another question, just Alan just mentioned that it's for the Xiaomi Watch Pro, it's got multiple CPU or something like that. Actually, we only have one CPU, but for you can see the AP, CP, DSP, sensor, OTE core. They are both the core on the one CPU. They are not different CPU on it.
Thank you for the clarification. Maju, do we have more questions over YouTube?
No, just one comment. Linux can support remote proc. Open map is for RTO side. That's all.
Maju, thank you. I think it's really interesting to see some of the internals of the smartwatch. And,
yes, the Linux kernel support remote proc, and the OpenMP is open source for the auto side. Yes.
If there are no questions, we will move to the presentation from Dan Goldman regarding safe Rust bindings to NuttX POSIX APIs.
Let's see.
By the way, Dan, thank you for attending our event, our workshop, and we know we are busy, and you had some scheduling for this.
So I'm going to talk about safe Rust bindings for NuttX's POSIX APIs.
We cannot see your slide.
Okay. Is there anything I need to do here? So I have my slides that are being presented.
For some reason, probably you have to start over or share the window.
The slide is not displayed yet. Yeah, maybe you need to stop sharing and sharing again.
Is it sharing now?
No, still no.
Yes.
Let's see what I can do here. All right, is this working?
No.
Not yet.
All right. All right, is it working now?
No.
No.
Yes, it is strange because few days ago during the warm up, it was working fine, right?
Yeah.
Yeah. I think Jitsi has some bugs that need to be fixed to improve the experience.
I will disconnect and come back. Right, come right back.
Yeah. By the way, we have some comments about this question about the KVDB. Mr. Shao Wan from Xiaomi said it should be open source soon. And it is nice because when I search for it, there is a kvdb.io. I suppose it's other different project.
All right, can you see my presentation now?
Yes.
Yes, we can see.
All right, great.
Now
make it full screen. Please also make it full screen on your side. F11 one.
Is that better?
Yes. Thank you.
Okay. Welcome. Okay, so quick about me. I'm new to NuttX. I work on a bunch of things that are in software that are unrelated to NuttX. And many of them are written in Rust. That's kind of how I got into this. I'm a Rust library contributor, and I maintain a Rust crate called NuttX, which I'll talk about a little bit later in this talk. And so Ellen reached out to me and said, like, hey, are you interested in like porting NuttX to NuttX, and do you think it would work? And so I said, sure, I'll try it. And this talk is kind of the result of what happened there. So quick digression. Why would you want to run Rust on NuttX? And so the Rust enables developers to build reliable and efficient software. Early on in Rust, a lot of people expected that the main audience for Rust would be programmers coming from C and C++. And one of the things that was a little surprising was that Rust also attracted a lot of developers coming from high-level languages like Python and Ruby. So Rust really helped open up the systems programming language to new audiences of developers. Rust has this property called memory safety, which means that by default in the language, Rust prevents dangling pointers, use after free, double free, and many other kinds of like pointer bugs at compile time. So they just can't happen at runtime. Rust does have an unsafe keyword, which means that you do have the full power of raw pointers when you really need it. But the really cool thing about the way this works is that Rust is safe by default. And so when you look at a large Rust code base, you know that all the code is written in this sort of safe Rust subset. And you can quickly find the places that are written using unsafe keyword. And so you can pay more attention to those places very quickly. And beyond memory safety, Rust's expressive type system can enforce many kinds of invariants. This enables library authors to describe their own library invariants in the type system to help their own libraries use their APIs correctly. In total, these properties that Rust has helped attract a community of developers and an ecosystem of libraries and tools that collectively emphasize writing correct programs. So as I jumped in, I took a look at like kind of the existing landscape of Rust on NuttX, and there's kind of two big things that I found. One of them is this very detailed walkthrough of using Rust on NuttX from Luke Yuen, who I believe is presented earlier in this meeting. It's a great walkthrough. It's got a lot of great stuff in it. And one of the things that you can see in this presentation is that there is no official support for NuttX in Rust. And so many of the steps in this presentation end up being fairly low level and kind of rough around the edges. But it's actually a really great kind of background for a place to get started. There's also a Rust Hello World in the official NuttX apps tree. You can see this in the PR that I like to here. And so this works great. But one downside here is that it's using Rust C directly rather than using Cargo. And so it's not easy to pull in crate dependencies like Rustix or other crates in the Rust ecosystem. So when I started to dive into this further, one of the big things I see when I look at NuttX is that it has these POSIX style APIs. You can see the NuttX documentation online. It has all these, the file system APIs on the left. It has BSD socket APIs, a screenshot on the right. And beyond that, it has a fairly complete set of POSIX APIs. And it's notable that this is basically the same set of APIs that, for example, the Rust library is built to work on top of. And so it seems like a lot of things in Rust could work really well on top of NuttX. And so I made what in the Rust world would be the next logical step. When you have a large C API, I created this thing called NuttX-sys. And -sys is kind of convention in the Rust world for crates, which are basically just bindings to existing C APIs, FFI bindings to call out to C code. And so what this roughly looks like is for every function in the NuttX C API, there's a Rust extern C, potentially with a CFG to reflect the NetX config net. It's kind of translated into the Rust CFG mechanism for conditional compilation. And then we have the receive function, which corresponds to the C receive function in NetX. We have a file descriptor, a raw pointer, a size of the buffer, a set of flags, and then the return type. NuttX-sys is semi-mechanically derived from NetX's syscall.csv, libc.csv, and math.csv. These are kind of these existing files in the NetX tree that describe NetX's C API in a CSV form, so it's actually in a fairly declarative form. This is the first thing I tried because I didn't really know what was going on in NetX. Since I did that, it also occurred to me that NetX has these header files, has C header files, and so another option would be to run Rust's BindGen tool, which is a tool for generating Rust interfaces from C header files, and just run that over the NetX's header files. I don't actually know if that would be better, but that would be another option to take instead. Another open question here that I'm interested in if anyone has thoughts about this, I'm sort of interested in catching up with people or answering questions about like how should we handle in binding to other languages NetX's many config flags. So NetX has a large set of config flags, which is great for many of NetX users. And these flags change everything from sort of internal implementation details of how NetX works to which API is available to, in some cases, what's the actual API of the APIs. So config variables like config SMP NCPUs actually changes the size of some types. So it's not possible to have a single set of C bindings that sort of describes all NetX configurations. And so one option is to sort of translate the config settings into the Rust bindings so that the Rust bindings are conditional in the same way that NetX is. Another option would be to say we should have a single set of configs that sort of represent a standard set of configurations to make it easy to have a single C API. I don't know which of those is best, but this is kind of some of the issues that I ran into when I first started looking at it. In any case, I have a thing that seems to work reasonably well for some default settings with these bindings generated from the CSV files. So this NuttX-sys library that I built, which with all these just raw bindings to C APIs, could be the start of a port of Rust's libc crate to NuttX. This actually looks very much like what Rust already uses in its libc crate to bind to existing platform libc libraries. This in turn could be part of the foundation for actually an official port of Rust to NuttX, which I think would be a huge step forward in terms of making Rust usable on NuttX. So I also maintain this library called Rustix, which is a Rust library that specializes in providing safe wrappers around POSIX APIs. So POSIX is an API that's all written it's written to be used in C, and so it has a lot of APIs that use raw pointers, raw file descriptors, and function exit statuses, and translate those into idiomatic and safe Rust APIs. Rustix has multiple backends. It's a libc backend to talk to the platform libc on platforms where that's the best thing to use. On Linux, it also has the ability to talk directly to Linux system calls, so it can just bypass libc entirely. And the architecture is such that perhaps it could use other backends in the future. A quick example of what Rustix looked like. I showed that the receive function earlier in that presentation, which is sort of like the raw C, binding to the raw C library. And so with Rustix, you could write a very simple receive function that just takes the socket object, which is some high-level socket type in Rust. It takes a buffer, which would be some kind of memory slice type in Rust. And this receive flags, a flag type that's dedicated to be flags, so you can guarantee that you're passing the right type of flags into this function. In Rust, the alternative to using something like this, if you want to call receive directly, is to do a fair amount of ceremony. This example I have here, it requires using an unsafe block because you're calling it to a C library, and by default, Rust doesn't know anything about what C code is going to do, so it considers it to be unsafe. You have to get the raw file descriptor out of the socket, be able to pass that directly. You potentially have to cast the raw file descriptor to another type because different platforms for C functions use different types. You have to get the raw pointer out of the buffer and cast that. You have to get the length out of the buffer and eventually cast that because different platforms for C functions take different lengths. And you have to pass this message peak flag, which is his type int, so there's no checking to see that you pass the right flag to the right function. The return value of the receive function is potentially -1 if it's an error, in which case you have to go and check the error no, which Rust has an API to get error no, but error no is kind of this awkward, like separate out-of-band communication thing to get the error message, and otherwise you can get a successful return. And so Rustix is a library that basically like bundles up all this kind of code and puts it in a very simple API that can typically be inlined to get the same result in your generated code, but it's much easier and much safer to use as a programmer. And so with this, I took Rustix and I took NuttX and added NuttX as a new backend to Rustix in an experimental branch that I have here. Using a separate backend within Rustix is actually kind of an interesting thing. Like it was the easiest thing to do right now to get started. But in the future, if there's an official libc port, Rust libc create port to NuttX, this extra backend will become necessary because then Rustix could just use its libc backend to talk directly to these APIs. So this port is highly experimental. It's not really usable yet, but it did kind of get far enough to prove the concept of a lot of these things being possible. And so as I was porting these things, I kind of ran into the kind of issues that I ran into were things like in NuttX, there's no fdatasync function. Fdatasync is simply defined with a preprocessor macro to be equivalent to fsync. And so that's fine. As a platform, you can do that. But C preprocessor macros aren't available to Rust. And so Rust needs to have extra bindings to deal with those things, which we can do. It just takes a small amount of extra porting work. NuttX's struct pool FD has some extra interesting fields that other platforms don't have. And so in Rust, by default, you're not allowed to ignore struct fields. You have to do extra work to opt out of struct fields that you're ignoring. And so this turned out to be a thing we had to port a little bit to. NuttX's UIDT and GIDT are 16-bit instead of 32-bit as they are on many other platforms. And so this is kind of the flavor of the kind of things we ran into when doing the ports. And all these issues are entirely manageable. They're very easy to work with. And it very much feels like if these are the biggest kinds of problems we have while doing the port, then making a full port that actually works properly seems like it's very manageable, very doable, which is very exciting. The hardest part of N2 in all this work is the build system. Trying to work with the NuttX apps and the makefile there, trying to get Rust to work in a form that looks like the makefile is expecting it to look, was quite difficult. And so that's the part that I struggle with. And so if people are interested in working on helping incorporate Rust code and helping build Rust code for NuttX, I'd be interested in seeing what people are interested in. So in conclusion, there's this NuttX sys library that I built, which could be usable on its own, but it could also be a starting point for porting Rustix, or also for a proper Rust libc crate port, which could also be the starting point for a proper Rust target for NuttX. And from what I've seen so far, NuttX's POSIX API looks like it's entirely suitable for porting Rust to Rust standard library, as well as Rustix. And that is my presentation. Are there any questions?
Okay, let's see in the chat. No question yet, so let's open to people here. If someone here want to ask something to Dan. Okay. Alan, do you have some question about Rusty that you have interest to know how to use it on NuttX?
No, and I will try to stay silent now because my daughter is running around. Sorry.
Okay. So then, let's see if other people will ask here, and we are very interested to have Rust not only for applications on NuttX, but eventually to do something like people are doing on Linux, to be able to create some drivers and so on. And by the way, I want to hear from you what should be the next steps for NuttX to work on this direction, because you have more experience with Rust and POSIX and RTOS and even normal OS, ordinary OS. Please share thinkings about it.
So for drivers, where you're going to be, actually back up. I don't actually have any experience in RTOSs or working in kernels. I'm mostly user space. For drivers, I would expect the biggest step is to just take the beginning that Luke Yuen had in his tutorial, and take the Rust Hello World that's kind of in the NuttX app trees. And it seems like the biggest challenge is really the build system. Ultimately, you want to write APIs. Having a build system that can build Rust code and integrate it into the main NuttX build, it seems like the biggest step. So someone familiar with the build system, person to jump in there. The second thing for drivers that occurs to me is that within the kernel, there's probably a kernel API, I imagine, of the way that the driver interacts with the rest of the kernel. So the second step would be to build a set of Rust bindings for that API, which would be the next obvious step. I haven't looked at that API, so I don't know what it looks like and know what that entails. But that would be the next step to look at. For applications, I think what I've concluded is that the next step to really do this properly would be to start working on an official Rust target. And so that's kind of where after I started porting RustX to this, I kind of started realizing this, that to really make this usable, we just port the Rust layers to get things like the Rust standard library, which also means you could port in large modes like the Rust ecosystem could be ported to this system as well. And so it feels like NuttX sys, assuming that this approach of using the CSV files is the right approach, it feels like that could be something that could be contributed upstream to the Rust libc crates. And then there's a process in Rust for proposing a new target, and that seems like the next step is to sort of go through that process of making NuttX officially supported in Rust. Rust has different tiers of target support, so I imagine that NuttX would start at tier 3, sort of the lowest tier, which means that it's in the tree, but not necessarily guaranteed by the Rust project to build. It would sort of be community maintained at first. But even having it be an official target would be a huge step up, where we could basically say, get these tools, as long as you use the right versions of things, then you get to the reasonably normal Rust developing experience out of the box. So for user space, I would say, let's start working towards a Rust targets. And I'd be happy to talk with people about roughly what that looks like, what the process is like. And for the kernel space, it's let's figure out the build system and let's figure out the bindings to the kernel APIs.
Okay, understood the idea. And yes, I think as we explained, the most difficult point was to integrate the cargo with the make files and use it on NuttX, right?
Mm-hmm. That's for the work that I did, and I can. It's kind of representative of writing application code in Rust for NuttX. That this is something that pretty much any application developer will hit, because Rust has a wide variety of crates. That's actually one of the strengths of Rust, is this ecosystem of crates you can use, and be able to pull those in automatically without having to do extra work to manually vendor dependencies or deal with dependencies directly. that's a huge thing we want to have for anyone developing in this kind of system.
Okay, thank you very much for this deep explanation about the next steps. And before we move, I want to ask everybody here again to turn on the camera. Let's take a picture for put later the shot. Okay, thank you, Rob. Thank you, Ken. Masayuki still here. Greg, Michael, Maju, Xiang, and Mark. Oh, great. Philip Neves, are you here? Hello, Philip. Okay, I don't know if he's still around, so let's take that picture. Yeah, who wants to speak? Sorry, I didn't.
It was my hand that activated. Sorry.
Oh, no problem. Maybe your daughter wants to speak.
No, she moved to her room.
Okay.
I can open the microphone again. Sorry for that.
No problem. Okay, very nice, guys. Thank you. And Masayuki, thank you for keeping at this time again. So I suppose it's too late in your side at this moment, right? Maybe 2 a.m. Yeah, crazy. Thank you, guys. Alin, I think now we can ask the next presentation, right?
Yes, I think that it is time. We have 2 more presentations for today. The first one is prepared by Rob. He will talk about Lua and laser gaming in NuttX with NuttX. So let's see.
Okay, just on detail, I see Xiang here. So Xiang, thank you very much, you and all the guys from Xiaomi, and thank you for the gift to the event. So we really appreciate it. Thank you very much. Your microphone is muted. Okay, thank you. Okay, thank you. So, Rob, as Ali said.
Okay, how's my audio?
It is fine. We cannot see your slide.
You hear me okay?
It's great. It's great.
Yes, we cannot see your
cool.
slide.
Okay, let's share this. Waiting for YouTube to catch up. Okay, I guess that's working. Yeah, so I am going to talk about using NuttX and Lua together to greatly improve a product of mine related to laser gaming. My name is Rob Voisey. I'm an embedded software developer. I have been for many, many years. And in 2008, I started my own company, Fen Consultants, and my colleagues and I have been developing products mostly in the embedded space, right across embedded, from medical instruments to laser games. So let's briefly touch on what laser tag actually is. You haven't necessarily heard of it before. The first laser tag system was actually a military training apparatus developed in 1978, which allowed soldiers to train without live ammunition. Their weapons would fire blanks, and apparatus would be fitted onto the gun rails that fired lasers, and then they could measure whether they hit targets with them. And this has grown and grown and grown. It's on battleships and aeroplanes and everything you can think of. You may have even seen it on Top Gear. And that's, well, not that exact system, but the
The latest version of that system is still used by militaries all around the world. But I don't work on military stuff. So the first entertainment version of laser tag came out in 1984, a game called Photon. It was designed to be a sport. Every Photon arena that opened was identical. The rules were always the same. And it proved very popular. You could join teams, go into the arena, shoot each other with laser guns, get a score. It was great fun. And as soon as that came out, it really took off. There have been dozens of laser tag systems since then, and many are still in use today. Most high streets have some kind of laser tag game, although more commonly they're played by kids for their birthday parties and things now, less of a sport these days. So the product I'm talking about is called Genesis, and it has some history. Developed my first laser tag game in 1993, as you can tell from the photo. Then I went on to develop a second system called Q2000 in 1997, and I guess that's my most successful project because it's still in use today. It's been through several revisions since then. There are about 50 sites running it around the world. Then in 2008, another new system, a bit of a departure from the earlier microcontroller-based stuff. This new system ran Linux on the player packs on TI-DM355 processors, had a lot more graphics and media. However, it was much more expensive to manufacture. It was around the time that TI support started to go down the drain, and the DM355 libraries never quite delivered on all the functionality we'd hoped for. So in 2017, we made a clean slate and developed a new version based on STM32. So why NuttX? I've been using NuttX since 2014. It's my go-to RTOS of choice. I've used it in a wide range of products. I've used it with Lua in a wide range of products, especially medical, but those clients don't like me talking about it. So that's why we're talking about laser tag today. I like the POSIX familiarity, really good device support, very compact. I've run this on every size of microcontroller, from tiny to pretty massive. And as we all know, it's in very active development. So there's great community support. There's always something new coming along. It also has excellent STM32 support, which was the microcontroller of choice for Genesis, something we're slightly regretting in the current market. So NuttX was perfect. So now Lua, probably by now most of you know what Lua is if you didn't before this workshop. So just very quickly, became very well known when World of Warcraft incorporated it into their NPCs and their other in-world objects. So all the scripted objects in Warcraft run Lua scripts to provide some semblance of intelligence. It's pretty fast. It's pretty small. It's got an easily readable syntax, not necessarily a syntax all developers enjoy, but people who aren't developers are able to read it and very quickly get the hang of it. It's kind of object-oriented. We'll look at a kind of example of that later. There's an embedded variant eLua, which targets microcontrollers very, very easily. And it's very easy to integrate with host code, and we'll look at how Genesis does that shortly. So NuttX and Lua were match made in heaven. When I did this project, they weren't officially joined. So I ported the code in, which was probably all of 10 minutes work. Now you don't even need to do that. You just check Lua in the menu config. And at some point, I'll update my project to use that. So why add script into my laser game? So the laser games that went before were all hard-coded. There were no scripts. They were implemented in C primarily. So to provide a wide range of game possibilities, because you don't want customers to get bored, we had to provide a very large number of options to cover all the bases. Well, for one thing, we certainly don't cover everything imaginable. And for another, that means, I think in Q2000, there were maybe 50 or 60 game options, which is way too complicated for people to set up and create new games. By moving to a scripted system, the games could be, the option presented could be completely targeted. So a particular game implemented in the script might have 4 or 5 different options, much easier for the sites to understand and for the players to understand. Also, it's much easier to pull in customized media, audio, video, LED effects, that kind of thing. Games themselves can be much more flexible. When somebody thinks up a kind of game to play that we never imagined, then they can implement that in the script. And whereas before any changes to the games required a firmware update, now we just have to distribute packages of scripts and assets, which is super easy, and it means customers as in the centers can build their own games as well if they want. We'll look at the components that make up Genesis. First of all, we've got a phaser, which everybody calls a gun, and for marketing reasons we don't. The phaser has a barrel transmitter, which is the very targeted narrow beam. It's actually infrared. The laser is just for show. It's also got targets on the side, so you can be shot on a target. Also, depending on the game options, the gun can fire out of the targets. There's a speaker for sound effects. There's polyphonic. There's a graphic display you can't see in the photos, 3.5-inch LCD TFT on the back. As previously mentioned, there's the laser just for show that fires out of the front. There's a vibrator that makes it enjoyable to get shot. And the whole thing's battery powered. The battery is actually contained within the phaser. And then the other part that the player runs around with is the body armor. Of course, it doesn't armor you against anything. It has targets on the front and rear, so you can be shot or it can shoot out of those targets. They've also got quite a lot of LEDs on for doing particular effects, which are completely programmable within the scripts. There's also shoulder targets, which didn't exist when we took this photo, making it harder to hide from being shot. And there are shoulder speakers so that you can get some directionality to some audible directionality of where the direction you're being shot from. Then there's the arena system. So these are components that go into the play area. There are things that take on different roles depending on what the scripted game is set up to do. Headquarters, energizers, power-up points. For example, you could play a capture the flag kind of a game where the headquarters would come into play. The power-up points could give you special powers or special bonuses. There were also video displays in the arena, which can be used for any purpose the game script devises. At least some of them will be used to show real-time scoring information usually. Music and sound effects are played into the arena, usually at huge volume. And the lighting is also dynamic. The DMX lighting in the arena is controlled by the arena system, so everything feels quite immersive and interactive. Then the briefing system is, this is where you go before the game to learn how to play the game. And because the games are scripted, one of the assets that comes with each game is the brief for that game, because they could be quite different. So across a number of screens, which are all synchronized, we play briefing video and audio. There's also synchronized lighting and effects there as well. And finally, there's the game server. The server runs the game. It provides the user interface to the center staff. to schedule their games. It prints score sheets out at the end of the game, has an electronic point of sale and a bookings diary, membership database, admin, all the things that you would expect. So that site server is a network Linux box with one or more web terminals running the user interface. So typically you'd have terminals in the cafe, maybe one in the arena, maybe one in the briefing room, so the staff can easily interact with the server. The game engine on the server is written in C, and that has Lua embedded. So that's the server side of the scripting of the game. There's also a cloud server. All that does is remove your money from you. It validates your license, does the accounting, but it also has a database of games so that we can roll out new game scripts and centers can pick them up if they want. Then the phaser and the armor, which is the main thing I'm going to concentrate on, they run on STM32. There's an F429 in the phaser and an F1 something, 103 maybe in the targets. The F4 is running Lua. The targets are fairly... the targets connect to the F4 over an RS485 network that runs through the pack. And there's an ESP8266 that provides the Wi-Fi. When we started this project, ESP32 was around, but the SDK was still a bit flaky. Now I would put it on ESP32 for sure. And then in the arena, each of those arena devices runs on a Raspberry Pi with our own synchronized media players, so you can split video across multiple screens and it's all synced up. The targets in the arena are actually the same physical hardware as the targets on the player pack, with STM32s in them. They connect over RS485 to the Raspberry Pi. And then those units are all networked together, usually wired. They could be Wi-Fi networked, but it gives your customers a lot of power to block your site. The scripts running on the server are responsible for customizing the game options that the center staff see when they choose the game, for deploying all the necessary assets for the game that's been selected to the player packs. Those assets are cached. There's an SD card on the gun board. But if for a particular game a pack doesn't have all the assets, then it will get synced up when the game is chosen. Then it runs the game logic as the game proceeds, controls the briefing system, all of the elements in the arena, and also provides the score and the completely customized score sheet. So within Lua, there's an API to render a score sheet that gets printed out with a laser printer at the end of the game. The player script runs on the F4 on the gun, and that provides the game logic for each individual player. It handles communication, which can be direct between players or with the server. For example, if you've just been shot, it means you've received an IR code, which has the ID of the player that shot you. You can then transmit over Wi-Fi directly back to that player saying, "Well done, you shot me," and their pack can do something, player fanfare or whatever. It also renders the script renders the LCD user interface, which is mostly a mix of MJPEG animations and text. It can play audio, so there's 4 independent audio channels. We only use 3 right now, 1 in the gun, 2 on the shoulders. And they're all up to 4-channel polyphonic, and because of that, we're WAV file trying to run too many MP3 decoders. And they handle communication with the player targets. Looking at the hardware, so this is the phaser hardware. That's the STM32, which does almost all the work. There's the ESP, which is on a separate module, so we can easily change that to an ESP32 or Bluetooth or something else that we might want. One thing we may put on there in future is an ultra-wideband location system for tracking players around the arena. 4-channel audio with amplifiers. That's the connector that goes off to the TFT on the back of the gun. the drivers for the LEDs. There are 6 IR pairs around the pack for sending and receiving infrared, and a connector that goes off to the highly focused barrel transmitter, which is much higher powered than the others. And then there's a whole bunch of RGB LEDs for looking pretty. That's the hardware for the targets. As I said, that doesn't do anything as interesting. We are running NuttX on that F1, but we don't run Lua on there. Lua controls the things that this board does over the RS485 connection. So looking at the integration of Lua into the firmware. So first of all, I added eLua to the NuttX apps trees, the thing that you no longer need to do yourself. I run the Lua engine on a thread, and I run a single Lua context on that thread, meaning that we're only executing one script at a time. But that's not a limitation of the platform. It's just that's all we need for this application. We expose an API called libglt, Genesis Laser Tag, to the script, so that the scripts have access to all the features of the hardware. All communication in and out of this thread is through message queues, and the thread is blocked while the script is running. But there is a hook, a feature of Lua whereby periodically during execution, and you can tune what that period is, it will call into a callback and give you the opportunity to time slice or do something else. In our case, we only use it to pick up on when we've aborted a script, so we can kill it through a horrible long jump. So here's some code. This is code that runs on the F4 on the gun to start a new script. It's a fragment. I've deleted most of the error checking, I promise, just to get it to fit on the screen conveniently. So each Lua instance has a state. It's effectively a pointer to a context. And Lua our new state creates a new one of those to which we keep a reference, and that gets used all around the Lua interface. Then we open the standard libraries. So this is the set of libraries that are common in Lua. They provide string handling, math functions, useful things. You usually want them, but you can customize that. Then we load our actual script, which by this point is a file on our SD card because some asset deployment has gone on before this happens. And then we do our first execution of the script. In this case, we're calling the global section. So you can kind of think of that as the global section in BASIC or Python. It's the stuff above any functions. And typically it's used to declare and initialize any global variables. Sets up the global environment. And then finally, we install the hook that I mentioned before. So in this case, my function script hook will get called every 100 Lua instructions. Not the best way to tune this, but it's what it is. So once you get a feel for how quickly your system's running, you can tweak this. We don't need that hook to run terribly often because all we're looking for in our case is a flag to abort the script. So next we want to build our API. Having created our context, we want to associate some C functions to be accessible from Lua. I've got a table. This is a fragment of the table where we have the Lua function name, so GLT close first of all, and then the C function that corresponds with that. And we'll have a look at what that looks like in a minute. And the Lua register function associates those together so that when GLT close is called from Lua, the C function will execute. I also want some API constants. Those are implemented in our case with as Lua globals. So again, I have a table. I've got a Lua label on the left-hand side, and on the right-hand side, the value to associate with it. So these right-hand values are all constants or defines. Lua is the interface into Lua is stack. But to define these global constants in, first we push the value onto the stack of the Lua instance that we're working with. And then we call Lua set global with the name. And now there's a global variable called IR barrel. It's not quite ideal because it isn't a const, but if anyone knows a way of doing that, tell me. And this is an example of one of the C functions that is bound to an API call. So the Lua call is GLT gets a configuration field, and it takes one argument, which is field. It's an integer, but usually you would pass one of these constants that's been defined previously, and it returns the value of that field. So the C function itself receives a pointer to the Lua context that is executing time, and when it enters, any argument passed into the function will have been pushed onto the stack. Rather than popping them off the stack here, we use some helper functions that let us access them by index. So this example, Lua L check integer, which takes the context, and then parameter number 1 will check whether the number 1 parameter is an integer, and if it is, we'll return that value. Again, my error handling's been removed. And we would just repeat this for any additional arguments, and there are similar ones for check string and check boolean and all the basic types that are in Lua. Then we can do some processing. This particular function is super simple. And if we want to return something, we push the return values onto the stack, and there can be multiple. So Lua can have multiple returns, multiple return values. So the C function returns the number of values that the Lua function will receive. In this case, 1. It would be 0 if we return nothing. And Lua push number pushes that value, which is obtained from this C function, onto the stack, and it's received in the script. So yeah, really simple. The last part of the API are event handlers. So Genesis is completely event-driven. In most cases, events are asynchronous, and they arrive on the message queue of our script thread. And this is on the left is a fragment of message dequeuer, where it's identified that there's a IO trigger event, which is a trigger change event. And that calls into a C function of our own creation over here, script call. It's just a general purpose way of calling functions within the Lua script. So it passes the name of the function to call and the details of any arguments. The first thing we do is look up the function. Again, there'll be some error handling here, not exist. And then we iterate over all of the arguments and push those onto the stack, just like before. Oops, try not to scroll something, not text. And then finally, we call the function using Lua pcall, same as we use to run the global context. This is wrapped up in a set jump for the reason that we've discussed before, that during the so this will block until it's completed, but our callback will be getting callback every 100 instructions, and if we've tried to abort the script for which there's an API call, then a long jump will happen that will take us back here and get us out of it. That's probably the dirtiest part of the whole thing. I'll very quickly scan through the API that's implemented. So these are the functions. There are some networking functions to get network status and to transmit network data to another station, which could be a player or it could be the server. You can also transmit and request tracking, which means you'll get a an event showing you whether that was successful. There are some timers. There's configuration, which gets and sets values that get saved to flash. Those are mostly to do with configuring the pack itself. There are various things that the site can set up. There's the maximum allowed volume, that sort of thing. You can load files. There is some script handling. So GLT close is the thing that does the horrible long jump. You can sleep a script, but because that will block the thread, it's not a thing you would normally want to do. You've got access to the NuttX console for debugging. You can also check the version. Then we've got some audio calls for playing sound clips. You can play them on any combination of the 4 available output channels. Can stack up to 4 of those if you want. Then we've got control of all the LEDs, of which there are dozens and dozens on the pack. LED play plays an LED pattern, which does pretty things that normally map to events that happen within the game. So if your particular game, if you're playing Capture the Flag and you currently have the flag, then maybe your front pack is flashing in the color of the team's flag that you've just captured. There's also numerals on the front pack that can be used to do a countdown or show you what your player ID is. It varies from game to game. You can transmit an IR packet through any combination of the front barrel and the sides. If you fire out of the sides, the thing works like a grenade and will hit anybody around you. There's a whole bunch of functions for drawing on the LCD, including text plotting and playing MJPEG animations. And then you can access the I/O channel. There's a trigger. There's a couple of different buttons. There's the laser and the vibrator. And then the events that are available. EV run is called once the script is stood up. So it's initialized, it's run the global context, and it's ready to go. IO trigger and IO button are called when the state of one of those things has changed. There's your timer event. Data received over the network and also confirmation of earlier transmits. Some of the data you send, so all of the data in Genesis right now is sent over UDP for efficiency. But some of that data might be important and it's going over Wi-Fi. So you may want to do something if it fails to get delivered, such as resend it. And then there's an event for when you receive IR, which normally means you've been shot, but it means something else. So we'll take a look at an example game script in an editor. Don't judge me on my white background editor. So this is a simple super game. We won't read through every line of this thing. I'll just skip through it. It's an example. It's not a game you'd really play with customers. It's more for game developers to look at. This particular game has 4 different states. So these are the scripts for the player pack, not for the server. And the player pack can be in 4 different states: offline, ready, online, and done. We'll look at those in turn. And each of those are implemented in a different Lua file. Do file just pulls in that file as if it were typed into that position in the code. So we've only had to run one script to pull in all of those. The game rules will get filled in later by the networking. They're things like the number of shots or number of lives that you have available. Actually, is my screen sharing right now? Oh, it is, yeah, okay. It kept blacking out on my laptop. Is it okay for everyone else?
Yes, it's fine.
Okay, it's just my laptop. Yeah, that's game rules. Yeah. Okay. So event handlers. So these are the handlers for the events that we just looked at, the ones that we're interested in. And these, most of these call a handler in the particular state that the game is currently in. So that'll make more sense when we look at how I've implemented this. So let's start with the offline class. This is waiting for a player to join the game. So typically you might have 40 of these packs sat in a rack before the game. You might only have 10 players. So in this case, the player will be asked to pull the trigger to join the game, but the pack will be offline until they've done that thing. And then the packs that are never joined to the game will just quietly go to sleep once the game has started. So we start by instantiating effectively a base class, which has empty versions of all the event handlers. So we only have to implement or override the ones that we actually care about. And in this case, we override EV trigger and NetRx. But I won't bother looking into the code in this particular state. When you pull the trigger, it will take you on to the next state. This is ready. It's waiting for the game to start. So the player is joined the game, but nothing started yet, so it won't let them start shooting. When we enter this state, we'll clear the screen, turn on the backlight. We will check whether we've got game rules, and which normally would happen instantaneously, they're received from the network. And if we've got them, we print something about the game title on the screen.
Robbie, just a moment, Ali, we are not seeing anything on YouTube.
Yeah, that's what I was talking about before.
Yeah. It's coming.
Yeah, for me, it keeps blinking on and off.
It's blinking.
I don't know if that's let's move this text editor.
Yeah, it's only on YouTube. Now seems like it is stable again.
Yeah, I see here, and it's back. It's okay right now.
It's okay now. Maybe some issues.
I'll keep going, and I'll keep an eye on it. There's not too much more to look at.
There's also a request to increase the font size, looks like.
Yeah, that's a pain in TextPad. Bear with me. This is the increased font size, by the way, but not enough, obviously. Okay, let's try that.
Yeah.
Of course,
better now.
All my other files will still be in the wrong size, I think. Oh no, it's done it for all of them. Okay, so we could look at a network data received event implementation here. So we're at this phase, we're only interested in receiving messages from the server, so we'll ignore anything that the guns send. If that message is the game rules message, then we will update our game rules appropriately and redraw the screen, and so on and so forth. maybe we'll just finish up looking at this code with the code that runs when the game's actually in progress. So we could look at, say, pulling the trigger. So as soon as the trigger is pulled, this will get this event handler will get called. We'll immediately turn on the laser for 10 milliseconds. Actually, that will be 100 milliseconds because it is. And then we will transmit over the infrared our gun ID out of the barrel, and we'll repeat it twice because infrared transmission is unreliable. And so that's the infrared shot that will hopefully hit another player. Then we'll reduce our ammunition, and if we've run out of ammunition, we'll lose a life, and then we'll get a full set of ammunition again. Next, we'll inform the what was that? And if we've lost a life, then we'll inform the server of that by sending a message that we've been hit by a particular player. Finally, we'll refresh the UI to show how much ammo we've still got left. So you get the feeling for how you can use the fairly simple API to build up game logic and actually produce quite complex strategic games if you want to. I would have liked to have given you a demo, but I've only got one Genesis pack here and no server. So the best of a demo that I can give you is to show the startup script. It's all of a 2-second demo, literally. This is a script that's run by the firmware when the firmware is finished loading. And it's pretty much to just look nice and show that the gun is charged up and working. What it will do is output to the console the version of this script. It will get our gun ID. It will clear the screen. It will print the Genesis logo onto the screen and print the firmware version on the screen. It will play a pretty LED animation on all the targets. It will put our gun ID, which is one of the saved configs, onto the numerals on the front pack. And then it will play the audio file, welcome.wav, out of all of the speakers. And they're quite loud. Then it will wait for 4 seconds, turn off the backlight, turn off all of the LEDs, and exit. And I can show you it doing that if I bring my camera up on screen. I may need to turn it off on the, I need to turn it off on the conference first. Oops. There we go. Okay, can you see that camera? Yeah, it looks like I see it on YouTube.
Yeah, I can see your camera looking your office.
Okay. So this is, well, it's a Genesis pack in Q2000 mechanics because it's old. Bear with me.
Mm-hmm.
So this will be over very quickly.
Okay.
So it's displayed the logo on the back, and my camera might slightly struggle with the LEDs. Let's try it again. Well, yeah, they're a bit overexposed, but I can't help that. But at least I've shown that a script does actually run on the gun. Yeah. So, unless there are any questions, then I think that's it for me.
Okay, very nice presentation. Thank you, Rob.
My pleasure.
And
we have one question from YouTube. Does it blink? Can you place bang on Alt plus or whatever is the front enlarge?
It was the Rob comment about the blinking of the screen. He during the code presentation.
There's a question: is flashware an issue in the game sites? Is that what you meant? Oh no. Okay. Yeah. No. There's a question before. Does it?
No,
oh yeah. Okay.
One.
I see. I got it. Okay. So yeah. So flashware isn't an issue because the configuration that gets written to flash happens. The writes happen very rarely. They're mostly to do with workshop data and information, and we've got quite a. So we. I just remember how we do it. I think we've got quite a large block of flash, and we don't need to erase it very often. We just walk through it. It's not an issue. Most of the data that gets written is written to SD card. That's all the game assets and things. For one thing, the SD cards have, a very large number of write cycles, and for the other, they're just in a card frame on the bottom of the gun board, so they are serviceable parts.
For the audio, did you end up using the NuttX audio subsystem or something else?
I did not, and I would have liked to. I'm not sure what state it was in 2017. This is for audio channels. I've at the time thought it probably wasn't up to it, so I just rolled my own code for doing that. But it's a thing that I would revisit. So the status of this project is it was finished at the end of 2019, and before beta testing happened, COVID happened, and now we can't buy any of the parts. So I haven't touched this thing for a couple of years, but at some point we'll be able to buy STM32s and Raspberry Pis and things, and then I'll revisit it. And one of the things I'll probably have to do is to bring NuttX forward from wherever it was in 2019 to something more recent, and I'll definitely revisit things like the audio stack.
Yeah, that might be 2024 or something from what my understanding.
It might be. Yeah, I have used more. So I did some other NuttX projects during lockdown. So I have used more recent ones, but not multimedia things. So I'm not totally up to date on all of it.
Yeah, we have some questions in the chat. Why not laser but infrared?
So yeah, okay. There have been laser tag systems that use the lasers. Most of the military ones do, and they're quite high-powered lasers, and they have to wear eye protection. Some of the consumer ones oops, sorry, wrong button. Some of the consumer ones also do, but they're extremely difficult to play because laser beams by their nature are extremely coherent. So by the time you hit the player, if you haven't hit them directly on something that's capable of receiving that signal, then it doesn't register a hit. Whereas as tight as it is, the infrared beam is shaped more like a shotgun, so it makes it more press has been tried. There's one system that I think used lasers and had fiber optics all over the vest. I mean, kudos for trying that, but I think the thing was just unmanufacturable and wasn't around for very long. So yeah, that's the reason. But you have to have the laser for show because it's called laser tag.
Yeah.
Okay.
Okay. I think let's see. We have order from Loop.
Yeah. So STM32 knockoffs. Oh no, he's actually talking about RISC-V. Okay, he's not talking about the knockoffs. Yeah, there are options. So there are Chinese STM32s. We've bought some. We haven't glued them down to a board yet to look at. I'm highly dubious, even assuming that they're legal. But yeah, there is some pin compatible stuff around with RISC-V, and we haven't looked at that yet. But this particular client is probably just about getting frustrated enough that we will start looking at those other options. If it delivers in 52 weeks, as far as I can tell, it's a continuous 52 weeks that always moves.
Okay, I think we are done, right? So
okay.
Thank you, Rob. Very nice presentation, and
thank you for inviting me.
You're welcome. And the next presentation is from Michael Young. In Portuguese, I will say Jung, because
it's Michael Jung. You can just call me Michael.
Okay, Mike. So the next presentation is from Mike. He'll talk about the Twisted M, right?
Right.
Security for. Are you using it for smart card, for credit card readers? What the main idea of this?
Credit card readers are my history, basically. That's what I did before. This is more for secure IoT applications. But yeah, let's see. Perhaps I will do smart, credit card readers again in the future because it's also usable for this kind of application, of course.
You can try to share now the screen, please.
Yes. I hope.
Not yet. Okay. Now it's okay.
Okay. And let's see if you can hear the audio.
Let's see.
Guys, my name is. You can call me Mike. I do have some professional experience with embedded systems and applied cryptography. And coming from Linux and looking for something more lightweight, I learned about NuttX and got fascinated by it sometime in 2017. And I've been playing around with it in my spare time ever since. Earlier this year, I decided to start my own business, planning to support my customers in the development of secure IoT systems using Apache NuttX and Trusted FirmwareM as two central building blocks. And today I want to share what I have learned so far from making these two play nicely together. Please be aware that I simplified on some technical details to hopefully make it easier to follow along. Now, as you probably have guessed, the motivation for integrating Apache NuttX and Trusted FirmwareM is to design better security into IoT devices. But what is IoT security? On a very abstract level, we might say that it is about establishing trust in a thing that it does what it is intended to do over its entire lifetime while operating in a non-trustworthy environment. Now, of course, we are all developing things that do what they were intended to do. But in this case, we are not talking about malfunctions or implementation bugs, but about an attacker trying to take unauthorized control over a thing. IoT security is all about establishing and maintaining trust that such potential attacks will not be successful. When talking about attacks, one has to distinguish between physical and logical attacks. For physical attack prevention, typically some form of protective housing is part of the thing, creating a security perimeter. If we think about an automated teller machine, the strong box that protects the cache would be that perimeter. In addition to making it hard to enter the security perimeter, many things integrate facilities that can detect unauthorized intrusion and will cause some emergency reaction. ATMs, for example, are occasionally equipped with a color cartridge which devaluates the banknotes by spraying them on intrusion detection. Naturally, physical security is not a topic for today, as it is mainly not a software topic. Things are logically attacked, on the other hand, via their external interfaces that cross the security perimeter without physical intrusion. This could be a remote attack via the internet, or it could be a local one via some of the device's external ports. It is known that ATMs, for example, have been caused to release banknotes by plugging USB memory sticks that have been prepared with some special auto-start files. Logical attacks exploit security design weaknesses or implementation bugs. This is where Trusted FirmwareM can help. Trusted FirmwareM is a reference implementation of the Platform Security Architecture, PSA, which has been created by an industry consortium led by ARM. Let's have a look at PSA. The Platform Security Architecture is defined in a set of specifications. One of those describes the platform security model. It includes 10 so-called security goals, which are common to most IoT systems. Let's briefly cover those 10 goals. Unique identification. To interact with a particular device, a unique identity should be assigned to the device, and this identity should be attestable. This identity facilitates trusted interaction with the device, for example, exchanging data and managing the device. Security lifecycle. Devices should support a security lifecycle that depends upon software versions, runtime status, hardware configuration, status of debug ports, and the product lifecycle phase. Each security state of the security lifecycle should be attestable and may impact access to the device. Attestation. Attestation is the evidence of the device's properties, including the identity and lifecycle security state of the device. The device identification and attestation data should be part of a device verification process using a trusted third party. Secure boot. To ensure only authorized software can be executed on a device, secure boot and secure loading processes are required. Unauthorized boot code should be detected and prevented. Secure update. Secure updates are required in order to provide security or feature updates to the device. Only authentic and legitimate firmware should be updated on the device. Authentication at the time of download may be performed. However, the execution of the update must be authorized via secure boot. Anti-rollback. Preventing rollback to previous software versions is essential to ensure that previous versions of the code can't be reinstated, as this might reinstate security vulnerabilities. Isolation. Isolation aims to prevent one service from compromising other services. This is done by isolating trusted services from one another, from less trusted services, and from untrusted services. Interaction. Devices should support interaction over isolation boundaries to enable the isolated services to be functional. The interfaces must not allow the system to be compromised. It may be required to keep the data confidential. Interaction should be considered both within the device and between the device and the outside world. Secure storage. To prevent private data from being cloned or revealed outside the trusted service or device, it must be uniquely bound to them. Confidentiality and integrity of private data is typically achieved using keys which themselves need to be bound to the device and service. Cryptographic operations and trusted services. A minimum set of trusted services and cryptographic operations should be implemented as the building blocks of a trusted device. These should support critical functions including security lifecycle, isolation, secure storage, attestation, secure boot, secure loading, and binding of data. To implement the 10 security goals, PSA has defined the firmware framework for Cortex-M microcontrollers, which is defined in yet another PSA standard. It states that there shall be 2 isolated processing environments, one being called secure, the other one the non-secure processing environment. It does not specify how this isolation is to be enforced. The design, based on 2 Cortex-M4 microcontrollers, which communicate via an SPI connection, for example, is perfectly reasonable. The non-secure processing environment contains the RTOS, NuttX in our case, and the application code. And it has direct access to most of the device's peripherals. In addition, it can take advantage of the services being provided by the secure processing environment via some form of remote procedure calls. In the secure processing environment, there's a simple RTOS-like executive called the Secure Partition Manager. It schedules the partitions which are conceptually similar to tasks and provides means for communicating between those and the non-secure processing environment. The partitions contain the so-called root of trust services. There's a set of services defined in PSA standards, which are called the PSA root of trust services. Vendor-defined additional services can be implemented in application root of trust services. The number of partitions and their characteristics are declared in configuration files prior to build time. Some peripherals, typically the crypto accelerators, are assigned to specific partitions within the secure processing environment. Also, the root of trust secrets, which are typically cryptographic keys, are accessible only within the secure partition environment. The secure partition manager might provide isolation between itself and the application root of trust service partitions, as well as isolations between those partitions, typically via the Cortex-M memory protection unit. This is dependent on the security level of the respective implementation. The well-defined functionality provided by the PSA root of trust services is made accessible to application code via the PSA functional APIs. The corresponding PSA functional specifications define the respective C function prototypes and describe the provided functionality. There are 4 standard documents for cryptographic services, including key storage, attestation, secure storage services, and firmware update functionality. A separate certification scheme and framework is provided, which covers only the functional completeness and correctness of the implementation. This brings us back to Trusted Firmware M, which is the reference implementation of the platform security architecture. Trusted Firmware M source code is distributed under the BSD 3-clause license. The project is led by ARM, but silicon vendors also contribute to the project. As you would expect, the architecture picture of Trusted Firmware M closely resembles the one from the PSA firmware framework. Trusted Firmware M integrates MCU boot for secure boot and secure update, while the firmware update service is basically just a shim that translates between the PSA firmware update API and the MCU boot library code. As you can see, Trusted Firmware M provides secure partitions for all the PSA services. The partition-labeled platform on the right includes the entry point functions that are called from the non-secure processing environment, for which it serves as a communication gateway to the actual service partitions. Participating silicon vendors provide the hardware abstraction layer for their respective Cortex-M-based microcontroller, and this can include a device driver for the microcontroller-specific crypto accelerators. If not, then per default, the crypto services rely on the software crypto library from the Mbed TLS project. The product vendor has to extend the hardware abstraction layer for his respective board, for example, to add support for a specific external SPI NOR flash chip used for firmware updates. And furthermore, a vendor might add application root of trust services. The isolation between the non-secure and the secure processing environment can either be enforced by using two separate ARMv6 or ARMv7M microcontrollers, or by exploiting trust zone technology, which was introduced with ARM version 8M. The most cost-effective way to implement the PSA firmware framework is with a single microcontroller that supports the trust zone extensions. So let's have a short overview of trust zone technology as defined in the ARMv8M architecture. This diagram shows various states latest Cortex-M microcontrollers can operate in. If you only consider one half of the diagram, you get pretty much the operating states supported by ARMv7 or ARMv6M processors. The processor is in handler mode whenever it is processing an exception handler, and it is in threat mode otherwise. And while in threat mode, the processor can run at the privileged or the unprivileged level, which is controlled via the npriv flag in the control register. If trust zone extensions are provided and enabled, then the processor can additionally be in either secure or non-secure state. Which security state is active at any point in time depends on the address of the machine instruction that is currently being executed. This means the contents of the program counter register R15. Or more correctly, it depends on whether this address is considered secure or non-secure. Simplified, one can say that the processor is in secure state as long as it is executing trusted code, and in non-secure state while it is executing untrusted code. Note that this makes security state changes very cheap. Branching between addresses of different security attribution change the security state of the processor as a side effect. And this is very cheap compared to the exception handling that is required to switch the processor from unprivileged into privileged level. I said that the security state of the processor depends on the security of the address it is fetching instructions from. But who decides whether an address is considered secure or non-secure? For this, Trust Zone introduces so-called attribution units, which mark ranges of addresses as either secure or non-secure. There are two major kinds of attribution units. One is the implementation-defined attribution unit, or EDAU, which from the processor's core's point of view is a black box that provides a security attribute when fed with an address. The EDAU's logic is outside of the processor core and defined by the silicon vendor. Typically, it's a relatively simple piece of combinatorial logic that derives the security state from a small number of address bits. The figure shown on this slide is from ST Microelectronics reference manual for the STM32U5 microcontroller, which is Trust Zone enabled. It shows the address ranges and corresponding security attributes as defined by the chip's EDAU. In the shown excerpt of the 4 GB address range, the yellow-brownish ranges are secure and the pink ones are non-secure. Note that the memories, both flash and SRAM, are aliased to both a non-secure as well as a secure address range. For example, the 2 MB flash is mapped to hex 8 million as well as to hex Charlie million. This means that the same code can be executed with the processor being in either secure or non-secure mode. Obviously, additional access control is required. We will get to this later. The second kind of attribution unit is the Security Attribution Unit, or SAU, which provides up to 8 address regions, each one defined by a base and a limit register with 32-byte granularity. Each defined address region is considered secure. Non-defined address regions are considered non-secure by the System Attribution Unit. The SAU-defined address ranges are overlaid to the ones defined by the EDAU. A given memory address is considered secure if it is attributed as such in either the EDAU or the SAU or in both. Certain registers are banked with regard to the security state of the processor. The most prominent example is probably the stack pointer register. There is both a secure and a non-secure instance of both the main stack pointer and the process stack pointer. This means that when untrusted code is calling secure code, for example, the stack is automatically switched to. The same applies to the control register, which holds the npriv flag. Those function calls between security states will automatically switch the respective privilege level. Furthermore, some facilities are duplicated. For example, there are two instances of the memory protection unit for the two security states. Thus, Trusted VMware Secure Partition Manager can use the secure MPU to isolate the secure partitions from each other, while NuttX in protected mode uses the MPU to isolate the OS kernel from the user space application. The system tick timer is also replicated, which, for example, allows to implement independent schedulers in the non-secure and the secure processing environment. There are also two vector table base address registers, and those two independent exception vector tables can be defined for the two security states. Only a single instance of the nested vectored interrupt controller is provided, but it is trust zone aware. All interrupts can be configured to target the secure or the non-secure state. This means if a certain interrupt is configured to target the secure state, then the secure vector table will be used to determine the exception handler address and vice versa. System exceptions are either banked. This is the case, for example, for the system tick timer exception, since there are also two instances of the system timer, or they always target the secure state, such as a secure fault handler or reset exceptions, or they are configurable just as interrupts. The dashed lines in the figure show the possible state transitions due to exception entries or returns. Note that a non-secure exception can interrupt execution of secure code and vice versa. This also means that the NuttX scheduler can preempt a task that is currently executing in secure state. When this task is rescheduled at a later point in time, secure state is re-entered as a side effect of loading the exception return value into the program counter register. The solid lines show the function calls and returns as they can occur across security boundaries. The dotted line just shows the transition from privileged to unprivileged level by setting the npriv bit in the control register. By now we know that the processor is either in secure or non-secure state, depending on whether it is executing trusted or non-trusted code. In the AHB5 bus protocol, this state information is provided for every bus transaction via a distinct H non-sec bus signal. Trust zone aware components attached to the AHB bus metrics make use of this signal to enforce security. For example, a DMA controller might allow to set up secure DMA transactions only if the processor is currently in the secure state, which means if the H non-sec is deasserted during the respective bus transactions. A secure DMA transaction is one which deasserts the H non-sec during its own bus transaction. Peripherals that are not trust zone enabled require some adapter logic in order to attach to an AHB5 bus. For memory components such as flash and SRAM, this adapter logic would be provided by memory protection controller. Simple MPCs are configured via watermark registers. All addresses below the watermark are considered secure, and the ones above are as non-secure. If the MPC is targeted by a bus transaction while the H non-sec signal does not match the security attribute of the target address, then the transaction will be answered as write ignored read 0. If you recall that memories are typically aliased to both a secure and a non-secure address region, the MPC is the missing piece of access control that isolates trusted code from untrusted code. The peripheral protection controller is typically configured via a single bit, whether the peripheral belongs to the secure or the non-secure processing environment. If accessed with a non-matching H non-sec signal, the transaction is once again processed as write ignored read 0. For non-trust zone aware busmaster components, The master security controller defines whether AHB bus accesses from the bus master should assert the H non-sec signal or not. This concludes the short introduction to trust zone technology. Now that we have talked about the platform security architecture, trusted firmware M, and trust zone technology, we can move on to the actual topic of the presentation, integrating Apache NuttX and trusted firmware M. Trust zone technology has been designed to make the non-secure execution environment match the ARM v7m architecture as close as possible. Thus, as you will see, letting NuttX run in parallel to trusted firmware M does not require substantial changes at all. Providing the PSA functional APIs to NuttX application gets a little bit more involved. Let's first have a look at how the code is laid out in Flash in a typical implementation. The figure on this slide shows the layout for my STM32U5 based setup, which has a 2 MB microcontroller internal flash. In my setup, I'm distinguishing between firmware and application code. Now, the idea is that firmware is developed and respective updates are provided by the device manufacturer. Applications for the respective device are developed and maintained by third-party system integrators with a tool chain provided by the device manufacturer. Let's look deeper into the firmware. Two artifacts are the result of the firmware build process. There is the 768 kilobyte firmware bin binary image that contains the functional firmware code. It is a concatenation of a trusted firmware M image with the NuttX kernel image from a protected node build. It is installed by programming it at a certain fixed offset into the flash memory. It's here at hex 40,000. The watermark of the flash's memory protection unit is configured in early boot stages such that the NuttX kernel and the application code are considered non-trusted code, while trusted firmware M and everything below it is considered trusted code. The firmware bin image is signed with an RSA private key, and the signature is copied into the image trailer. This image can be programmed during device manufacturing, and it can also be distributed as a firmware update file that can be installed in the field. The second artifact is the 128 kilobyte BL2 bin file or image, which contains the second level bootloader code. BL2 is trusted firmware terminology. The MCU's ROM boot code is considered bootloader level 1, and the bootloader in Flash is considered bootloader level 2. The BL2 is basically an extended variant of MCU boot with support for the respective board. It contains the secure boot validation method for the functional firmware image. This means the corresponding RSA public key is linked into the BL2 image and used to validate the signature on the functional firmware image before booting it up. It also contains secure update functionality to update the functional firmware from an external SPI flash. The BL2 bin image is installed during manufacturing of the device, but this one cannot be updated in the field. STM32U5 specific security features protect the integrity of this image against potential attacks. The remaining flash areas in the trusted address range are used by PSA root of trust services as persistent storage. The non-volatile counters area, for example, is used to prevent firmware downgrades. It stores basically the last installed version of a firmware and can be used to only allow higher level firmware to be installed or updated. The one-time programmable area is used by attestation services to store device unique data like a serial number or a unique ID. And the ITS and PS areas are used as backing storage for the secure storage services. Minimal changes are required to make NuttX running in parallel to trusted firmware M, as long as you do not want to exploit the respective services. The basic system initialization is already done by trusted firmware M code that runs before NuttX starts up. Thus, system clocks cannot be configured by NuttX. Up until now, I am doing fine with providing an empty STM32 board clock config function and configuring NuttX accordingly. All peripherals that are configured to belong to the secure processing environment will not be accessible to NuttX and must not be enabled in the NuttX configuration. Back when I started with the integration work, the exception common code for ARMv8m would load certain fixed exception return literals into the program counter register during exception returns, which breaks the case when a non-secure exception occurs while the processor is executing trusted code. But this problem was meanwhile resolved when the code to support lazy FPU register stacking was removed. Of course, you need to provide a matching linker script for the kernel build. Trusted firmware M starts the non-secure code by fetching the initial stack pointer and the initial program counter from the first two vector table entries, just as in the hardware reset case. And TFM expects the vector table to be at the beginning of the non-secure code image. And if I recall correctly, this is about all that needs to be done to have NuttX boot up and run besides trusted firmware M. So let's look into what needs to be done to give access to the PSA functional API for applications. Besides the actual trusted firmware M binary image, the build process also produces the s_veneers.o object file, which provides the entry point addresses to 5 secure functions that non-secure code can call. Furthermore, the trusted firmware M repository provides source code that is meant to be compiled into a static library and linked to the non-secure code. This source code implements the PSA functional API based on 5 service functions that correspond to the 5 entry points in the s_veneers object file. All remote procedure calls from the non-secure execution environment to the root of trust services are tunneled through PSA connect, PSA call, and PSA close. Some shim logic must be provided to, for example, forward application calls to the PSA connect function to the TFM PSA connect veneer entry point while maintaining multitasking consistency. What I mean by that is that if, for example, one NuttX task branches into trusted code and is then preempted by the NuttX scheduler before returning to non-trusted code, and the newly scheduled task is also branching into trusted code, this might cause problems. There are basically 2 options to handle that. The first option is to link the veneers object into the NuttX protected mode kernel build and to provide a character device, def TFM, with 5 IO control commands that call the corresponding secure function entry points in the veneers object. A static library meant to be linked to the user space code provides the corresponding 5 C functions, which will issue respective IO control commands on the def TFM device. The def TFM device driver enforces serialization by use of a mutex. That means only a single NuttX core task can call the secure processing environment at a time. This is relatively simple to implement, and this is what I have currently implemented in my setup. As a second option, the static library that provides the required 5 functions directly links to the s_veneers object file. That means that applications are calling into the non-secure execution environment without NuttX being in the path, which means that NuttX cannot enforce serialization. Instead, the NuttX scheduler must be extended to inform the TFM whenever it schedules a new task. It informs TFM via the TFM non-secure client extension load context function of the task switch. TFM will accordingly switch the execution context for calls from the non-secure execution environment. This approach provides lower latency and reduces lock contention, but is somewhat more complex to implement. Have a look at the non-secure client extension integration guide on trustedfirmware.org for more details. With what has been described so far, the secure boot chain only guarantees the integrity of the firmware image, but not of the application image. Some extensions are required for NuttX to extend the integrity checks to cover all code running on the device. Furthermore, with the concept of shipping devices to third-party system integrators without any application code pre-installed, Some facility for device management must be provided by the NuttX protected mode kernel image to enable initial installation and update of applications, for example, via a serial port or a USB port. NuttX is also currently not capable of running without a user space image. For example, the STM32 user space function is called in early initialization code to set up the user space BSS and data sequence. And there's also some code in the generic NX bring up that requires the user space image to be present. Changes are required here. Also, the integrity of the user space image must be guaranteed before any information from it is being processed. This requires addition to the NuttX initialization logic for application startup. The integrity check will include a signature verification, which needs access to the corresponding RSA public key, which itself must be injected in the PSA cryptography services key store by the third-party system integrator. My plan is to work on these topics over the next couple of months. Okay, this concludes my presentation. Thank you for your attention, and if you have questions, I'm happy to answer them.
I think we don't have questions, only on comment, right, Maju? Could you please put the comment on screen? By the way, I am preparing the spreadsheet to do the draw, and so I will. Guys, we are preparing the material, so I want to invite others to to discuss here, okay? To keep the conversation and let the people in the YouTube know more. Ken, are you around? Greg, I hope that your sound is good. I can see Greg around now. Okay, Rob. Yeah, I think he was out. So, Ken, so I will ask you to be our temporary host there. Okay.
Yeah, I actually did have a question about the trust zone. I know that's largely driven by ARM, and there's a big push these days to go with the RISC core. I don't know, has there been any, have you heard of any developments on supporting any kind of similar, trust zone or secure boot for RISC-V processors that are coming out?
Unfortunately, I'm not very familiar with RISC-V.
Yeah.
That is why I asked for the physical memory protection unit, if this is more than just the MPU from ARM, but it appears to be pretty much the same as the MPU. So I don't think they have protection on the buses, right, to the peripherals, like TrustZone has.
Yeah, I don't think so. I didn't know if there was anything specific in TrustZone that it was, copyrighted by ARM, that they would have to implement something different, I guess, right? They couldn't probably implement TrustZone as it is what I'm guessing.
Yep.
They would come up with something similar along the same lines. But yeah, it definitely would require, memory protection units and stuff, which I know the processors, a lot of the RISC cores now have those, and some of the other ones are even capable of running Linux, right? They have a full MMU. But it takes more than just, protected memory to do a secure boot. So
yes.
Yeah, so I suspect that would be forthcoming at some point.
And on RISC-V, there are also things that are actually built into the ISA spec itself. For example, the RISC-V privilege mode. So typically those CPUs already have privilege mode for MS and U, but there are also in the upcoming ISA spec there is hypervisor mode coming and other things. So it's a little bit different than in ARM world, but the security is there both in the RISC-V specs.
Yeah, I was aware. I mean, they've had the hypervisor kind of extension in there from the beginning, although I don't know that they had it that well defined. It was, they had the 4 levels of security from way back when. I mean, I've been doing RISC-V cores for 6 years now.
Do you think
Go ahead.
Sorry. What do you think about RISC-V and ARM? Do you think RISC-V is going to be big?
I think so. I mean, there's more and more. In fact, I've even seen where Intel is now looking at doing some RISC-V microcontrollers. And it's like, okay, which was kind of some interesting news back in February. Yeah, exactly. It's like one of the guys at work sent me that text, like, what is Intel doing in RISC-V? It just doesn't make sense, right? So, which I guess they discovered, there's money to be made, even though the instruction architecture is open source. You can still make money by selling chips, right, or by selling IP cores, etc. In fact, that's what Open5 has done, which they were originally called Sci-Fi, purchased by Open Silicon, and now they're called Open5. I've put RISC-V cores in the process, my ASIC chips at work. I've actually developed one of my own, which is a very small state machine based. It's about, a fifth the size of some of the higher power ones that have pipeline architecture and cache buses and axes, so on and so forth. But I've got a specific use case for that. So I've used a couple of different ones. I've not actually used any of the ones from Open Silicon that have the cache controllers and the ability to extend to multi-core. Haven't had the need yet. Although when I'm doing this coming year, I'll be doing a 5 nanometer, which means even more transistors on the chip, and I'll probably be looking at doing something like that. And that's kind of one of the reasons why I was asking, because a lot of the applications I have are for mean, some of them are military applications, not all of them, and that's one of the things that have come up is security. And I know currently I haven't seen any offerings yet in the RISC-V community for anything like Trust Zone. I didn't know if you had heard of anything.
One thing I wanted to ask Craig actually while he was still here, as soon, or let's say from the point in time when NuttX became an Apache project, I think that Craig's commit frequency dropped pretty suddenly. And I was wondering whether he was doing that to be compliant to the Apache rules because the code shall not be owned by a single person, or does anybody know why he stopped sending patches?
I do know the history. I mean, I've been doing commits to NuttX. I haven't done any in the last couple of years. I've been busy at work, but I have been. In 2013, I was pretty active during all that. I know that basically, he's retired. He's getting up there in age. That's one of his concerns was how does he continue to support this long term, and that's why he was looking at moving it to Apache and having the community support it more than just one person, right? For longevity of it. So I think it's more that than anything. Of course, Greg's not here to say no, Ken, that's not right. But I do know that was one of his concerns even prior to going to Apache was the longevity of NuttX. He's not going to be able to to carry it forward for the next 10, 20 years, right? I mean, it's just. They'll be 110 still writing code, right? So, but whether that's why he hasn't been making as many commits, right? I don't know if Alan or any of the rest of the team has additional insights on that.
Yes, I agree with Ken. I think it is something like that because he was the father of the project all this time. So now with Apache, he wants to pass the ball for others. So it was difficult for all other developers because normally Greg solved all the issues very fast and he very smart to make things working, to make everything working. And then it's like you leave your children to take care of everything themselves. So it's a little bit difficult, especially in the beginning, right? But I think the NuttX community is doing good work. It is a little bit difficult at the beginning, but now things are starting to become more stable. We can see many commits every day and many pull requests. So things are happening very well. So yeah. And Aline, just a comment I want to put to let people know about the rules. Yesterday, what we did, everybody that just watched 3 presentations, we qualified them to be part of the huffle, of the final draw, sorry. But today, looking the spreadsheet, I realized maybe it's not too fair to let people that just watch 3 presentations and go out and still no more have the same opportunity that others that are here all day long watch the 10 presentations. So we decided to do different. Alin, if you can show the complete list of participants, the spreadsheet that I send you. So what's the idea? Yeah, we put all the names according with the people who are filling the form. So this way, if you fill the form 10 times, you have more opportunity than some people that fill only one time. This one that Ali is showing is the final raffle for the Xiaomi smartwatch. So this one have people from all the places in the world that are not allowed, for example, to receive some board from Sony that's not certified yet. So so this way, if you watch more presentations, you have more chance than others that watch only 3 times or only 4 times, for example. Okay. So I think we can start. Alin, let's start with the presentations. Sorry. Yeah. Let's see. Maximum number is 87. 8 and 7. 87. Eight. Yeah, Felipe Koval. Congratulations, Felipe Koval. By the way, I don't know if he received board yesterday. I think so. Let me. Didn't? Oh, congratulations, Felipe. 6, 8. Yeah, Yannick. I think he got board yesterday. Just let confirm. Winner, day 1. Let's see. Yes, he got one already. Six is yeah. Yeah. By the way, AS Philip Koval, we need to put in bold to indicate. Okay. So Robert Lippi, he already won yesterday. No, he didn't receive yesterday. So sorry, repeat the number. I was. I'm trying to find here. Here. I think we got only one until now. Only Felipe. Yeah. 53. Okay, so we have only 2 boards. So we have more 6 boards to. Okay, here again. So please. 8-2. Congratulations. Let's see. Yeah, he did receive yesterday. So we have 3 boards and we still have more 5 boards, right? Yeah, I think he also didn't. He didn't receive. Let's confirm. Yeah, he didn't receive yesterday. Congratulations. Yeah. Okay.
Sorry to interrupt. Bertrand won a board yesterday. I'm seeing here. Can you check this information?
I have the list for yesterday. He's not selected.
Okay. Sorry.
Yeah. So we have 4 boards and yeah, here again. So 81. Roberto. Also Roberto Lipies yesterday. So another 48. 48. That's him. By the way, Ali, I think we need to find a way to show your both screen, right? Because people cannot. Okay, it's no way to find both at the same time. Yeah. Sorry, 28. David Sugar. Yeah, he didn't won yet. I think only three now. Let's confirm. 1, 2, 3, 12. Gabriel Aguilar Lemos. He didn't won yesterday as well. So what's the other? I think only 2 more to go. Yeah, he didn't won as well. $69. Robert Leap again. So, 15. Yes, hearing. Okay. Congratulations, Eric. By the way, he sent me the link for the all the positions of the videos from the presentation of yesterday. So if you go in NuttX channel, you try to watch the presentations of yesterday, and you can see in the video description there is now a link for each position. He did it in the previous event as well. Thank you, Ari, very much. Okay. Yeah. Now, Ali, if okay, I will follow here. Maybe later we can show the listing, but yeah. 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 We put we put no Brazil, but it's other countries as well. We just use Brazil because almost 80% of all the participants are from Brazil. Okay, so but now for the great prize for the Xiaomi smartwatch, all the participants from Brazil. Yeah. Yeah. Now. Yeah. Now you need to change the final number in the 167. Who the winner? Number 14. Let's see, 14. Adriano Henrique. Oh, sorry. Yeah, yeah, yeah. Do you want I share my screen or do you want to share? Oh, let's see. Yes, Adriano. Congratulations, Adriano Rezende. I am very happy to that someone from Brazil win this great prize because as you saw, we have many people from Brazil, and unfortunately, because this board is not the other board is not certificated to Brazil yet because the 3G, the Brazilians cannot participate. But finally, the justice was done in some way. So I'm happy to see it. Congratulations, Adriano. Let's say congrats. Yeah, and nice to see he's still here for all the events. So congratulations, you deserve it. So in the next year, right, Ali? In the next workshop, we want to see Adriano developing some applications to this smartwatch running Netx. Yeah, me too. So, guys, we are finishing our workshop today. So I want to thank you initially, Ali, for doing all these happen. Without him, it was not possible. And also Maju for being here today, help us, because as she explained yesterday, she was competing in the volley championship, and fortunately their team won. So thank you for being here today. And so, guys, I want to ask everybody here to turn on the camera. Maju, thank you very much for your great help. As Aline can say, yesterday was very, very difficult for us, right, Aline? Today, it's moved. So, guys, I am very happy to have all you here, and I hope to see all you again the next year. So each one of you to be here decide give up other things. Maybe you could have go out with your family or enjoy some party or other thing, and you are here to make our event big, our even greater. So we want to say thank you very much for all your effort to do that, and also thank you guys for making Netx this great RTOS. Without you, without this community, we couldn't do anything like that. So thank you very much. Thank you, Rob. Thank you, Ken. Thank you, Aline. Thank you, Yuka. Thank you, Michael. Thank you, Mark. Thank you, Maju again. Thank you, Felipe, that you was here presenting about the motor control using Open AMP, and also all the participants that was watching us in the YouTube. So I know it's not easy for all you to watch the presentation, because some are more technical and maybe we don't have this skill to understand everything, but over the time you are getting more information and you get more understanding about NuttX. So it's really, really great. Now, by the way, Ken, I am curious about your t-shirt from the first day. What is in your t-shirt? Bad joke, bad part, that. Nice. Yeah.
A gift from she thinks I live at the intersection of bad jokes and dad farts, I guess.
It was a gift for your
for Father's Day. Yeah.
Nice. Yeah, I like it. So, guys, thank you. If you want, some of you want to say something and want to say anything or want to say some comments, so please.
It was great.
Ahead.
It was a lot of fun, and thank you for the organization. Yeah, really great.
You're welcome. Thank you. So I think we are done, and this is our first time, our fourth workshop. The first one was in face-to-face in Netherlands, in Gouda, and I hope next year, right, Ali, will be. Yeah, I hope next year we'll have a real virtual, real and online events. It should be nice. Yeah. 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 I think maybe I want to suggest Brazil, as many people here are already from Brazil. So I suppose some of you don't know our country yet, so I think should be a nice travel to here, and we can decide where to do it. Maybe in Campinas, maybe here in the south in Florianopolis. Let's see. And so thank you guys. It was really amazing, and as every year. And so, as I said to Ali, we are still learning how to do presentations. I don't know how to do. Sometimes I make too much mistakes, and I even can be a host, and I cannot say any English word correctly, but
you sound perfect to me, Alan.
Oh, thank you. You're so kind. Yeah. 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 Next year we will do better. Yeah, hopefully in person. So
okay, bye-bye.
Bye-bye, guys. Have a nice rest of weekend.
Yes, thanks to everyone.
Thank you. Bye-bye.
Bye-bye.